Since already running a little bit late, introductory remarks. So first of all, thank you all for coming, visiting Minnesota despite our lovely spring weather. This conference, hopefully it will be really exciting. I feel like this is really one of the most, if not the most exciting time to be at Pentalayer since I've been alive. Hopefully many of these talks will make you feel that way too. Some logistical things. So coffee breaks will be roughly every 2 talks in this atrium here. We will also not be providing lunch, but locals can sort of help guide you. There's a lot of food around here in small groups. After the main sequence of talks today, there will be a reception with various different kinds of refreshments. Can give you an opportunity to meet some of our amazing graduate students and postdocs here. And then after that, while we do not have a banquet today, we're going to make an effort to go as a large group to a nearby food hall brewery complex, weather permitting. Final logistical thing is there will be a banquet tomorrow. So that will be all paid for and provided. Before we begin, I also just want to thank the Simons Foundation that really made all of this possible. So without further ado, Long is going to tell us about chiral superconductivity. By the way, talks are all 30 minutes plus 5 for question.
Okay. So give me 5 minutes.
Yeah, I'll give you a 5-minute warning.
Okay, good. Yeah, it's good to be back here. I was here, I guess, a couple months ago, maybe. I know the weather's, I can guarantee it's better than 2 months ago. Okay, so I'm going to tell you about the 2 different phenomena. The first one is probably at this point rather familiar to most of you, and I'm going to spend most of the time talking about the superconductivity. Okay, so these are the people who contribute to the experiment I'm going to share with you. My group at MIT. Zheng used to be a postdoc in my group. Now he's a PI at Florida State University, and we enjoy the benefit of working with our theory colleagues and the ray assurance group for some capacitance measurement, and collaborators when I didn't even have vector magnets in my dual fridge. So part of the data was actually taken in Dominic Zombo's lab in Switzerland. And of course, nice HBM crystal from NIMS. Okay, so I will start to encourage you to think about electron correlation and topological phenomena, right? Emergent from interactions of many identical particles in the crystals in a setting called crystal. We know that 2 prominent examples is fractional quantum Hall and the superconductivity, and they used to happen, usually happen in very different materials, and in very different experimental settings, right? Fractional quantum Hall needs high magnetic field to get lambda level quantization, and the superconductivity does not like magnetic field, right? You can find superconductor that's sort of okay with getting along with magnetic field, like type 2, or like 2-dimensional superconductors, the flux can penetrate through, but in general, superconductors do not like magnetic field. So what I'm going to show you today is that these 2 physics actually can happen in the same material. Not only in the same material, it happens in a way that there's a sort of interesting twist. The fractional quantum Hall effect I'm going to show you actually happens at 0 magnetic field. Well, the superconductor I'm going to talk about itself is a magnet. Okay, let's see how that can work. Okay, if you ask like as an experimentalist, where to find correlation topology, right? As a naive experimentalist, my view is that, okay, you probably want to find a flat band or at least a flat portion of some band dispersion. So when you feel electrons in that flat part, you have correlation effect prominent because the kinetic energy is dwarfed by interaction. On the other hand, if you talk about topology, there's this very basic concept called barrier curvature, which leads to anomalous velocity of electrons. And if you integrate that by measuring the Hall resistance, you can measure some integer quantized number called Chern number, right? And it seems that you don't need to look at a very complicated material to look for these two essential ingredients. Graphene or graphites, at least part of that, already have both essential ingredients, and that should be the place that we understand what's going on first. Okay, and of course, I'm not talking about monolayer or bilayer exfoliated graphene. I'm talking about multilayer graphene that has some internal structures in it. Okay, so this is an optical image of an exfoliated 4-layer flake. This corner here is 3 layers. If you look at it on the optical microscope, the optical contrast simply tell you this is the way that most of the experimentalists in the audience, if they work on graphene, this is how they select the flake to use. Well, it turns out even if within this seemingly homogeneous region of 4-layer graphene, there's a lot of internal structures that you can simply use the in-gas camera to visualize, right? This is at 1.5 micrometer wavelengths, 3 times of the visible light. It's more sensitive to the subtle difference in the electronic band structure and optical transitions. So that's why it's revealing these internal structures. And different contrasts here actually correspond to different way of stacking the layers of graphene on top of each other. Okay, it's stacking order difference, but I'm not stacking it. I'm just exfoliating using tape and randomly find a flake and look at it. So nature does a job for us by stacking these carbon layers in certain configurations. There are 2 leading ways of stacking the layers due to the energy consideration. The leading order is called Bernal stacking or ABA stacking, while the metastable form is known as Rhombohedral stacking or ABC stacking. If you go beyond 3 layers, it will become AB, 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 and ABC, ABC, ABC. Of course, there are other intermediate stacking orders. And in principle, every layer you add on top of it, you've got to choose to go left or right. That makes things very complicated. Luckily, these 2 are the leading stacking orders. And the Rhombohedral stacking order is what we're going to talk about. It has this kind of staircase structure. And as a consequence, if you only care about low energy band structure, you only need to look at this orbital down here and this orbital at the very top layer, because everything else will basically push themselves away from 0 energy through the very strong, like hundreds of millieV interlayer coupling or hopping. So the low energy band structure will, to the least order will be proportional to momentum to the nth order, where n is a layer number, right? That's because this one, in order to talk to this one, have to hop through all the n layers, and that simply give you k to the n. So if you are looking at the monolayer, it's a linear Dirac cone that we are familiar with. But if you go to something like 4 to 5 layers, you actually get flat bands naturally in this crystalline form. Okay. For example, in 5-layer, if you estimate the density of space here and the effective mass, this is already comparable to the bare electron mass. Okay, going from monolayer, which is very light mass when you're close to Dirac cone, the Dirac point to bare electron mass, there's a huge enhancement of the flat band effect. And this is without twisting. This is without moire. This is even without gating. So nature does a job for us, and all what we need to do is to find the right region to look at. And of course, because these 2 orbitals are at the different layers, you get a further tuning knob by applying gate electric field to put these 2 orbitals at different energy. And that electrostatic energy will, potential energy will translate into a band gap open, right? Now you have a semiconductor, and you can tune the band gap very conveniently by just tuning the electric field. so what happens to the flat band is that although you have some with flat band here, large density of states to begin with, but when you open up the band gap, you are squeezing the bottom of the conduction band even more. So you can enhance the density of states here to be even several times bigger than here. Okay, so you have a very tunable flat band system. On the other hand, this band crossing point is also a good place to look for barrier curvature and topology. Once you open up the band gap, there's big barrier curvature distributed around both the conduction and valence band. And the rule is if you look at the K and K prime value, they have to cancel each other because the whole thing, in order to preserve time reversal symmetry, needs to have two states cancel, right? Of course, if you have flat band and you have some spontaneous degeneracy lifted due to the flat band effect through exchange interaction, they do not necessarily cancel because you can have more population in one valley. And that's how you can actually pick up a net accumulation of barrier curvature and Chern number to make the system topological. Okay, so with those in mind, we just did the experiment, right? So we first look at the 5-layer rhombohedral graphene, standard Hubbard, top gate, bottom gate to control charge density and gate electric field to tune the band structure. Right, then it's just a DC transport experiment, measure longitudinal resistance as a function of N and D. You got a very complicated phase diagram. I'm not going to talk about any of these, but just to let you know that the majority of the feature that you're looking at here is due to the flat band effect and some kind of symmetry breaking. Especially, I feel I never got enough time to talk about this work, but it's quite interesting that you actually can get integer quantum anomalous Hall effect with a Chern number 5. And this is down in the absence of Moiré effect. This is just putting 5-layer graphene on a TMD layer. You can ignore all the Moiré effect in that setting, and you get the largest Chern number of any quantum anomalous Hall material so far. I'll be happy to talk about how that works later. And I'd like to acknowledge that we dive into a range of layer number that was, basically ignored by previous people, but there have been works at both the thin layer limit and the very thick limit. They all find some kind of correlation effect. It's just like, seems like there's an intermediate range of layer number that makes things super interesting. Okay, so first, I promise you two things, right? This is the first one. If you put 5-layer rhombohedral graphene on a Moiré superlattice with one of the HBN, right? This is like close to 0 degree, 0.7 degree, and they got a spatial beating of about 12 nanometer, which is mostly set by the lattice mismatch between graphene and HBN. You can do the same trick by applying gate voltage. You open up the band gap. You get this very flat bottom of the conduction band. Okay, now you can put charges to this very flat part of the band structure. And that gives you something really bizarre, even in today's view. Basically, the longitudinal resistance have two regions, okay? This low density region here at the high displacement field is very, very resistive. While the high density half has a lot of anomalous Hall signal. This is at 0 magnetic field. Okay, so clearly time reversal symmetry is spontaneously broken here, most likely due to valley symmetry breaking. And if you look at these vertical features at the constant density or fitting factor, these long stripes correspond to integer and fractional fitting factor of the Moiré superlattice. So one here corresponds to 1 electron per Moiré, like per 12 nanometers. And if you look at the line cut of Rxx and Rxy, at the integer filling Rxy is quantized at h over e squared. So this is a Chern number equals 1 state. And the Rxx go to 0 within noise level. This is pretty good. At that time, this is back in 2023, we got 6 fractions at fractional fitting factor, like 2/5. And the Rxy is h over e squared divided by that fitting factor. Okay, 6 of them all following the Zhang sequence. And they all have dips in Rxx, although not to very low value. But now we know it's just a matter of electronic temperature and sample quality, because now in our best sample, we actually can observe a total of 8 fractional states And the residue of our XX here at the lowest temperature we can access here is about like a 500 ohm. Last year, no, in 2023, this was about like 7 or 8 kilo. Okay, so within 1 year, without much effort, like making tons of samples, we can actually got like 18 times smaller resistance than before. So everything is moving in the right direction. If you're familiar with the history of gallium arsenide, that's roughly how it works. At the beginning, 1/3 has 8 kilo ohm residue, but soon it got reduced, and now we know it's pretty much zero. Okay, and if you zoom into this, fractional fittings, you get this very nice plateaus that is very precisely quantized within like 0.1% level of what is expected. Okay. However, the theory is still not clear what's going on. I'm just listing part of the theory that has been published after the experiment. There's no consensus yet, although I've heard from Alan McDonald and Andrew Bernovik's group that they are making some progress in thinking like what is going on here. So hopefully soon we can figure out why and how this system can host fractional quantum anomalous Hall and why it was not realized by theorists in the very first place. Okay, so I've shown you that flat band plus barrier curvature plus Moiré effect, although not entirely clear, result in fractional quantum anomalous Hall effect at 0 magnitude, right? And next I'm going to make things even simpler. I'm going to get rid of Moiré. That's very easy to do in experiment. You just increase the twist angle between graphene and HBN, you make it big. So the spatial beating in real space will be very tiny, and then it corresponds to a very big momentum in momentum space. And it doesn't matter for the low energy physics that happens around the Fermi surface. Okay. Some of theory suggests, okay, maybe you get fractional or integer anomalous Hall crystal. But what we found is superconductor. You probably know that there are many superconductors in two-dimensional material, especially graphene. But there's good reason to believe the superconductor happening in this system is quite different and bizarre. Okay, so superconductivity has been observed in both twisted and crystalline graphene system. And this is the work that we did on ABC trilayer graphene, proximatized by TMD. We got a rather complicated influence of spin-off coupling on superconductivities. One of them got completely killed, the other one got enhanced, and this one got induced from nowhere. It's a very complicated role. Okay, but I would like to focus on the setting without Moiré and without spin-off coupling, without TMD effect. This is just bare 4-layer or 5-layer rhombohedral graphene sandwiched by HBN. Both sides have large twist angle. There's no Moiré effect as far as we can tell. And the phase diagram shows 1, 2, 3 regions to be zero resistance in both 4 and 5 layers. They look quite similar, right? And they both share this big insulating region at low charge density. We tend to think of as Wigner crystal, but it's to be confirmed. Okay, just to put it in a context, we're still talking about using electric field to open up the band gap and make the bottom of the connection band to be very, very flat. And then we put charge here. Okay, at the displacement field less than this value, the band is probably not flat enough. And at the displacement field bigger than this optimal value, the band structure starts to develop this Mexican head shape, which also destroy a simple flat band. Okay, so as a function of temperature, 4-layer has slightly higher TC than 5-layer. Both of them has like 200, 300 millikelvin range. It's not very high. And both of them show reasonably good differential resistance curves versus current. The 4-layer especially shows this very sharp resistance peaks at critical current. And if you look carefully, there's a clear asymmetry between the negative and the positive side. And that is known as superconducting diode effect. We haven't really investigated systematically in our sample. It seems to be there, and many people believe this suggests that time versus symmetry is broken. We can talk about that later. I will show you more direct evidence of time symmetry breaking later. Okay, so the first thing that you can do once you get a superconductor is to test it against magnetic field, right? And see if there's anything weird. So we first tested against in-plane magnetic field. Okay, to put in the context, a TC of 180 millikelvin in a pentalayer correspond to a Pauli limit of roughly 0.34 Tesla. However, experimentally, this superconductivity largely survive even at like 5 Tesla. We have to stop there because there's a limit on the magnet. But both SC1 and SC2 can persist to like way beyond the Pauli limit, at least 15 times. So this is strongly suggesting the superconductor is likely to be a spin polarized superconductor even to begin with. And not only is it robust against in-plane magnetic field, it turns out to be also super robust against out-of-plane magnetic field. If you're familiar with graphene literatures, in both twisted and untwisted and crystalline graphene, usually the out-of-plane critical field is a few millitesla, tens of millitesla at most. Twisted trial graphene may be able to persist to more than 200 millitesla. But in this case, 4-layer can persist to like 0.6 Tesla, while 5-layer persists to something like 1.4 Tesla. It's quite robust, and this even the outer plane critical field is several times beyond the Pauli limit. Of course, that's the wrong thing to compare, right? There's a lot of orbital effect here. So this is quite bizarre. But the most to put in the context, how big is a critical magnetic field of 1.4 Tesla? If you compare the coherence length you extract from the critical magnetic field with the interparticle distance, which you can extract from just the charge density, you actually can find that they're already comparable. The SC1, at least in the pentalayer, is already at the crossover from BEC to BCS if you just look at these two length scales. Okay, and experimentally, the most striking observation we made is there's hysteresis in the superconducting state. So what do I mean by hysteresis in a zero resistance state? So basically, it remains zero, but some small finite value until there's a finite resistance peak. But after that, it goes back to zero as you scan magnetic field. And when you go back, it repeats this behavior. It's like kind of mirror image, and with a delay, right? So this looks like a magnet. It has clear magnetic hysteresis. This happens to both SC1 and SC2. And we also notice that sometimes when you get a device and you scan the charge density to get this map, there could be a lot of fluctuations in certain part of the phase diagram, right? You don't see fluctuation here, you don't see fluctuation here, but here you see fluctuation in the SC1, SC2, and the neighboring metallic state. And even if you park at a specific point inside the superconductor and watch as a function of time, sometimes you can observe this like random temporal fluctuations, which also reminds you of what a small mesoscopic magnet does because thermal activation can randomly flip it. So all this suggests that somehow the superconductor behaves as a magnet. It's a magnetic superconductor, but it's probably not the same as the ferromagnetic superconductor that you get from heavy fermion system. Well, you can ask like in this system, does this magnetism come from spin or orbital, right? Because you can have both. But luckily, we're in two-dimensional limits. We actually can experimentally tell them apart. So the idea is that orbital magnetization has to point either upward or downward perpendicular to the plane because the motion is confined in the 2D plane. Well, spin can feel free to respond to magnetic field pointing in any direction in the 3D space. So the first thing we did is to apply a large in-plane magnetic field to completely fix the spin direction. And then we scan the outer plane magnetic field to see what happens. And turns out you can still have hysteresis, just like what you got without applying a big in-plane magnetic field. So this tells you that what's behind this hysteresis is some orbital motion or orbital magnetism instead of spin. Because 2 Tesla is way bigger than the range of outer plane field I apply here. So spin is always polarized in plane. Of course, you can do the double check it, right? You can apply a small outer plane magnetic field to lock the valley degree of freedom. And then you sweep in plane magnetic field in a big range. Well, this time you don't get hysteresis. So this is telling you that once the valley or the orbital degree is completely fixed, spin itself will not give you hysteresis in the resistance curve. This all makes sense, right? Because we're talking about a system that spin-off coupling is very weak. Trevor is probably going to tell you it's not that weak, but it is rather weak. So you should think about spin as really respond to magnetic field pointing in any direction in 3D space. Which direction you put your magnetic field, spin will simply follow without the delay. Well, orbital is kind of like a Z2 thing. It can be either in K or K prime. Of course, it can also be a superposition of K and K prime on this Bloch sphere, but the orbital can easily give you a delay when you scan magnetic field. Okay, so our picture is like when you scan magnetic field and get this hysteresis, probably what's going on is you can have either polarized completely in the K valley. The Fermi surface completely polarized in K valley, so the superconductor is a K valley polarized superconductor. And when you scan magnetic field and introduce a domain wall between K and K prime, the transport through this domain wall is naively resistive because you have to at least overcome the large momentum mismatch when it tunnels through. Of course, there's more to investigate here, but at the lowest order, we think this resistance peak may indicate there's a domain wall between the two voltage pairs of electron. And when the switching is finished at high enough magnetic field, when you're beyond the coercive magnetic field, the whole thing just got flipped and you got zero resistance again. Okay, so basically that's how we understand the time versus symmetry breaking and the magnetic behavior of the superconducting state. And you can ask whether this is a property of the Fermi surface above TC, or this is something that formed when together with superconductivity. And turns out even above TC, you have signatures of anomalous Hall resistance and magnetic hysteresis. So you already have valley symmetry breaking in this part of the phase diagram, right? This dashed line is the SC1 region, and the star and the square position are both inside SC1. Okay, so there's already valley polarization above TC, and that property got inherited by the superconductor as you cool down. Of course, once it becomes superconducting, you can't tell the RXY unless you're at the switching point. Okay, and we can also do characterization of the neighboring metallic state. This is a superconductor. This is the neighboring metallic state. It turns out the metallic state nearby has anomalous Hall at the same temperature where superconductivity develops. And that tells you the valley symmetry is broken. And you can further do quantum oscillations and count the period of this oscillation. And that suggests this neighboring metallic state is a quarter metal. So you are likely to have a spin and a valley polarized, a quarter metal, right next to the superconductor. And because at a high enough temperature, they just merge into one. You couldn't really tell which part is going to be superconducting. We think the ground state of the superconductor is probably also a spin and valley polarized superconductor. I have more data to show that if you're interested. Okay, so basically to summarize, the observations that we got superconductor is very robust against both in-plane and out-of-plane magnetic field that has hysteresis and anomalous Hall above TC. And comparing to other superconducting in the literature, we found that 2 and 3 are simply unique. There's no other example of these two among all the other superconductors. So of course, this has a lot of implications that needs time to further investigate it. But at this moment, we think it's a spin triplet. And there's a large, there's a momentum for the Cooper pair, given that the valley symmetry is broken. And we think the time versus symmetry is broken at the orbital level. So you can already tell left-handedness and the right-handedness of your Cooper pair without worrying about how the other parameter look like, right? Even if the other parameter delta is a simple px, the fact that the two electrons come from the same valley automatically defines a chirality due to its angular momentum. Okay, so we call it chiral superconductor. What's not clear at this moment is whether the other parameter is p plus IP or simply p. whether it's topological or not, whether it's Moiré or not, and what is a magnet. Okay, so basically just emphasize we are talking about the superconductor where the two single electron wave function come from the same value, and that already breaks orbital level time reversal symmetry symmetry and defines a chirality. We are not talking about the px plus IPY at this moment from the experiment. Okay, but this triggers theorists to think about what's going on here, and several works found it makes sense to be P plus IPY. I don't know if at this point we should regard this as a solid knowledge, or that's something still to be tested by experiment. Okay, so lastly, let me show you this. Okay, I hope I have convinced you that rhombohedral multilayer graphene can house fractional quantum Hall at the zero magnitude, and this very phenomenologically bizarre superconductivity in the same material. The only difference is that when you have a moire with HBN, you got fractional quantum anomalous Hall, and when you don't have moire, you got superconductivity. Okay, it's kind of interesting to note that these plots are plotted in the same density and the displacement field range. If you outline the boundary of the superconductor here and overlay it here, you see there's pretty good overlap between the anomalous Hall region and this weird superconductivity. So somehow moire completely changed the ground state, and that's something to be figured out. Okay, and I'm borrowing Liang Fu's view on this. Think about helium-3. It's the simplest possible system. Well, the rhombohedral graphene, because it has no twist and you don't need moire to get the superconductivity, maybe this is the electronic analog of helium-3 with some just electron gas, dispersion, barrier curvature. The interaction does all the job to make it interesting. Okay, so with this, I like to just wrap up here.
Good time for questions. Andre.
I have one question, but
Sure.
let me first ask about your last slide, comparison helium-3. Did I understand correctly that you are saying that superconductivity comes out of valley polarized and also spin polarized?
That's what we think is going on.
But then it's not helium-3.
Oh, okay. It's not the exact analogy. It's just
set not ordered state in helium-3 from which superconductivity comes in.
Okay, I see what you mean. Yeah, we're just trying to emphasize how simple this setting is.
Sure.
Yes.
And very quick question. At one point, you had a slide with Mohit picture with BCS crossover.
Yes.
Do you have any evidence in your resistivity measurements that resistivity drops before superconducting transition? In other words, evidence for preformed pairs behavior from resistivity.
I don't know how accurately the resistance itself can tell you that, but I think it's a very good question that we probably should, I don't know, like look for gap above TC, maybe nurse effect, things like that. That's on our list. Yes.
So you had a slide saying that this is an FFLO superconductor. How do you measure that? Like, is there some weight for you to detect the Q at which your ground state is ordering?
Okay, so this is a dual gated sample, which means you can't do STM at least easily. Yeah. There's one technique that Shahal Ilani is practicing. It's called the atomic SET, which may have, which should have the good spatial resolution. And I'm working with Shahal to see if this actually can be a way to probe any spatial structure in the system. Not only the superconductivity, but also the Wigner crystal. That has even bigger length scale.
Sure.
Yes.
You show that there is also like integer quantum anomalous Hall effect and like Pentalayer graphene, right? Even if you don't twist it, but you stack it on top of TMD.
Yes.
So due to this lattice constant mismatch, there's also like intrinsic moire. Do you think that plays a role, or?
Well, yeah. So technically, there's always a moire when you put two material like this, but that will correspond to a very big momentum. And if experimentally, how we know that's different from the moire, way to get quantum anomalous Hall is when we observe quantum anomalous Hall, we're at charge density 0. It's Haldane physics. It's not Moiré physics. For Moiré system to develop integer quantum anomalous Hall, you have to break the value symmetry, which means you put in a certain amount of charge to completely fill one value. That won't be at charge neutrality. Well, Haldane model is at charge neutrality. Yes.
How would you expect the Fraunhofer oscillations to differ if the pairs time versus symmetry breaking?
I'm sorry.
How would you expect the Fraunhofer oscillations in PID to differ?
Ooh. First of all, we haven't really got clear Fraunhofer. I think there's probably something, if you look carefully, there's a weak modulation if you choose the right combination of charge density and displacement field, according to the experience of Andrea and Stefan on crystalline graphene. How that looks like when you have P plus IP superconductor, I think if you make, if you look at the little Parks effect, and if you do have some domain wall in there, maybe you can see a shift of pi in the Fraunhofer. But we can talk about that experiment later. Yes.
Data, are you sure it's going to be a gap superconductor or gap?
How can I tell at this moment?
I thought you have some DIDV curve or.
Yeah, I have the IDV curve, but that doesn't tell you if it's gap or gapless, right? I mean, you cannot say, "Oh, this is flat, so it's gapless." No, that's not how it works.
You can look at temperature dependence.
Yes, you can look at temperature dependence. You have to squeeze yourself into a narrow enough temperature range well below TC and ask if the superfluidity density changes. We are aware of the microwave experiment people have done with twisted graphene. At this moment, I think it's probably challenging because the TC is a bit too low. Yeah. I should note that if you track the archive close enough, there's a report from Leo Lee's group at Brown who checked the 6-layer sample. It's one sample, one pair of contact. They get the TC of 1 Kelvin. We're trying to repeat that and see if it's real.
All right, any last questions? Not, let's thank Long.
Yeah. Okay, thank you.
Next up is Trevor Arp from UCSB, who's going to continue the theme of Rhombohedral graphene.
Okay. Hello, I'm Trevor. I'm a postdoc in Andrea Young's lab at UCSB. And I want to talk to you today about some recent work we have on the magnetism of pentalayer graphene. Very much the same system that Long just gave a very nice talk on. So in this, we're talking about Rhombohedral graphene. That is this kind of ABC stacking order of multi-layer graphene. So the sort of really notable thing about this that's been expanding the horizons of physics in recent years is that you get very tunable Van Hove singularities in this rhombohedral graphene, both as a function of layer number. Like I said, you can kind of keep adding layers in this ABC staircase pattern in order to sort of really enhance the density of states even at 0 displacement field. But you also get to apply this displacement field. You get to introduce an interlayer potential. And if we say start with rhombohedral trilayer graphene, and we introduce an interlayer potential, what that does is it really flattens out these bands and enhances this sort of, the divergence in the density of states. And we can end up with a lot of electronic interactions and new physics from that. So this sort of approach of sort of building up the Van Hove singularity has really resulted in a lot of discoveries recently, in particular in Pentalayer with the fractional anomalous Hall effect, and of course the chiral superconductor that Long just talked about quite a bit. So this, in particular, the chiral superconductor was pretty sort of inspiring to us at the Young Lab, because we think a lot about magnetism and magnetic graphene, and to combine a superconductor with that is rather sort of motivating, especially since to us magnetism is a very good experimental quantity in order to look for physics in these systems. So that's what I'm going to talk about today, is how you can use magnetism on graphene as a way to sort of understand these states. So I'm going to build up first an experimental toolbox focused mainly on Rhombohedral trilayer graphene, because it's, at least for me, a bit better understood. And then I want to show you some newer results we have on 5-layer Rhombohedral graphene, the Pentalayer, and sort of conclude with what we can tell so far about the parent state of the chiral superconductor, along with talking about. I would say that the results on Pentalayer are pretty fresh, so I'll largely be sort of empirical and experimental about them. Detailed modeling come later. Now, I have to thank these 3 lovely gentlemen for all the help they gave on this experiment, especially Owen, who my partner with a lot of these experiments, and Young, Jun, and Ben, who actually made the Rhombohedral graphene devices I'll be talking about. So to begin with, as I've showed this graphic before, you are taking graphene, in this case trilayer Rhombohedral graphene, and applying an interlayer potential in order to increase the to open up the gap and then to increase the Van Hove singularity. In practice, the way we do this is we take Rhombohedral graphene and we sandwich it between 2 graphite gates with hexagonal boron nitride as just very nice, clean dielectric spacer. And then we can apply a differential gate voltage to get a displacement field across the Rhombohedral graphene. And if we do this, you can, again, apply the interlayer potential. And what our basic expectation is to start breaking the symmetries of graphene. So graphene, as I mentioned, has sort of 4-fold symmetry. You always get 2 for spin, but then it also has this valley degree of freedom. So if we think about fully sort of symmetric graphene, it has electrons that are spin up and spin down on Fermi surfaces at the k and k prime points. And then as we have interactions, you start to break that. You can think about this in the context of the classic Stoner criterion, where once you turn on interactions, like at exchange, and you might get spin polarization into a half metal, where you only have spin up electrons. But you can also get valley exchange, and thus get a quarter metal, where you are spin and valley polarized. This is sort of the cartoon picture. In reality and graphene, you can get all sort of permutations that you can imagine, 3-quarter metals and the like, but also things that don't fit nicely into the sort of Punnett square representation, like intervalley coherence. So our question, yeah.
So is there a reason that you're showing the spin polarization as happening, kind of higher in the hierarchy than valley polarization, or might there be a situation where it first wants to valley polarize and then spin polarize?
In general, we don't see that. I don't think, in principle, I mean, a lot of this is based on like details of the the interactions, which can be very hard to calculate from first principles. And as you'll see, it sort of always does the spin breaking first. So our sort of basic expectation is that some of these symmetry broken states are magnetic, and that's how we're going to sort of go after them here. So if we want to measure a magnetic state, we can do transport, but we really like to do a direct measurement, or as direct as we can get. And for that, we're going to use nanosquid on tip microscopy. This is an experimental technique where we take a pulled quartz pipette and we fabricate superconductor onto it in order to make a squid at the very end of the tip. Squids are very precise magnetometers, and these nanosquids are no exception. We're typically getting nanotesla per root hertz sensitivity here, but in a extremely sort of local measurement. The sort of resolution is set by the diameter of the squid tip, which ends up being between 50 and 300 nanometers. We can bring that in very close to the sample, and so it'll be limited just by the size of the squid. This is sort of an extremely sort of sensitive and high-resolution technique, and that pairs very well with 2D materials and the geometries and signal densities that we expect. I will just sort of give one note about how we use this in practice. When I say you're nanotesla per hertz sensitive, you say nanotesla, you think about a DC measurement. And indeed, I'm going to show data that looks like DC. But in reality, there's often a lot of noise in DC measurements, especially 1/f noise. And the reason this has a frequency unit is because you tend to measure these things with some sort of frequency AC contrast mode. And the way we're going to do that here to get something like the DC magnetism out of it, we call this pulse gate or boxcar averaging, where if we have some gate-tuned magnetism, so you have a gate under your graphene and you apply a square wave of voltage to that gate. So this is just turning your voltage on and off very rapidly. Typically, we do this in the kilohertz. And you end up with this sort of pattern of response in your squid called a boxcar pattern. And what we do is called boxcar averaging, which is just to say that this is done as a function of time, but we're going to average over that to get the signal sort of that is different in time. And that means we're performing differential measurements, always relative to some state, which might just be charge neutrality, turning the whole device on and off. So I bring this up just to explain what you're going to see, but also because this sort of how you measure these things will become relevant as we go on. So we have this nice scan probe sensor. How are we going to use it on the graphene? So the first thing that you do with the squid tip is you bring it in and you sort of scan it over the surface of your sample. And what we will generally see is something that's fairly uniform, at least in Rhombohedral trilayer graphene. And so you see sort of a fringe magnetic field. If I have anything that causes a magnetization in the graphene, then you will get some fringe field that extends out of the device. And the squid tip being 100, 150 nanometers away from the graphene will be able to pick it up as like a surface field. So what we're going to do for most of the data here is to take the squid tip and sort of park it in the center somewhere of the sample and use this fringe field as a measure of magnetization up to some geometric factor. So what this ends up looking like and what a lot of the data I'll show is like this. Where, just to break this down, on the x-axis here, I have the charge density of electrons. And then on the y-axis, we're going to apply this sort of differential gate voltage in order to get displacement field. So as we start sort of down at the bottom, you have what I call the full metal, the fully symmetric graphene. And as you turn up the displacement field, you're enhancing the Van Hoff singularities and turning on electron-electron interactions. And now you're going to start to see some magnetic signal. First, we see magnetism from this half metal. And then as we keep going, we can see spin and orbital magnetism from the quarter metal. So the magnetism from spin, we are applying a small out-of-plane magnetic field to bias the squid. So you see the spins lining up. And then, as Long talked about, in these systems, there's a lot of sort of incipient, there's a lot of Berry curvature in the valleys. And when you start to sort of symmetry break into a single valley, you can get a large sort of orbital contribution that's out of the plane that is normally positive and negative in the two valleys and cancels out.
Sorry to interrupt, but why you are saying that when you increase displacement field, the electron-electron interaction increases? I thought that band becomes more flat, but there is nothing to do with electron-electron interaction.
I mean, in this case, I'm more meaning that you turn on exchange.
Okay, continue.
So this is these are basic phenomenology that we observe with displacement fields, and it can get more complicated and interesting, and we'll get there. But one thing to emphasize about this technique is that not every possibility is magnetized, and so we usually want to pair this Yankowitz technique with some sort of additional technique, and the one that we like to use is electronic compressibility. The way that you measure this is to you think about these devices. They have a top and bottom gate that we're applying gate voltages to. That makes them like a capacitor. So you can measure the capacitance by, for example, oscillating the voltage on a gate and on the bottom gate and measuring the charge oscillation on the top gate. And if you do this, that capacitance is very sensitive to the dielectric, which in this case includes your sample. Sample has some electronic compressibility that can be transduced with this capacitance. So we end up measuring the inverse electronic compressibility d mu dn. And that is a way that we can get contrast to the isospin order again. So this is showing this electronic compressibility, again, as a function of density and displacement field. Whereas we turn on the displacement field, you'll see these lines of bright contrast show up. These are, again, the half and quarter metals, and sort of all of the structure that comes with them. The way to read this data is wherever you see sort of a line, something that is a big change in signal, either a step-like signal or a sort of negative dip, then that is showing some change in the S-spin order or showing a Lifshitz transition. We can also apply magnetic fields and see quantum oscillations show up in the compressibility and sort of count the period of oscillations to tell us about the generacy. And again, basically confirm this half and quarter metal picture. And then to sort of bring it all together, this also gives us another way to sort of look at magnetic properties. Sort of as we apply out-of-plane and in-plane fields, which will affect the sort of energy balance. If I have sort of two zones, so this is zoomed in on sort of up here now, and this is the quarter metal regime, and we actually see that there's, for example, two areas of quarter metal. I can tell that these both have quantum oscillations consistent with being a quarter metal, but there's some divide between them. That line is indicating a change in the isospin order. And what we were able to work out, as you sort of tune the out-of-plane field and one of the phases expands into the other, and same with the in-plane field, you can work out the sort of energetics of the magnetic moments. In doing so, we see that the quarter metal is not sort of just the simple sort of Punnett square representation I was showing. You can have what you call invariant balanced quarter metal, where you see it's just the classic all the electrons are in a single valley. You can also get an intervalley coherent quarter metal. That is where you have a hybridization between the two valleys, which is something like being on the equator of the valley block sphere. And one thing to note is that since this is valley balanced, it actually doesn't have any signal in the nanosquid because you don't get any net magnetism. The two valleys are equal and opposite. But using this other technique, we can understand this too. And that's sort of has been the basic sort of progress that we've made in understanding, especially rhombohedral trilayer graphene. It's to use these two techniques together, sort of build up a classification of all the different sort of symmetry broken states that you can get in these systems. If you're interested in trilayer, I'll sort of just give an advertisement that we can sort of understand a lot about this intervalley coherent capacitance based on the influence of intrinsic spin orbit coupling in these systems. And then we can also do things like bring in a TMD, tungsten diselenide, to strongly enhance the spin orbit coupling and see things like spin canting in the half metal. But it all comes down to sort of using these two techniques together in order to work out a lot of the details of magnetism and what it shows. So we sort of have this experimental toolbox, and now the question is, can we apply this to this pentalayer rhombohedral graphene, in particular, looking at it without a moire in this sort of chiral superconductor regime. So my colleague Youngjun made this a pentalayer device, and I will just get a few notes about it in terms of the temperature scale. This is the sort of optical image of the pentalayer device. It's actually divided into two devices that one has filtered contacts, and we do this in a 300 millikelvin system. So we expect the electronic temperature to be about 300 millikelvin, and the other, which ends up being, for technical reasons, a bit easier to work with, is more like 500 millikelvin or above electronic temperature. And unfortunately, these contacts on this device are not great for looking at superconductivity. So I can't do what I long did and sort of take detailed transport measurements in addition to what I'm going to show. But sort of our goal was, again, to look for the magnetism, and this device is great for squid and this capacitance technique. So let's get to it. I'm going to start sort of with the compressibility, and then looking at this sort of broad regime of parameter space. So this is large displacement field. It's negative in this case. That's just how, because this device has both a HBN side and a WSE2 side, and is proximatizing away from the WSE2. But sort of basic physics we can work out, again, from the compressibility and quantum oscillations. So if we apply a out-of-plane field and count the quantum oscillations, we see that sort of this whole area I'm outlining is consistent with being a quarter metal. And we also see this half metal. So that's sort of our basic picture. There's some additional structure in here, sort of at this edge, but this is sort of all contained in showing a big quarter metal wing. So we start out with compressibility to sort of guide a nanosquid, and now it's time to actually bring in the nanosquid and ask the question, okay, well, does this look like what we expect from a hydro trilayer, where this quarter metal is magnetized? And so our first sort of surprise ended up being that when we bring our squid in and we measure this plane magnetism, this orbital magnetism we do see that it's strongly magnetizing the quarter metal regime, but that a large section of this quarter metal is negative, which is sort of an unusual thing to see in these nanosquid measurements. Sort of as a reminder, we're always applying some out-of-plane field in order to bias the nanosquid. And that means that we don't really expect to see sort of different signs in orbital magnetism. The orbital magnetism is locked out of the plane. External magnetic field is out of the plane. We would expect to have a favored valley that you're in. But actually, to start to think about what's been seen, there may be a way to understand how you can get sort of this negative magnetism. And that's from the basic fact that, I've sort of shown this basic equation of the orbital magnetic moment, but this sort of term isn't static. If I consider sort of where it comes from, Barry curvature and band details, but it can change quite a bit as a function of some parameter, for example, the charge density. So this is a schematic of magnetization versus charge density. And I'm just going to start out here at the origin. And as I move left to right, there's some onset. And then the two valleys have equal and opposite magnetization. Let's say that valley K prime is favored. Positive magnetization is favored, so value K prime is favored. We expect the system to just go into the sort of lowest energy state. And then, but as it continues, it can actually be metastable as it goes through 0. So you can sort of trade places with K and K prime, but the system will stay in K prime until whatever energy barrier is overcome or something causes a reset. That's sort of our basic picture for this sort of sign changing behavior. For some reason, as I enter kernel from this state, it ends up going into K prime and then staying for quite a while until you hit this reset. And to sort of, this is essentially a form of Valley hysteresis. And so the way we demonstrate that is by changing the history. We're again doing this sort of differential measurement. But now how I'm going to do the differential measurement is by doing essentially an A minus B measurement. So I'm going to measure magnetism here minus the magnetism here sort of as a function of time. And then do that as I scan the squid over the device. This in black is the spatial device outline. I see a large domain of negative magnetization. But in order to do this measurement, we had to initialize the system. And that meant we swept in our gates from charge neutrality to point A and then measured. We can sweep in our gates another direction. We can come in from this direction and then go to point A and do the same measurement and see that we sort of flip the magnetization. That's another sort of just way to see this is I've been showing you these phase diagrams. These are generally referenced from 0, but that means that every point has a sweep direction sort of inherent to it. But I can change the sweep direction and sort of sweep in from the side from the half metal direction. And in doing so, we sort of recover the basic phenomenology that we saw, where you have a single sign of this orbital magnetism, sort of maybe looks like the trilayer rhombohedral graphene. So this is sort of recovering the basic phenomenology. There's still a lot of open questions, namely how you end up in the K prime valley in the first place, and sort of why, when we look at it in the single valley, this whole quarter metal is not magnetized. But again, the details of this system can get quite complicated. One can think about spin orbit, nematicity, and even maybe having some valley imbalanced IVC state. So this is a fairly new result, and I just want to leave you with something that's sort of most relevant to what Long talked about of what was happening at the Chiral superconductor regime. So this is the sort of broad regime that the Chiral superconductor lives in. But if I look at, say, the MIT data, we try and compare to where do we actually expect these superconductors, and it's down here where you do see some substructure in the compressibility. And these sort of lines here are telling you that there's some change in the phase. If we take a line cut and apply an out-of-plane field, we can actually see that these there are sort of multiple phases here, and that they're expanding a little bit with out-of-plane field. So at the onset, this phase expands, into whatever it comes from with out-of-plane field. That indicates it has some magnetic moment. And then phase 1 expands a little bit into phase 2, and phase 2 expands a little bit into phase 3, and phase 3 expands a little bit into phase 4. There's sort of a cascade of magnetized states that we're seeing here. They're right in this regime. And we, so now again, we bring in our nanosquid, sort of look at what we saw in compressibility. And so this is doing it slightly differently. I have gone to the device with the filtered contact, so this should actually be at 300 millikelvin. And I'm sort of saturating the color scales. The brightest feature is this magnetism up here. But again, if you look in this regime, you actually do see some distinct orbitally magnetized region that's right on top of, or I should say right in the middle of this area. Again, I can't see superconductivity directly in this device, so I can't line it up exactly with the superconducting phase boundary. But that's very sort of suggestive. Also suggestive is the fact that this is not sort of spatially uniform. So this phase diagram was measured at one part of the sample, and then I translated a nanosquid over here, and you actually see that this structure changes. In particular, there's sort of little domains of positive and negative magnetization. There does appear to be some domain structure in this regime, which again, you could probably expect if you look at Long's data, showed often sort of right in here around the superconductor, you see a lot of switching and hysteresis and things like that. So we are sort of continuing to work on this. The nanosquid is a scan probe technique, so it can resolve things spatially, but being able to, but having to deal with spatial degree freedom does complicate our lives a bit. So work is sort of ongoing, and that's sort of the basic picture of what we're able to understand now about this fundamental regime dynamics, and we're starting to sort of go out and talk to people and try and understand maybe what's going on in these systems. So again, this is sort of a quarter metal regime, but it's not as simple as the one in Trilayer. There's some more complex dynamics on top, that we are trying to understand. With that, I should thank everyone who was involved in this project, in particular of these lovely and talented people here, and I should thank you for your attention.
5 minutes for questions.
Well, yeah. So on your phase diagram, the low density boundary of quarter metal, what is the ground state to the lower density side?
You mean sort of in here, like sort of right at the edge there? We can't really see much, from these techniques, we can't see much magnetism or much contrast. I mean, you do expect from transport that there's that sort of Wiener crystal phase in there, and we can't quite see the boundary for it here.
So basically, I should not take too seriously the sharp boundary that you draw between quarter metal and something else.
Yeah, except that this is, we see this expanding. If you look at it, maybe I can show you this data a little bit later, but it's sort of a very subtle boundary to see it. So it's a little bit hard to say. Generally, with these compressibility, we really like to look for things that are like a negative dip in the compressibility to really say that that's a strong phase boundary that I can resolve and understand the magnetic dynamics of. So yeah, it's hard to tell just from compressibility, for example.
In prior systems like twisted monobilayer graphene, where you see this switching of the magnetization, I think that was understood as basically a competition between the magnetization coming from the filled band and then from the topological edge mode in the gap.
Yeah.
In this case, where you don't have a topological gap, you're just partially filling a band. Do you have some kind of cartoonish picture of how the magnetization can switch sign as a function of doping?
So when we advanced the to like shows the single particle band structure, it's hard to see where that would come from. I showed a very schematic picture of it, sort of varying, but that's not sort of based on any calculation. And so I guess the answer is that the absent some more than single particle picture, it's not exactly clear where that sign changing comes from yet.
I have probably a very naive question. So naively, there are two possibilities for quarter metal. Either you have ferromagnetism within a valley and simultaneously valley polarization. Basically, you break valley symmetry and you break spin symmetry. This one possibility, and I guess Ju was mostly referring to this possibility. Another one is a combination of IVC and spin IVC. But in both cases, you need both because otherwise you will not get quarter metal. You need to break two symmetries.
Yeah.
You get out of 4, you get only 1 pocket. So when you were referring to it's not conventional magnetism, were you referring to the second possibility that it's combination of IVC and spin IVC or something else?
Yeah, so there is a version of the IVC that we actually have seen in sort of as a subtle effect in Trilayer where you get, it's called IVC-Z, where you the IVC is sort of hybridizing two values, and we generally think about it as you can get that there's sort of an equal number of electrons that are putting together. You can also think about having more electrons in one value than the other. It's called the IVCZ. So maybe you think about you have a state that is still somewhat magnetic because it's sort of has sort of more, it's still this IVC quarter metal, but it has more electrons, in one valley, and therefore some excess magnetic moment.
We expect in this case that you also have a conventional ferromagnetism in the valley. You have more fermions in one valley, right? You are in quarter metal state. So don't you expect that there will be also then ferromagnetism within a valley?
In the
Similar
case,
virtual breaking.
yeah, I mean, in the case of the you would expect to see some paramagnetism. It might be fairly weak, but again, we're sort of, it's not clear exactly, like we don't even have like a Hartree-Fock-ish calculation to guide us on exactly what is happening sort of right there. So.
And do you have any data in half metals?
In the half metal state of this, yes, we do. We sort of, maybe I'll just very quickly flash.
The question is, do you see magnetism there?
Yes. So this is sort of, there's a lot going on here, but just think about this is a way that I can sort of visualize all of the magnetic moments with the nanosquid. And you see these sort of wings here. These are the half metal states, and there's some half metal magnetism down there. Maybe the better comparison is to the sort of Rhombohedral trilayer here, where again we always see this sort of hierarchy of having the quarter metal and then a half metal wing surrounding it. It gets a lot more complicated sort of in this pentalayer, and so the regimes we were talking about were up here, but you do see, again, a basic quarter metal wing, and then quite a bit of sign switching behavior, something that's more than a Bohr magneton per electron, so that would be the orbital magnetism happening sort of at lower displacement field. So there's sort of a lot to work on here, and we're just trying to understand it.
We have time for a couple more questions. So Dan and then Alex.
In the far upper right of your title slide, are you seeing a 3 flavor metal there?
Oh, yeah, we do see the quarter metal. The three quarter metal.
3 flavors.
Yeah.
3 quarter metal.
3 quarter metal, yes. See, what's the best to show this?
On a small border, probably between the half and the full.
Yeah. Yes. So this is essentially a way of using the nitroselenide and the turning off the supermagnetism and the WS2 proximatized sort of displacement field configuration. So this sort of sliver here is a 3 quarter metal. So
in the pentalayer.
In the pentalayer. I'm not sure that we can make that assignment right now. We do see a 3 quarter metal in trilayer.
Yeah, so for Pentalayer, you have the negative magnetization region. It seems to switch over at, a very striking feature in the compressibility.
Yeah.
Do you know why that is?
That striking feature in the compressibility looks to us like a Lifshitz transition. So there is some sudden change to the Fermi surface coming, and that I guess causes the magnetization to reset somehow. Changes the sort of energy barrier between states.
So even though you're still in the half metal.
Yeah, quarter metal regime.
Yes.
All right. Well, ask more questions over coffee. Thank Trevor again. So get started. So whether to have Devakul tell us about theory perspectives on quantum graphene.
All right, thanks. Thanks, Hart, for organizing and for introducing me. So today I'm giving a theory talk on basically the stuff that you have heard about this morning already. So let me first start out with this plot, which hasn't been shown yet this talk, this workshop. This is one of the most beautiful plots in physics, I think, and doesn't need much explanation. But once you have, if you've been working on it for a while, it's kind of easy to forget that all of this phenomena, quantized RxX, RxY at all these fractions, emergent anyons and everything, all comes down, all emerges from a really simple Hamiltonian that really only has three key ingredients. So you have 2D electrons, there's some dispersion, just p squared. You add a magnetic field by minimal substitution, and then you add the simplest possible interactions you can think of, Coulomb, and that gives you all of this rich phenomena that's occupied us for decades. So today's talk is not about a magnetic field, but I'm going to be talking about Berry curvature. So probably most people here already know what it is, but let me just fairly briefly introduce it in the way that that I'm going to be talking about it. So Berry curvature is a generic property of multiband systems, unless there's some reason it's symmetry forbidden. Simplest thing you can think of is just a two-band model, Hamiltonian some 2x2 matrix. And if you look at the states at a particular momentum, it's a two-component vector. So this Hamiltonian is really just a map from momentum kx and ky to some point on the Bloch sphere labeled by this two-component vector. And if you now imagine, right, tracing your momentum around a small loop, the wave function will also trace out a small loop in the Bloch sphere. And this is the classic example that Berry's phase is defined. So this Berry phase that you pick up from going around the circle in the Bloch sphere, you can really interpret that as nothing but some kind of Aharonov-Bohm type phase in momentum space. You go around this loop, your wave function picks up a phase that's equal to the integral of the Berry curvature enclosed in that loop. So in that sense, Berry curvature, this omega of k, is nothing but a magnetic field in momentum space. And we can make this more precise. So what I'm going to be talking about today is not the quantum Hall effect. I'm going to get rid of the magnetic field and replace it by Berry curvature. And as a result, we won't get the quantum Hall effect. We'll get something else. And this whole enterprise was really motivated by very amazing, groundbreaking experiments that we've already heard a lot about in rhombohedral n-layer graphene. So I personally only got into the system a year or two ago when Long had this beautiful fractional quantum anomalous Hall effect in HBN aligned rhombohedral pentalayer graphene that he just told us about. More recently, there's this very interesting chiral superconductor that he also just told us about. So I'm very happy that I don't have to talk about these. So one thing I should point out that the system has generated 4 journal club commentaries so far, which is a lot. So what I'm going to try to address is what's going on in this system. And in fact, I'm trying to make a claim that most of the surprises in the system can be qualitatively understood with just a very, very simple model, physical model that has only these 3 ingredients. I just want 2D electrons, Berry curvature, and interactions. Okay. So this is rhombohedral graphene. You've heard a lot about it this morning. This is a picture from one of Long's papers. If you zoom in on the K-value of this system, there you get these bands. They have some dispersion, and they have a lot of Berry curvature. That's the most important thing about them. Because of time reversal symmetry at the other valley, K prime, you always have a time reverse partner. But if you're at low densities, then by Stoner, there's some Stoner criterion, then you can get into a regime where all of your doped electrons or holes are really only in one valley. Then it makes sense to ignore the other valley. And in fact, for most of this talk, I'm going to basically do that. I'm going to assume that there is some kind of interaction-induced valley polarization. I'm also going to assume spin polarization, but spin sort of plays a minor role in most of this. The picture that this should remind you of is if you look at this band, it kind of looks like just a 2D standard 2D electron gas dispersion. You can do some kind of effective mass dispersion about the band edge. But the main difference is that there's a lot of Berry curvature. It's very red. And in fact, if you go to n layers of rhombohedral graphene, that roughly the total amount of Berry curvature that you get scales with n. It goes as n pi. Okay. So as a theorist, I'm going to consider an abstraction of this model because I want to sort of identify the essential ingredients that gives you the physics that I'm after. So I want a model with only the essential ingredients and nothing more. If I want to describe things quantitatively, I'll have to worry about all the details. But if I just want to understand the physics going on, I want to stick with only the essential ingredients. And I claim that these are the essential ingredients. Some dispersion, you just have a band with some dispersion. As long as the band edge is sort of flat enough, I don't really care what the dispersion is. So I'm just going to take it to be k squared. There's some Berry curvature distribution at the band edge. In reality, there's some, it's non-uniform. There's all sorts of structure in it. But I'm going to try to just say, okay, can we just assume that there is some Berry curvature? And the simplest thing that I can do is just assume that it's constant, or just take it to be constant, and then add on top of this Coulomb interactions. So this is sort of the distillation of the three ingredients in its most simple form. And I'm going to try to see if this can capture all the physics. So the first thing when I was looking for a model that had all of these ingredients. So the first question I had was, has this been studied before? Surprisingly not. This limit of uniform Berry curvature is frequently studied only in semi-classics. But so far, I was surprised I couldn't find a fully quantum model that had all of these properties. So the first thing I had to do was write down a concrete model with all of these ingredients. And it turns out that that's possible. So in this paper, we wrote down some family of solvable Hamiltonians that gives you this kind of tunable Berry curvature. There's there's sort of a multi-band model. So the first one is this 2s plus 1 band model where s is like a spin, and you can just change that. It's half integer. And what this model, there's some parameters that enter into some form of the Hamiltonian. And what this gives you is a perfectly parabolic band and a Lorentzian squared Berry curvature distribution that we can tune. That by tuning parameters, I can tune the distribution and the dispersion sort of independently. Yes.
What is lambda?
It's a parameter in the Hamiltonian.
One is.
It's hidden inside of this function. And this gives you a bunch of bands, but if we isolate one of them, it has this Lorentzian squared Berry curvature, and we can sit in there. We can also take sort of the s equals to infinity limit while keeping the Berry curvature density uniform. And in that limit, there's a sort of another type of Hamiltonian that you can write down that sort of can be connected to this one, but in terms of some unbounded bosonic degrees of freedom, but the details are not that important. What this does is it gives you a bunch of bands, infinitely many, separated by a band gap j. Each of them have exactly quadratic dispersion and totally uniform Berry curvature. The details of this model I'm not going to use very much in this talk, but I just want to tell you that they exist, and if you're a theorist and you're interested in studying them, I encourage you to take a look at the paper. Okay, so I'm trying to talk about interactions. So let me before I start, let me just be precise and just define everything properly. So I'm going to be let me take the CK operator to create an electron in the block state, e to the IKR times some U of K. K here is unbounded. There's no Brillouin zone. I'm doing some effective continuum expansion. This U of K is taken to be the lowest band in the active band in the multiband models that I've shown you before. And if you project to this band, you get a many-body Hamiltonian that looks like this. The first term is just the kinetic term. There's a k-squared dispersion. The interaction term is just a Coulomb interaction. V of Q here is the Fourier transform of the Coulomb interaction. The only difference between the standard 2D electron gas and this model is the appearance of these form factors. And these form factors are the block overlap. So they encode all of the Berry curvature and all these other properties. And if we take this, and in this model, the microscopic model I give you, you can sort of derive this form. It turns out that this is the sort of minimal legal form factors that you're allowed to have. And if you consider this model in isolation, this is actually equivalent to working in first quantization, but doing the minimal substitution. When you apply a magnetic field, you send P to P minus A. When you take this form factor, you're sending A to A minus A. You're sending R to R minus A of K. So it's exactly analogous to applying a magnetic field, but in momentum space, just K and R reversed. Okay, so with the groundwork set, I want to consider this as an abstraction of the real system. It's very nice theoretically because there are only a few dimensionless parameters. We can add and analyze the effect of Berry curvature completely systematically. You can turn it on without changing any details of the band dispersion. And also, it's surprisingly analytically tractable. There's an asterisk here because it's strongly in tracked physics. Nothing is truly analytically tractable, but it's much more analytically tractable than, say, the fully microscopic model. The big question is, can it capture the qualitative physics of the real system? And I'm going to show you several cases in which I argue that it can. Okay, so I'm going to talk about there's two parts of this talk. The first part, I'm going to talk about what happens when you consider electron crystallization in the presence of Berry curvature. And then the second part, I'll talk about superconductivity. Okay. So this was the experiment that Long just told us about. There's 5 layers of graphene, and it's aligned with HBN on one side. This is the transport data. I'm very happy that I don't have to talk about this. Down here, there's a Wigner crystal. Up here, there are all these integer and fractional quantum anomalous Hall states. And my claim is going to be that these states are also related to crystallization. Those are the focus of my talk. So to get a quantized anomalous Hall effect, it's characterized by a Chern number, which is the sum over filled bands of the Berry curvature of that band. So the first thing to realize is that to get a quantized anomalous Hall effect, you need a band. And to get a band from this sort of by band I mean sort of a bounded band. To get a band from this continuum starting point, you need to break continuous translation somehow. This can be done either explicitly or spontaneously. And once you open it up, you need to have a Chern number that's not 0 to give you a quantum anomalous Hall effect. So if you go back to the trivial 2D electron gas, just p-squared dispersion, which you can get from this model by setting Berry curvature to 0, then we can break continuous translation symmetry either explicitly by adding a periodic potential, in which case, if you're at filling of one, let me ignore spin and be at 1 electron per unit cell, then adding a periodic potential just puts you into some kind of trivial band insulator state. You can also break translation symmetry spontaneously by adding very strong interactions in the strongly interacting limit or the mass goes to infinity limit. The status can be well described sort of classically just as an array of localized charges, and this is a Wigner crystal. So these are 2 ways of breaking translation symmetry in the 2D electron gas. We can now let me now take this non-trivial band, this with uniform Berry curvature, and just do some numerical experiments to see what comes out. So let me do two things. Let me add a periodic potential to break translation symmetry explicitly. And let me also add interactions to break it spontaneously. And let me break this translation symmetry with the appropriate Brillouin zone so that there is one, first of all, that there's one electron per unit cell, and that the total amount of Berry curvature enclosed in this Brillouin zone is exactly 2 pi. So this is sort of the commensurate value, if you will. And this is just numerics. So if I turn on the potential strength and I look at the first mini band, so the band gets split up into lots of mini bands, I look at the first one and I can plot its bandwidth and the gap between the first and the second mini band. And they do what you'd expect. The gap gets bigger, the mini band gets flatter. Somewhat surprisingly, this gives you a Chern number -1. The minus here is if you just integrate over 2 pi, that should give you a 1. There's a -1 here. I'll get back to that. We can also do the same thing by adding interactions and just doing mean field Hartree-Fock, self-consistent Hartree-Fock theory. Yeah.
And what happens when interaction strength is 0?
It's just a metal. Yeah.
So what? You said C is equal to 1. What it means?
So below the critical value, nothing happens. Above a critical value, then the gap opens up. And then it becomes Chern 1. So when I first saw this Chern -1, I was sure I was convinced my student had a sign mistake in his code. So I asked him, plot the Berry curvature of this mini band. What does it look like? And this is what he showed me. If you look at the zone center where the potential is not doing much, you get a positive Berry curvature from the parent band. But when you go to the zone boundary, which is where all these mini gaps open up, you get a really, really negative Berry curvature. And it sort of is it just enough to completely cancel out all the positive and give you a total Chern number -1. Very surprising. You can do the same for this state with Chern +1, and it's just all red. So this state is sort of somehow more intuitive than that. And since this breaks translation symmetry spontaneously, this state should be regarded as some kind of topological Wigner crystal, which has been called this anomalous Hall crystal, which maybe we'll hear more about from Dan later today. So let me move on. So I can go from, instead of just 2 pi, I can go to 2 pi n Berry flux and do the same thing. What I find is that here I get a Chern -n insulator with a periodic potential. Add strong interactions, I always get a Chern +n crystal. It turns out this is an exact statement. We can prove this. And this Chern n state, we can understand this in a certain limit. So the limit of dominant exchange, then this statement sort of also becomes exact. And the precise way, the precise statement of this you can find in our paper. We proved this using some series of mappings between this band and the trivial 2D electron gas that I don't have time to get into. But let me now sort of come back to the microscopic model for rhombohedral pentalayer graphene and try to convince you that these results are more general than this limit of uniform Berry curvature. This is the band structure we take from a microscopic model with all the orbitals and everything in the real model. There's Berry curvature. It's not uniform. It's some ring-like structure. And we can do two things. We can add Coulomb interactions, allow it to break translation symmetry with this fixed unit cell, and see what happens. This is plotting some quantum geometric properties, but the important thing here is just that it's a Chern 1 band. So that's sort of in agreement with this Berry curvature is positive, and you get a Chern +1 band. That's in agreement with our analysis. You add a periodic potential to this system, and this is a phase diagram as a function of the displacement field and the potential strength. You see that pretty much the dominant phase that you get is a Chern -1 band. And that again agrees with the very simple model.
So if
yes.
Berry curvature is fixed,
yes,
and you want to have C exactly 1,
yes,
that seems to dictate very definite density.
Yes. So one exercise you can do is sort of look at the total area in momentum space in sort of this low energy region of the band. Take the total Berry curvature and sort of spread it out uniformly within that area and ask how much Berry curvature is there roughly per per Brillouin zone. And I forget the numbers, but that's roughly around 2 pi. So we ran that, we did that exercise. So the density is appropriate for a Chern +1 state.
Question.
Yeah.
So if you just have a single band, but it's not k squared, but minus k squared, nothing will change? Or?
Minus k squared, and then you oppose it to it. Yeah, that's the same. Yeah, that's just particle Hall transformation.
Ask one question.
Yeah.
You don't need it to be like neutral Berry curvature. There's no constraint. Like from the physical system, there's some sort of neutrality condition, whereas you don't seem to worry about that. Or
So we're just working this one band limit, right? There's another band that sort of cancels that out.
okay, you have like a somewhere else canceling it.
Yeah. Okay, so let me now go to some more experiments. There was actually a recent experiment. So experimentally, right, there's moire only on one side. You can add a displacement field, positive or negative, and if it's positive, then you sort of push your electrons onto the side away from the moire. I'm going to call that the weak moire. If it's negative, then you have to push electrons towards the moire. I'm going to call that the strong moire. In the first experiment from Long, they were in this weak moire regime. They didn't see anything at strong moire, and they see this Chern +1 insulator at nu = 1. So I'm going to try to interpret this as a weakly pinned Chern 1 anomalous Hall crystal. I'll come back to this in a second. But in a more recent experiment also from Long and Ray Ashuri, they went to the strong moire side, and while there's nothing at zero magnetic field, when you apply a weak magnetic field like half a Tesla, there's this very prominent Chern -1, this insulating state that appears, and it slopes with to the left, which tells you that it's Chern -1. So this, I'm going to argue, it corresponds to a moire-dominated Chern -1 insulator. So this interpretation hinges on some assumption of the orbital magnetization, namely that it doesn't change sign as you go as you turn up the moire strength. But I mean, we have some calculations that seem to suggest this is the case, which I don't fully trust. But if we assume this, then this picture, this interpretation makes sense. And there was also a more recent experiment from China where they see also flipping Chern signs for positive and negative displacement fields. Yeah. Oh, 5 minutes. Oh my God. Okay. Let me splash one slide to say that we can also do something fancy for a fractional case, and we find that fractions are very close to competing with integers in this model of uniform Berry curvature. So it's very reasonable that when you turn on a weak periodic potential, it will cause the commensurate states to dip slightly below, and this could be an explanation for the fractional states that are seen in experiment. Of course, this approach that we've done here, we've developed only works for this particular. We've only applied it for this particular model where we can do very a surprising amount of analytical progress. Okay, so with my last 5 minutes, let me talk about superconductivity. So this is obviously very exciting. Let me skip all the background that Long already talked about. So the reason that this is very interesting is because this is a candidate for a topological superconductor. And also, as with most of these 2D superconductors, a big question is, what is the pairing mechanism? Is it phonons, or is it purely electronic, or others? The reason I'm even mentioning this is because I'm going to try to say something about it. So as Long's already mentioned, in a sort of valley unpolarized superconductor, you can have pairing between the two valleys. When your normal state is spin and valley polarized, you have no option but to pair electrons within one valley. And as a result, in the system, time reversal symmetry is broken at the outset, so you're always stuck in this band. And as a result, if you have pairing like this, you can sort of argue that the Berry curvature that the Cooper pair sees, it sort of cancels out between the two valleys. But when they're both in the same valley, they sort of add. So Berry curvature becomes very important. So the first, let me just go see what this model predicts. So we can take our model, uniform Berry curvature, and let me just add an attractive interaction with some interaction range sigma. This is the phase diagram that we get. So this is Berry curvature, and that is the interaction range. what you find is that basically so you can open up a gap, and you generically will get a gap with a non-trivial winding of the order pair. So this is like px plus ipy, for instance. And the winding number C is, you can calculate that based on the Chern number of the BDG Hamiltonian. It's always positive, and it goes from 1 to 3 to 5 to 7. It's always odd, also because we have only one spin flavor, so it needs to have odd winding. But the way that we can interpret this phase diagram is as a kind of momentum space little Parks effect. The Berry curvature is just a magnetic field in momentum space, and you can think of this superconducting order parameter along the Fermi surface as a momentum space superconducting ring. And so as you add Berry curvature, that's like applying a magnetic field to your superconducting ring. The phase winding of the order parameter sort of locks on to some nearest integer, and that explains this phase diagram. Yes.
Can this be interpreted in simple ways, transition from P wave to F wave and then to other states?
Yes. We can consider another case, which is repulsion. So let me now consider only a short-range bare repulsion. Now you can still get superconductivity, but it has to come from some kind of overscreening effect. So the Kohn-Luttinger effect. What we can do is we can take this bare interaction, and we do a perturbative analysis. So this analysis is perturbatively exact in the limit of weak interactions. We take sort of a weak, again, a Gaussian interaction. And we can look at the phase diagram, and again, and now it looks completely different. The phase boundaries are no longer vertical, but also, perhaps more surprisingly, is that the Chern numbers are all negative. So this is something like an anti-little Parks effect. You apply a positive Berry curvature, and somehow the order parameter winds negatively. You always get a Chern negative winding. So it's like P minus IP order parameter. It turns out this sign of C, I'll come back to the interpretation of why this is the case on the next slide, but let me just argue that now the sign of C is a robust prediction. We can take this microscopic model. Now let me make the assumption that it has full rotation symmetry, because that simplifies a lot of the numerics and allows angular momentum to be well defined. The Berry curvature looks like a ring. We can do the phase diagram for two interactions. We can do some short range attractive interaction that's supposed to approximate photon interaction mediated attraction. We can also take some Coulomb interactions and treat overscreening via RPA. And all over here you see that there's positive winding of the order parameter, and all here you see negative. And we can do the same analysis for n equals 3, 4, 5, 6, 7 layers, and the sign is all consistent among all of these. So while the numbers, I wouldn't trust the numbers of these or the phase diagrams, the sign of C seems to be a robust prediction. Let me comment on the physical origin of this. So one way we can understand what's happening is that because the band itself breaks time symmetry, the Cooper pair wave function in terms of the relative electron coordinates is different for positive or negative winding. If you try to create a state out of electrons on the Fermi surface with positive winding, you get say C equals 1 or 3 winding, you get a relative wave function that has a peak at the origin. It's non-zero at the origin here as well, even though there's a dip. Whereas if you try to create a state with negative winding, you create a wave function with a very dramatic difference. There's a very dramatic zero at the origin. So if you have an effectively short-range attractive interaction, it's very natural for them to favor positive winding, as opposed to when you have repulsion, this overscreen Coulomb interaction you can think of as being repulsive at short range but attractive at longer range. Then it's very easy to understand why this kind of wave function for the relative coordinates is very favorable for that kind of overscreen Coulomb interaction. Now, in fact, we can make a concrete prediction out of this. If you go to above TC, you get a normal state. It has some anomalous Hall effect that's proportional to the Berry curvature with a minus sign because the electron has negative charge. If you go into below TC and you look at the superconductor, now the superconductor carries a Chern number. So there will actually be a quantized thermal Hall effect. And basically, if you run a thermal gradient, you should get a thermal thermal buildup on one side or the other, and that sign will tell you about the sign of Chern number. I'll be done in 1 minute. So the relative size of these two effects can provide some empirical evidence for distinguishing one of these two mechanisms. And possibly we're working on trying to see if there are more accessible measurements that can explain this. So let me conclude. So I've been looking at these basically just these three ingredients. It's an interesting setting for potentially new physics, and it's also relevant to real systems. Now we have a microscopic model that can really be systematically studied. You can sort of separate all of these things into separately and tune them all individually to find out what is the effect of each of this. And decades of study has gone to the quantum Hall effect, where you have a Berry curvature. This is just changing the Berry curvature from real space to momentum space. Could this setting be as rich as the quantum Hall effect? And what's next? I have some speculations, but that's it. Let me thank my students. We have my student Tishan Tan, who did most of the work, and my postdoc Julian Mayman, and collaborator Tobias Hellberg at Stanford. Thank you.
Good questions.
Yes.
If I may, let me bring you to the beginning of your talk. When you talk about the model.
Yes.
Question is this. You said from the beginning that in order to get Berry curvature, you need basically at least 2x2 Hamiltonian.
Yes.
This 2x2 in case of, say, bilayer graphene or three-layer graphene with 3x3 is provided by terms which create trigonal warping. And the same terms also break rotational symmetry in Hamiltonian.
Yes.
So then obvious question, you keep K square.
Yes.
And you keep at the same time Berry curvature. Is it allowed? I mean, do you need to keep also the terms which
you can have Berry curvature while maintaining full rotation symmetry. You don't need to break rotation symmetry in order to get Berry curvature.
Okay, but at least it's the examples that you later considered.
Yeah, so
multi-layer.
We did consider, like, for example, in this calculation, we did have we used the full model. Like this band has all of the that features in there.
The results are the same, so
Yes.
it doesn't matter.
Yeah. Yes.
I believe with your Hamiltonian interaction, Hamiltonian that includes the Berry curvature, you should get superconducting pairing as a first order effect in the interaction. No need for convolution. It's not a question, it's a comment.
How does that work?
We'll talk later.
Okay.
But have you tried to get it from your electron-electron interaction?
Well, with pure repulsive interactions, and if you just do like BCF
it's not
field
repulsive,
theory.
it was long that you include Berry curvature there.
With just no, with just like linearized gap equation, all the eigenvalues are non-superconducting.
Okay.
All right, we're out of time, so let's thank Trevor again. Next speaker is Yankowitz, Washington.
Oh.
Biker? Get back in the room. Okay, cool.
All right, thanks for the introduction and for the invitation to speak at this really nice workshop. So I'm going to be talking about superconductivity and Chern states in Rhombohedral graphene. If you're worried that this sounds too much like what you've already heard a lot this morning and that you'll be bored, don't worry, it's actually in a pretty different regime of parameter space than what we've heard before. So if you end up being bored, that's for other reasons. Okay, so the kind of evolution of 2D materials over the past 8 years or so has been to design and really create flat bands that have Berry curvature so that we can try to probe the interplay of strong correlations and topology. And the original ideas were in twisting graphene, and eventually that twisting program extended to many other materials where we can generate flat or reasonably flat bands with non-trivial Berry curvature coming from the fact that these bands are made up of states from values at the K and K prime points. And as we've heard a lot this morning, more recently, we can see the same physics in crystalline systems. So for example, in the Rhombohedral or chiral stacking of multi-layer graphene, you get this progressive band flattening as you add more and more things, at least to leading order. And then when you apply an electric displacement field, you can open a gap and further flatten the bands at the extrema and create very large density states. So we heard, the number of ways in which you can get pretty exciting novel quantum phases of matter out of these flat bands. For example, the signatures of chiral superconductivity in 4 and 5 layers, more recently maybe 6 layer graphene. And when you add a moire pattern, that these phases seem to switch into integer and fractional quantum anomalous Hall states. So the kind of unifying theme of all of those phases, and if we really zoom out and think about rhombohedral graphene more generally, is that these phases happen when we apply a fairly substantial displacement field to open a gap between the valence and conduction bands and create this band flattening at the edge of either of these bands. And so indeed, if we look at Brunel bilayer, which is equivalent to rhombohedral in the bilayer, or rhombohedral trilayer, tetralayer, pentalayer, now 6 layer, what all of these have in common is that you see superconductivity form at some modest to large displacement field. And this corresponds to having a gap between the valence and conduction bands and then putting the Fermi level very near the top of the valence band or very near the bottom of the conduction band, so lightly to with electrons or holes. So, a feature of rhombohedral graphene is that when you open a gap, or even if you don't actually, the states at the K point or the K prime points, the corners of the monolayer Brillouin zone, are exact layer and sublattice polarized eigenstates of the system. And the consequence is basically that when you open a gap at the bottom or top of these bands, all of the electronic weight or the density of states basically segregates almost entirely with exponential localization to the top or the bottom layer of the structure. And so this can be understood kind of in analogy to the SSH model of polyacetylene, where you end up with these topological edge modes. This is a calculation of the density of states for a 7-layer sample with some modest interlayer potential. And what you see is, as I mentioned, this kind of exponential localization of the wave function onto either the top or bottom surface, dictated by which way you're pointing the displacement field. And so we don't really think about the spatial structure of the wave function along the stacked axis. We kind of think that we're just projecting it to one or a small number of layers. But the story changes quite substantially when we look at intrinsic rhombohedral graphene without applying an interlayer potential. So in this case, in a very simple model, you would have some band touching, and once you include higher order popping terms, you get trigonal warping that distorts the bands. And because these bands end up being relatively flat, they have a very large effective mass and a high density of states. You actually end up with a substantial regime of density in which you have the valence and conduction bands overlapping. So if you were to put the chemical potential there at neutrality, for instance, or somewhere nearby, you would end up with a Zhen belt. And this is a calculated phase diagram from Falco's group from a few years ago, showing what happens as a function of the layer number of rhombohedral graphene. It's a function of either electron or hole type doping with 0 interlayer potential. Okay, so out here, when you add a lot of electrons or holes, that's our kind of familiar regime where you have a single simply connected Fermi surface. But in here, there's actually a pretty substantial range of doping, a few times 10 to the 12, in which you have the coexistence of Fermi surfaces from the valence and the conduction band. So you can think that you have this kind of semi-metallic coexistence of electrons and holes in the system. And this regime has received, I would say, comparatively less attention so far experimentally compared to what happens when you apply a large displacement field. And so this will be the primary focus of what I'll talk about too. All right, so I'm going to show you data from a number of samples of rhombohedral graphene of slightly different thicknesses and with and without alignment to boron nitride. It turns out that for the most part, the details of layer number and even more for much of what I'm going to tell you don't matter so much. This work is done in collaboration with Josh Folt's lab at the University of British Columbia. So this has been a really nice Pacific Northwest collaboration for us. My students, Manish Kumar, Derek Willett, Anna Okinkova, will make devices. They'll drive up to Vancouver one morning, load the dope fridge, start it cooling, drive back, and then do all the measurements remotely with the assistance of Josh and his team. And that's been working out really well. So I'm going to start with a sample of rhombohedral octalayer, 8-layer graphene. And what I'm showing is a measurement at zero magnetic field of the longitudinal resistance. So blue is small resistance, red is insulating, as a function of the units that we normally plot things on, charge doping and displacement field. What we really measure is as a function of top and bottom gate voltage, and then we use a standard linear conversion to switch to our favorite axes. Now, I'm going to start at neutrality and tell you what happens at very large displacement field, which is something that we've heard a number of times by now. We open a gap, and so that corresponds to an insulating phase. When we're at a more modest displacement field, the system is in a regime in which non-interacting band structure would predict that the valence and conduction bands are overlapped. So you should get a semi-metal. And indeed, for most of this red bar, the resistance is pretty low at neutrality, consistent with that semi-metal expectation. You'll notice right around zero displacement field is actually another insulating state. This shows up in many different layer numbers of rhombohedral graphene and has been pretty well understood in thinner limits to be the result of an interaction-induced gap, which is generally thought to have some sort of layer antiferromagnetic ordering. But for the purpose of this talk, it's mostly not relevant. There's one more feature I'm going to point out just to tell you to ignore it. Due to details of how we have to take this map and tune silicon gate voltages to make the contacts work well, we ended up with these two diagonal lines that you can see if you look hard. Those are just measurement artifacts, so you should not look at them anymore. All right, so let me try to orient myself and all of us into what's happening when we move away from charge neutrality. And specifically, I'm going to focus on primarily whole dome side of the sample, so n less than 0. So what we can see here is that when the gap opens at the neutrality point, there are these two weak resistive features that emanate away from it. This one's more obvious. This one is actually almost parallel with the boundary from color to white. That boundary corresponds to tuning a single gate voltage. So this is a feature that's almost parallel to a single gate voltage, and that will become important later. If I take a Landau fan by parking one gate voltage and sweeping the other perpendicular to that boundary, what you see is that on the very extremal side of this map, the quantum oscillations look like a kind of normal Landau fan diagram. You just see them dispersing all to some point all the way up here. And if you take an FFT of this and plot it in the right normalized units, it seems to imply that this is an unpolarized fourfold degenerate metal. Now, once you cross this resistive hump, the quantum oscillations become much more complicated. These originally dispersive ones actually flatten out, and then you get some other sequence that exists on top of that. And so what I'll argue is basically that this is a signature that you're crossing over from the regime on this side where you have simple quantum oscillations, where the Fermi level is cutting through just a single band, just the valence band. And on this side, you actually have the coexistence of both electron and hole type pockets from the valence and conduction band. And now these states, their quantum oscillations kind of lie on top of each other and form this complicated sequence. And then in fact, this entire boundary that's emerging from the gap at the charge neutrality point corresponds to the chemical potential crossing, or rather using displacement field to move the conducting band across the Fermi level while the system is whole doped metal. So we can extend that logic and basically draw this triangle where everything inside this triangle corresponds to primarily whole doped metal, where we have a coexistence of Fermi pockets from both bands in the system. We can see this in calculation as well, and I think this provides some useful insight. So this is work that's still in progress, but is being done in collaboration with Cyprian Lewandowski's group in his postdoc FOM at FSU in the Magnet Lab. So what they've done basically is to take, in this case, 8-layer graphene, although really the layer number doesn't matter so much, and add a very small or even 0 interlayer potential and some doping of 1 × 10⁻12 holes to the system. So what you can see is a kind of now usual band structure that we've seen a number of times, this quasi-parabolic conduction band and this Mexican hat-like valence band. But what we're looking at on top of this is the layer polarization of these states. So in this plot, I'm showing the average layer polarization. So red at the bottom of the conduction band means that the states are primarily polarized to the top layer of the 8 layers of graphene. Blue at the bottom of the of this little hump in the valence band tells us that the valence band states are primarily on layer 1, the bottom layer. And this goes back to the story about how the states at the K point are exact layer and sublattice eigenstates of the Hamiltonian. As you move away in momentum space, these states become more layer delocalized. And indeed, that's what we see as you move out to the edges of this band, the average layer polarization becomes somewhere in the middle of the stack. And so that's why you have another sequence of states here that are shown in green. It's a little bit misleading to plot the average layer polarization. So instead, I can just make a plot of the density of states for both the valence and conduction band as a function of the layer number. And what you see is that the conduction band is exponentially localized on, say, the top surface. The valence band is mostly localized on the bottom surface, but this has a weight of the wave function that's actually extended all the way across the 8-layer bulk, and then has a secondary localization on the same surface where the conduction band lives. And as a quick aside, this is all single particle calculations, but we're working on doing this correctly. And it turns out to be quite important for doing that to compare with transport experiments in a dual gated sample, because when you have very flat bands in many layers, you have to treat the electrostatics of how the charges distribute across all those layers self-consistently. And that actually leads to a decoupling of the action of the two gates. So, these layer polarized states may end up on the bottom surface, whereas the layer delocalized states extend throughout the rest of the stack. That means that one gate couples to both of them, but the other gate gets screened from that special layer polarized state by the delocalized states. And this provides a natural explanation for why in many flat band systems, you actually see features that are tracked to single gates rather than fixed to doping and displacement field, which is kind of an unusual feature of these systems. So we're working on including that. But I think the basic picture of having this dual surface polarized normal state is rather generic. All right, so let me zoom in now on this 8-layer sample again and use the kind of natural axes of the system, which are top and bottom gate voltage. These become important when we're in this band overlap regime, because now we have charges living on both surfaces simultaneously. And so we get this kind of gate decoupling where tuning the bottom gate primarily tunes the charges on the bottom surface, but can't do much to the top surface charges because it's getting, and vice versa for the top gate. And what I'll focus on are these 5 pockets where the color is either slightly more blue than the background or much more blue than the background, meaning that the resistance is dropping towards 0. I'm numbering them SC1 to 5, and the reason is that I'll try to argue that these are in fact superconductors. And there are 5 seemingly distinct pockets for one sign of displacement field. So if you include the other, then there's actually 10 apparently distinct pockets of superconductivity within this regime of the bands overlapping. So first I want to show you that these are indeed superconductors. If we zoom in around 0 volts in the backgate, this is just a zoom in plot. I can raise the magnetic field to 100 millikelvin, those pockets are gone. I could go back to 0 field and raise the temperature to 270 millikelvin, those pockets are gone. So that's kind of indication that those low resistance pockets are indeed superconductors. We can park in the middle of these pockets and measure R versus T. This turns out to be a pretty tricky measurement for technical reasons, just based on how fragile these superconductors are. But all of them have some kind of quasi-abrupt downturn below some very low critical temperature. We can measure differential resistance, dVDI, as a function of the DC current in the magnetic field. What you should expect to see are basically spikes in dVDI at the critical current that form a diamond-like structure. It's pretty messy because these are relatively fragile superconductors with ultra low TC. There's also some sort of zero bias anomaly that we think is due to some sort of contact issue, but we don't totally understand that. But nevertheless, you can see the hints of the structure of superconductors that you expect.
Just curious if you believe the data from SC5 equally to SC1, or if one is a little bit more less believed than.
Let me show you one more set of data. And
that's fine. Like SC2 is a little strange, but
they're all strange in their own way, and I think it's related to some sort of issue with thermalization with the contacts. That's our best guess. I mean, there's also some spatial extent of these states that we don't totally understand how this works yet. But the last set of characterization is to basically sweep the gate voltage. So we park one gate voltage, the top gate, and sweep the other as we raise the temperature or as we raise the magnetic field. And as we raise the temperature, we see these kind of characteristic domes of low resistance pockets forming. As we raise the magnetic field, we also see these characteristic domes. And so, all of these pieces of evidence together suggest that these are some incipient or fragile superconductors, possibly with some contamination issues fertilizing the test. One feature I'll point out that I don't understand, but it's actually rather generic if you look through the literature of Rhombohedral multi-layer graphene, is that with magnetic field, you end up seeing these residues of low resistance, but nowhere close to the lowest resistance you can measure, that persist to way above the nominal upper critical field. And for SC3, it actually goes to like 50 millitesla. So I don't understand what that feature is, and if anyone has an idea, I'd be happy to. But in general, all of these have very low upper critical fields of order like millitesla. And if you believe that that's truly representing the zero temperature upper critical field, then the Ginzburg-Landau coherence length would be very, very long, something on the order of like 500 nanometers to a micron. So compared to the interparticle spacing set by the doping of about 10 nanometers, that puts us really deep in the BCS limit of superconductivity. Now, it turns out that there's nothing special about 8 layers. There's also nothing special about it being misaligned. What we find is that if you align very, very well with boron nitride, you suppress all of these superconductors. But here's a 7-layer sample with like a ½ degree twist, and there's still a superconductor that survives. So now on top of all of this that I told you about before, we have the Moiré physics. So these sets of correlated insulators showing up at 1, 2, 3, 4 electrons per Moiré unit cell. But I want to do the same analysis where I'm restricting my attention primarily to what's happening in this small regime of displacement field where we've not yet opened a gap. So again, we can take a Landau fan using one gate that crosses this resistive ridge emerging from the band insulator at neutrality. On the far left-hand side here, you see this simple set of quantum oscillations that corresponds again to a fourfold degenerate Fermi surface. As we move in here to this nominal band overlap regime, these quantum oscillations flatten out and you get some extra dispersive ones on top. And the FFT becomes more complicated. So all consistent with there being some additional Fermi surface that enters the equation. So again, we can draw the triangle here, and I'll argue that everything in this triangle corresponds to primarily hole doped but band overlapped regime in the system. So I can now focus on this top region. This corresponds to the Moiré remote side for electrons, and plot it in the kind of natural axes of top and bottom gate voltage. And now we can see that everywhere in here forms this kind of like checkerboard of resistive ridges that are likely coming from Van Hoff singularities in the system. And then once the gap opens, then everything takes a left-hand turn and follows contours of fixed displacement field, or fixed doping as a function of displacement field, based on the capacitive lever arm of the top and bottom gates. So now this semi-metallic or band overlap region lives here. And the interesting thing to note is that if you zoom in on this region where we have a low resistance pocket, what you see is that that low resistance pocket forms along a contour of high resistance elsewhere in the map, so what seems to be a Van Hoff singularity. And whether it's superconducting or not seems to be modulated by features coming from being controlled by the other gate. So basically features residing on the other surface of the sample. So the simplest interpretation is that basically, this Van Hoff singularity, which lives on, say, the top surface, is the one that primarily goes superconducting, but it's modulated. It's turned on and off by the nature of the Fermi surface on the other side of the crystal. We can do the usual characterization, so we can measure resistance versus temperature as a function of the gate voltage, resistance versus magnetic field. These have no contact issues, so they look much more like normal superconductivity. Yes.
Yeah, so you say those are Van Hoff similarity features. Do you say that based on Paul data? Or?
I'm probably using it too colloquially, so maybe it's best to think of them just as resistive, short resistive humps. I'm speculating that Van Hoff is the most likely thing that would produce that, but I know we don't know.
You could look at like RXY, changing.
Yeah, we can, and we have that data, and I need to think about it carefully before saying something in front of everyone. Yeah. No, good. Thank you for the suggestions. Okay.
Something to say 5 minutes.
Cool, okay. Right, so we can measure resistance versus temperature, and indeed we see kind of a sharp drop. Again, it saturates in some resistance that's not zero, but turns out to be a relatively common feature of crystalline graphene, especially when the TC is very, very low. Here we don't have this contact anomaly, so you see a much more unusual differential resistance versus DC current, and it goes away by around 10 millitesla. Okay, so some possible implications. The superconductivity is forming out of a very unusual normal state where the density of states is primarily segregated simultaneously to the top and bottom surfaces from two different bands in the system. So we can speculate that maybe one surface or one Fermi surface is primarily responsible for the superconductivity, and the other one may pair by proximity, or it may not form a gap and just remain as an itinerant metal. So just by measuring DC transport, we don't know what the scenario is. We can also speculate at kind of zeroth order that if BCS mechanism is responsible for superconductivity, then having this additional surface layer of charge may actually raise TC by helping to screen away repulsive interactions. But alternatively, if it's cone ligature, then it may actually suppress TC by screening away attractive interactions. And again, these are just speculations at this point. We don't. Now, let me zoom back out and look at what happens once we finally do open a gap in the sample. So with large displacement field, we open a gap, and now this is the regime that we heard a lot about earlier today from Long and Trevor. And what we can see is basically that this same resistive bump that forms the superconductor, once we open a gap, it kind of drifts back towards nu equals 1. And once it hits close to nu equals 1, it triggers a valley polarized symmetry broken phase that has a simultaneous vanishing of the longitudinal resistance and an h/e² quantization of the Hall resistance at zero field. So we can take a Landau fan, and indeed we see that the state slopes consistent with the Chern number of 1 from the Strata formula. It turns out to be a closely competing Chern -1 state. I think it's related to this flipping of the orbital magnetization with doping that we heard about earlier, but I won't go into that. The state is very well formed, so you see this kind of sharp region where Rxx goes to 0, Rxy is h/e² in a kind of canonical hysteresis loop that switches between the two above a coercive field of about 50 millitesla. One note is that this state, to the best of our ability to judge, actually does not form precisely an integer filling, but slightly away from it. And so I'll just point that out, but I don't know what the implication is yet. All right, one more quick story, going back to a 5-layer sample with a moire. Again, this is a regime that has been the subject of the attention this morning, but this is a regime I want to tell you about briefly. So yet again, we can draw these boundaries that seem to indicate this band overlapped, hole doped semi-metal. And within that, there resides this little pocket where we have zero field orbital magnetism, as judged by the fact that you have a non-zero Hall effect at zero field. And this Hall effect can be switched both by sweeping the doping back and forth or by sweeping the displacement field back and forth. Those are separate tuning knobs. And if we look at the maximum value that this Rxy achieves at zero field, it's about 6-ish kiloohms, so that's consistent with the Chern number of 4. The real surprise comes when we turn on a small magnetic field to suppress magnetic switching, although you'll see it here at zero field, even if we didn't. In addition to this primary Chern state, there's some sequence of additional dips in Rxx and bumps in Rxy that have apparently no algebraic relationship with the doping and displacement field. And if I just take a cut, it looks like some sequence of quantum oscillations, but happening at zero magnetic field. We can confirm that these states are topological by raising the magnetic field and taking Landau fan diagrams. And we see that all of these things slope as predicted by the Strata formula. This is the primary state with the largest Rxy. But there's a surprise that the Chern number here is larger than we expected from the Strata formula based on what we saw from Rxy. So Rxy implied a Chern number of 4, and the Strata slope implies a bigger Chern number. That's opposite from what you would expect. And I should mention that Long is also seeing something similar in pentalayer samples and 4-layer samples, I believe.
So this is kind of the opposite of what you can expect from disorder, where disorder can make RxY too small. Actually, this is the opposite hierarchy. So as far as I know, it's not trivially explained by disorder. So here's complete speculation. We're still working on trying to understand this better. But because this is happening in this dual surface polarized regime, you can imagine that there may be some sort of multi-stability condition where the complex electrostatics actually can move charges back and forth between the layers and recur you into the same state over and over and over again as a function of different gate voltage conditions. So the argument would be then that this primary state corresponds to a whole doping of u equals -1, but then you have some two-dimensional electron gas on the other surface that remains itinerant in parallel. That spoils the strata formula. You need to add an additional term to account for these itinerant charges, and that leads to an over-tilting of the strata line, which could explain this mismatch. Okay, so a few brief notes of outlook. With the right Moiré sample, you can get what seems to be just kind of BCS-like superconductivity and very well developed integer quantum anomalous Hall as the same sample. And indeed, this is fairly generic. There's work from Andrea showing that 4-layer sample that happens too with a different Chern number. So you can imagine now trying to create lateral junctions between these two phases in the same device electrostatically to try to engineer for non-abelian localized states. I think also there's a lot of opportunity in terms of lattice control of the system. So in my lab, we've been working on making hydrostatic pressure measurements easier to do. And we also have recent work using piezo-based devices to apply continuously tunable uniaxial strain down to millikelvin temperature. So there's some results on magic angle bilayer graphing that we recently posted. And I think that given how simple this is as a lattice system, we really know the structure. We can start to mess with the lattice in controlled ways and try to understand what happens. So these are just a few of the, I think, many exciting opportunities for the future. And so let me wrap up and thank the people who made this happen. Most of the work was done by my graduate students, Manish, Derek, Anna. Some of the 5-layer work was done by former postdoc Jason Waters, and collaboration with Josh Folk's lab and theory support from Cyprian and Fong at FSU, and of course, Ian from Japan. Okay.
Yeah, let's talk about that. So these features that seems to respond to only one gate, couldn't that be just part of your sample is on a single gated region and you get those kind of features?
No, I think that those single gate features turn out to be like quite universal across, if you look, like many flat band graphene twisted or untwisted, and even twisted TMDs. I think we have some general understanding of why they happen, but the long story short is that we don't have such single gated regions except for small portions of the context with the whole device.
Yeah, but that is at exactly where content is, right? So I would imagine they will give you some weak features adding onto the whole map.
We should talk about it after, but I think the simplest way to see that that's not necessarily the case is by seeing how the quantum oscillations change abruptly from kind of canonical fan-like to these coexisting dispersive and flat states. The flat is basically the portion that's you're not able to tune by the remote gate. The dispersive one is ones that you're directly tuning.
Another question is that in the 8-layer sample with Moiré, do you see the chiral superconductivity?
We haven't pushed the gates there. So,
yeah, so the question on these structures, so you can keep, the people seem to keep going, like 5, 6, 7, 8. So do you have to worry about stacking forms, ABC becoming ABA somewhere?
I think eventually you do, but there's some calculations from the Manchester group that I think indicate that the only stacking configuration that will give you gaps at the charge neutrality point at large displacement field is rhombohedral. Any stacking domain will spoil that and you'll always be metallic. So my understanding is that if you see an insulator at neutrality at large D, it can only be rhombohedral.
Locally, you don't have to worry about disorder where
well,
the stacking disorders.
We image the flakes with an IR camera and Kelvin force probe microscopy, and we see that it has a uniform surface potential. So that's what we can do.
So how far can you go? Can you make 16 layer?
Sure, yeah, I mean, there's work from Manchester that shows that you can go to like, I think 15 nanometers or something. Or
Cool. They have a PEM from the side.
we haven't done it. Yeah.
Is it possible to do?
Sure, yeah, that's
You
possible.
could, so then you could.
Yeah.
Check that, yeah.
Yeah. It's just it.
Yes, question on the superconductors. I haven't looked at Long's data that carefully, but it doesn't go really to zero. Is that also what?
I think honestly that
Yours
it
goes to
goes
zero,
zero.
so it's a little, yeah. okay.
Yeah, okay, so
The
the
superconductors are almost superconducting or?
Well, okay, I think that the sample actually has, you know, a well-formed superconductor. It's just a question of what we measure transport.
Okay.
You know, transport, you have to make electrical contact to the Hall bar, and if you have any small amount of like resistive heating at the contact, and you have such a fragile.
So do you see like
you know,
hysteresis as you cycle or anything like
I
that?
haven't checked so carefully, but
Okay.
it's nothing is obviously hysteric about it. But I should say that, you know, if you look in the,
Sure.
no, I know, I'm also curious, but if you look in the literature, even in like 3-layer Rhombohedral graphene, especially from like Andrea, you'll find that many of these
Yeah, I
states,
haven't been looking.
low TC, like they don't vote the same. But they have all the other signatures of superconductors. So. Any final questions?
No, thank Matt again. Next up is Dan Parker from San Diego.
Can you let me know what like half time done?
Half time? Yeah, sure. And that won't include the Q&A.
Great, okay. All right, so I'm very excited to tell you all today about some surprises in anomalous Hall crystals. So this will be a talk about the subject of electron crystallization, where I take a system that to start with has continuous translation symmetry, and it will spontaneously break down to discrete translation symmetry. The venerable Wigner crystal is the first example of this study. Since then, there have been a few others. In 1986, Halperin and collaborators proposed the Hall crystal, where in a finite magnetic field, you can undergo crystallization and end up with an insulator that has a non-zero Hall conductivity, non-zero Chern. So that's reasonable to have happen in a magnetic field. And just last year, we proposed you could have an anomalous Hall crystal. A system starting at zero magnetic field with time reversal symmetry that crystallizes and spontaneously gives you a Hall conductivity. So that will be our topic for today. What I want to tell you first is, one, why you should care about anomalous Hall crystals, and hint is from Rhombohedral graphene, no surprise today. I'll then tell you about lambda Jonium, which is a proposal for a very simple model where you can understand the universal properties of this new phase of matter. And I'll tell you about 3 surprises in this very simple. And then to conclude, I'll tell you just one thing about the implications for rhombohedral multilayer graphene. Okay, so to start with, let me thank my collaborators here. I particularly want to highlight the role of Zheng Dong, who is graduating this year and will be on the postdoc market. He's phenomenal. Okay, so as motivation, let me flash the same data that we've seen from Longju many times today. And the fractional states here are very inspiring. But to me, the bigger mystery is actually how you get Chern band in the first place. Once you have a Chern band, then getting fractional states is not so rare. But getting a Chern band by itself here is quite surprising. Because, as we've heard, this occurs in the regime where the displacement field pushes the electrons very, very far away from the HPN. And so in that regime, if you look at the band structure in a reasonable single particle model, it's gapless. You get a metal at single particle level, and you don't know which band you might possibly turn into a Chern band here, right? There's no isolated band at all. So It came as quite a surprise then, last year when we looked at this model in mean field, and when you add mean field interactions, then you split off a Chern bin. You take some of these states and you pull them down and split off a Chern bin. And this state you get depends somewhat sensitively on the parameters. If you, for instance, go to very low angles or very low densities, then you will get a trivial band that's split off of the day. And that trivial band looks an awful lot like a Wigner crystal if you look at its charge density. And so the Chern-1 band, by contrast, has this charge density, which is peaked more or less at a hexagonal lattice instead of a triangle. And you can see also it's very large charge everywhere. There's a minimum. What we then notice is that this state survives when you turn the Moiré potential off entirely. In fact, the gap basically doesn't change as you reduce the strength of Moiré from what we thought was realistic to 0. And so what this is saying is you have a transition, for instance, as a function of displacement field from a metallic state into a state that spontaneously crystallizes in the absence of Moiré potential. So this is what we call the anomalous Hall crystal. You're undergoing spontaneous crystallization, but you get a Chern band out instead of a Chern. Okay, and I should mention there are some other groups, including Senthil's group, that found this more or less simultaneously. I think it was the same. Okay, so why does this work? At a qualitative level, we can explain it as follows. The bottom of the bands in Rhombohedral graphene have a huge amount of Berry curvature. And when you open a gamut, there's two sources of Berry curvature. There's the inherent Berry curvature you had, and then there's also the Berry curvature you gain from opening the gamut. So these two sources of Berry curvature could either add, which would give you the Hall crystal, or they could subtract and give you the Wigner crystal, or if you saw in Trithep's talk, they could really subtract and give you the opposite. So all those are possible. This potential mechanism may explain some aspects of the experiments Zhang sees, but there's a number of very tricky questions matching up between this and real experiments. You don't know exactly how strong the Moiré potential is in real life. It's very tricky to understand if you had such an electron crystal, what you would actually measure in a transport experiment. And so to get at this, we decided that we wanted to simplify our lives and first think about the new and universal physics of anomalous Hall crystals in the simplest possible model we could come up with. Okay, so I want to reveal what are the properties we expect to not depend too strongly on any particular model, and just think about what are the properties of this state as a whole. Of course, it's helpful to still take a model. And for that, if you're studying crystallization, there's really nothing better than the Jellium model, the 2D electron gas with interactions. Because there's now many, many decades of understanding on Jellium. And let me just remind you for a second, right? You take a quadratic band, and you add Coulomb interactions, and there's one parameter in it, RS, which is the potential to kinetic ratio. As you tune RS, you go from a Fermi liquid to a Wigner crystal. And basically all aspects of this model have been studied in gory detail, very, very carefully. For instance, there's many decades of development on diffusion Monte Carlo or variational Monte Carlo, understanding this model and its phases and transitions. So if we're trying to understand topological setting for crystallization, it's really helpful to link up with this massive understanding. What we want to do then is we want to upgrade from the Jellium model to a topological Jellium. Okay, so that's our motivation. And in principle, that's easy. You just add another axis on the phase diagram, the Berry curvature axis. Right? Jellium only has a single component, so it has 0 Berry curvature identically. So if we can just add another Berry curvature axis, then we are in good shape. To do this, there is a very very simple way you can do it, where you can add Berry curvature without disrupting any other properties of the molecule. So for this, I want to consider the dispersion term I'm showing here. I'll take a two-component spinor. On the off diagonal, I'll put the Dirac equation, which will give us Dirac cone. Then here I'll put a 1, and here I'll put a del squared. And if you do this, then you get the following dispersion. You get one completely flat band and one very far away band at a energy delta that we can tune up to infinity. So this basically gives us one flat band, and you can write down its spinor analytically. You can just check that this is a zero mode of this equation. This spinor has the structure of a skyrmion in momentum space. At q equals 0, it points up, and as q goes to infinity, it points down. And so here you can see it has actually, well, that's the flip of this one. Yes, flip of this picture. And this gives you a tunable barrier. As I adjust this parameter of lambda here, then I can tune the strength of the Berry curvature, and it will again take the form of a Lorentzian centered at k equals 0. Okay, so that's very nice. This is a very lovely band. We can control its amount of Berry curvature analytically. You can show that the integral of Berry curvature here will start at 0 at lambda equals 0 and go up as you increase them. So our lambda Jellium model then is to take normal Jellium and just tack on this extra kinetic term. So we now have two components. They obey the normal Jellium dispersion plus the extra kinetic term. So this extra kinetic term, remember, had this exactly flat band, and then this p squared over 2n type dispersion turns that into a quadratic band. Standard quadratic band, except now it has an amount of Berry curvature that we tune. Okay.
It breaks some symmetries though, probably.
So far, yeah, let me just say the symmetries. I have continuous translation symmetry and continuous rotation symmetry. No time reversal. So, okay, this is a little bit of a cheat, right? For a real anomalous Hall crystal, you want to spontaneously break time reversal. Here, I'm going to explicitly break it. So you can pretend I had another valley and then explicitly break it, which will always happen in the regime we care about. Okay. So here's what we would hope the phase diagram might be. Right? We have the Fermi liquid, the Wigner crystal is normal. In fact, this entire axis, we know exactly the phase diagram because that's Jellium. And as we move up, we would think that our Wigner crystal might eventually turn into an anomalous Hall crystal because we've put enough Berry curvature in the middle for it to feel it. Okay, so to start off with, we're going to do mean field. Now, one of the motivations in choosing this model is you can do Monte Carlo on it, but for now, we're going to do mean field. And so here's the phase diagram that we end up with. We get the Wigner crystal here in blue, Fermi liquid here in gray, and then a big anomalous Hall crystal regime up here. And I want to walk you through several aspects of this phase diagram. There's some things that are, at least to me, were quite surprising. Okay. And I should mention, of course, that this is the mean field transition. Everything will be pushed very far to the right once you add interactions. But even so, you expect the Fermi liquid Wigner crystal competition to be at something like 5 orders of magnitude less than the interaction strength, so it's very close. You can imagine it'll be pushed to the right differently up here than down here. Okay. So to understand this phase diagram, there's one very important principle that occurs again and again. And that comes from the spinor structure. The schematic way of saying it is that spinors like to align to decrease their energy. And we can understand this as coming from the exchange term. In the exchange term, what happens is you have the dot product of the spinor K with the spinor K plus Q, different momentum. and then there's a minus sign out front. So if the spinors are aligned, then you reduce the energy, right? That's how we get ferromagnetism. And if they're not quite aligned, then we don't. We reduce the energy quite so much. So let's think about what happens then in the limit of large Berry curvature, right? A big Berry curvature peak at 0. In that case, the spinor will as I move away from 0, the spinor points up at the origin, will quickly cant down, pointing down as I move away from the origin. So it'll move quickly over. This means that at the origin, all of the nearby spinors are quite misaligned. And so I can't take advantage of the exchange energy. So meanwhile, if I'm very far out, then everything is more or less aligned, and I do take advantage of exchange. So far out, I'll move down in energy a lot, but near the origin, I'll only move down in energy a tiny bit. So the band will be pulled down everywhere except at the origin. If I think about this just within a Fermi liquid phase, this means that at small interaction strengths, I'll get my normal Fermi liquid. But at large interaction strengths, I would tend to prefer an annular Fermi surface, right? Because I have the origin, which is not pulled down that much, and the rest of the band, which is pulled down, so I'll peak out in the middle. And if you work within mean field, that's exactly what happens. Here you can see at lambda equals 0, the whole band is pulled down, but at high lambda, high Berry curvature, then you peak out in the middle. And so what this leads to at very low interaction strength is a normal Fermi surface, circular Fermi surface to annular Fermi surface. You're out of time. Okay, so that is a lead in to some of the more surprising aspects of this seemingly simple model. Yes.
When this happens, no other instability is still detected, right? It's still Fermi liquid.
Still Fermi liquid. So, okay, here what I'm showing is the mean field phase diagram, assuming it is a liquid state. Not allowing symmetry translation. But yes. So, of course, on top of this, you get translation. Yeah, but this is the phase under.
And just clarify, so this phase diagram that you showed, like in the previous 2 slides, just understand this middle region that you call anomalous whole crystal, you quantified by what? Computing sigma xy?
Yeah.
And just to understand, so how do you compute it? So what, you do mean field to compute sort of renormalized bands, and then you use a single particle formula to compute the sigma xy. This is what you do.
Yeah, exactly.
And you do the rest 10 or 15 and 20. And so what controls all of this?
What controls all of which?
Yeah, what controls even the computation of sigma xy from the single particle?
He's comparing the Chern number.
Yeah.
But still.
So you discretize, you take, 48 by 48 unit cells and you do mean field there. And then you compute the Chern number of the band you get. So that was exactly the same procedure I was doing back here. Okay, so let me tell you now about 3 surprises. The first is what happens as I go from here tuning to here. So up here, we have a re-entrant Wigner. And the reason for that is, again, this k equals 0 point, right? I can't push that down by exchange interactions. And what actually happens at some point is that you will undergo a gap closing, right? This band here with a lot of Berry curvature here will hybridize with the next band up, and you'll close the gap, get Dirac cones for an instance, and reopen. So a standard Dirac mass sign change, except now everything is in interaction induced. I don't even have any Dirac cone at all without. Okay. So that's kind of cute. You get a second order phase transition between a topological to a trivial crystalline state. Okay. The next thing that we wanted to look at is the phonon spectrum. Yeah.
Maybe I get the question. When you say second order phase transition, what's the order parameter?
Interact RS.
No, it's
Oh,
not
no,
order
order
parameter.
parameter. It will be you can work in the two band subspace here, and then look at the the project into that two band subspace, and you'll get a Dirac equation with a mass term on the diagonal. So it will be expectation of the Z Pauli matrix as normal if you work in the band subspace.
No, there is no order parameter. It's topological.
Sorry, say again.
There is no order parameter.
Yeah.
Order parameter.
Yeah. Okay. Next up, we wanted to look at phonons. So for an electronic crystal, there's a gap for charged degrees of freedom, but neutral degrees of freedom are still gaps. You still have Goldstone modes from spontaneously breaking the symmetry. There's actually a distinction here that is not so widely known. So for normal Wigner crystals, there's two modes, which are called the sound mode, which is linearly dispersive, and the plasmon mode, which is square root Q dispersion. In a magnetic field, though, you have a Lorentz force which mixes these two together, and you actually gap out one of the modes, and the other one gets a 2 to the 3 halves. Okay. So for an anomalous Hall crystal, you have Berry curvature in the mix. In terms of the charge degrees of freedom, the Berry curvature gave us a Hall response. Does the same thing happen in the neutral degrees of freedom? Do you get these magnetic type phonons with only a single gapless mode, or do you get the normal 2 gapless modes? To address this, we worked within time-dependent Hartree-Fock, and it turns out that just like a Wigner crystal, you get 2 Goldstone modes, 2 gapless modes, which, as before, are linearly and square root dispersive. So again, you have a sound mode and a plasma. And so it seems like the quantum geometry didn't enter here at all. One would have thought it would mirror the magnetic field in real space, but all it does here is it determines the velocity and the mass that control these. It does not actually gap out the mode.
Are you so confident that other one's gapless?
Well, one reason is because of the following field theory. So we were very confused by that. We didn't want to just trust numerics. We wanted to really understand this carefully. And it turns out that there's a very clear argument you can for this, which I'll say over the next few slides. So to look at this, Ophelia, my collaborator, did a careful Landau theory for the deformations. So we're thinking about an elastic theory for the phonons in a electron crystal. And surprisingly, there's a few things in this theory that have been missed, even though it's many of these terms have been written down for decades. So let me just save them out for a second, and then only 2 will show up afterwards. You have the Coulomb term, which will be responsible for long-range interactions, giving the plasmon. You have a standard mass term. You have a standard volume expansion term. You have a standard shear stiffness term. And then you have a Berry phase term, which you can see has the form of a Lorentz force, right? R's coupled to Py and vice versa. And then there's a new term, the kineoelastic term, which I'll tell you about in a little bit. This, to our knowledge, has not been found before, even though it seems to play a somewhat important role. And so, just to be clear, this is assuming C3 symmetry, but breaking inversion and time. So if we take this field theory, carefully extract the coefficients, then we can do a 0 fit comparison to what we have here, and you can see that it's bang on. And so this is really giving us confidence that it really is capturing things. Okay. So the term here with beta is the one that's like the Lorentz force, and this is the one that is non-zero at finite magnetic field that gaps out one of those voltages. So the question is it 0 here or not? And it turns out you can show analytically that it is exactly 0. The reason for this is a little strange, but follows intuitively from the semi-classical block equations of both. So here they are. Let me remind you. The R dot is coupled to magnetic field, real space, and dually K dot is coupled to the barrier curvature. So those look like they would have the same role, but it's actually a bit different. Our low energy modes are always from sliding crystals, right? You kick the system and then it will start sliding at constant velocity. So if you're sliding at constant velocity, R dot will not be zero. You'll see the magnetic field, but K dot is still zero. And so that means that you don't actually end up coupling to the barrier curvature. Only once you're accelerating, you actually couple to the barrier curvature. So this is the intuitive reason. We also have a nice proof that this is exactly zero. And let me then say the role of this other term, the new one, the kineoelastic term. The kineoelastic term, if you work through it, will give you non-reciprocal phonons. A question?
Is there a symmetry reason, like explanation for why beta is zero?
It has to do with the commutation of the momentum operators. Maybe let me say more. It's not a simple story.
What was the question?
Is there a symmetry reason why beta is? The right way to think is that at zero magnetic field, it will be zero. That's the result. Yeah.
Can we understand the fact there has to be two gapless modes just from there's two commuting translation operators?
Precisely, yes. And so when you have a magnetic field, they fail to commute, and then the for instance, the Haruki and Murayama work applies, and you can show the one. Yeah. Right. So okay, great. So very quickly, the kineoelastic term you can show gives non-reciprocal phonons, where phonons going to the right and phonons going to the left will have very different velocities. And in principle, this is a measurable quantity that you can see will be there. Right, if you deform the crystal, then it will start moving at a constant velocity. And so this has experimental consequences. It should be there whenever you have an electronic crystal without inversions. So in particular, in Rhombohedral graphene, there's inversions. Okay. Our last surprise then is looking at stiffness. So the shear stiffness was one of the terms in our field theory. You can compute it as the derivative of the energy with respect to the modular parameter, which is kind of fun. And so what we did is we looked at the stiffness, for instance, over this line. And what we find is something very alarming. The stiffness goes down. It becomes negative right when you enter the anomalous Hall crystal phase, and then eventually recovers. And if you look at time-dependent Hartree-Fock, you see the same effect. The eigenvalues there become imaginary, signaling that your mean field ground state is unstable. And unstable to what, you might ask? It turns out that it's unstable to lattice deformations. The triangular lattice we've been assuming so far, just because the Wigner crystal is triangular, isn't actually the best ground state. And so if you plot out the ground state energy as a function of the modular parameter of the lattice, you find that the minimum actually can be somewhere different. And so you can have square electron crystals, you can have rhombohedral electron crystals, or you can have triangular electron crystals. And this is kind of generic, right? That once you no longer have the classical limit of the Wigner crystal, you no longer need to be very close to a triangular lattice, and you can have many other options showing up. Okay, so that's something one should be aware of, especially if we're thinking about rhombohedral graphene. It doesn't have to be a triangular crystal. Maybe I can finish, yeah. For the last 2 minutes, let me go back to actual rhombohedral graphene. So there, we were able to find at least one point where the anomalous Hall crystal within our microscopic model is triangular, and we have computed its soft mode spectrum as before. there, because C2 symmetry is broken, we see these non-reciprocal phonons where the phonon velocity to the right is substantially higher than the phonon velocity to the left. And you can see there that again, there's the plasmon curve, and it very quickly hits the next bands before you get too far. So this means at least that there's one point in this phase diagram with a stable Hall crystal that's triangular. There's been some doubt and confusion about that in the literature, so I just wanted to give you its stats right there if you want. And with that, let me wrap up. So today I told you about lambda Jillian, which is a very simple extension of the Jillian model that incorporates topology while preserving the quadratic band of the Jillian model exactly. This is a very good testing ground for our understanding of electron crystals with topology. In particular, this is a good model for numerics like variational Monte Carlo, and I'm working in that direction with some collaborators. And we also saw a couple of surprises. There's a second order crystal to crystal transition. Despite the Berry curvature, you see that the phonon spectrum aligns with non-magnetic instead of magnetic Wigner crystal spectrum. And we see that, at least in this regime here, non-triangular electron crystals are stabilized. I also wanted to remind you, finally, that this kineoelastic term is generally present whenever you have an electron crystal without inversion symmetry. And so if Rhombohedral were to exhibit any Wigner crystals or Hall crystals, it should be there and should be in principle there. All right, thank you very much.
Okay. Before that, I wanted to ask you 2 minutes ago. So in your data, stiffness is negative, but in a relatively narrow range.
Yes.
Question: outside this range, is triangular state ground state, or it's just local minimum?
Right. So the way to think about this is that we're doing the mean field assuming a triangular. And so within that variational space, we find some Hall crystal state here. But if I broaden my variational space to allow all possible lattices, then I find I was actually at a saddle point. And I could go down and there's some other minimum down here, right? This one is triangular and this one is, say, square. And so that's what I'm showing happens here on this slide. If I start at the triangular point here, I can go downhill to the square.
And in the range where stiffness is positive,
yes,
you still get this, or how it works?
Yeah, so in the range where stiffness is positive, so at sufficiently large amount of Berry curvature, then the stiffness becomes positive, and I recover to to an actually stable point, even within the lattice deformation.
But does that mean it's the global ground state?
Global is hard to say. It is the ground state at mean field level over all lattice shapes, assuming a density of 1 electron per unit. So I'm not allowing further charge density.
Are you ignoring spin here?
Yeah, there's no spin in this file.
So I appreciate your discussion of elastic modes of the Wigner crystal, but I think earlier in your talk, you had picture of electronic band in presence of Wigner crystal. Now, what is it even? I mean, your electrons already crystallized. Now, who is living in this band?
Right. So probably you meant here, right?
Yes.
Yes. So this is the Hartree-Fock band structure, right? So I'm assuming some ground state, and then I can ask about 1 electron or 1 hole excitations on top of that.
So this is empty band, one particle band. So it's not a filled band.
So this is a filled band, yeah.
But filled by whom? Electrons already form a Wigner crystal.
Yes.
Now, who fills this band?
So when I formed the Wigner crystal, right, I started with continuous translations. I formed the Wigner crystal, breaking translations.
Right.
And now I have a bromosome. So I can ask about bands in that bromosome.
Right.
And I'll have some number of electrons that are occupied, so I'll have some number of filled bands.
But that's not the same electrons that form Wigner crystal, or is it Same
It's
electron.
the same electrons, yeah.
But you already localized them. Why should?
I already localized. You can imagine thinking about this is, right, take my Wigner crystal, turn on a tiny penny, right now I have an explicit Rho zone from the start. And then it makes perfect sense to ask about what is the mean field band structure relative to a particular ground state. And so that's the same thing, you know, adiabatically true to the potential.
More final questions? Since we're already running a little bit late and I need to make an announcement, so let's thank Dan again. So lunch, as I said this morning, is up to us. There are several things that are nearby, including a sweet cream, a knockoff Java equivalent Mediterranean restaurant, the name of which I can't remember. An Anomaly place. Well, that's the deli, which is quite good. And a Korean restaurant, also quite good. Something else. If you're getting lost, find a local. Locals will hopefully fractalize on some level. So find me, find Andre, find Fiona, find Alex, they will take you somewhere. But you know, already in.
I haven't seen you in ages. I know, he was figuring it down and just, I know.
He's been tremendously going. Yeah, it's nice.
I thought somebody would
Teach me.
I should just I should essentially one part. It's actually like some levels. That much like typically, we don't see pretty uniform. Like bubbles of.
No, kind of incredibly like from.
It seems to be like pretty large demand. We're not sure if they're like.
What you want to think about is like.
Yeah, I mean, we don't really know what's going to do, but the games are.
Possibly change it. Quite the same.
Yeah.
Every day, someone gets the no.
You're still at distance.
There's no
So right now I'm working on just handling this. It is specific. Yeah, looking similar to how to do version of local connection. So you that was the function lecture for non-local operations. But it was no. More that can have. So what about fixed dynamics? Was on target and then for some space. Simple from the everything is done. Okay, so the shepherd will start with to make it into their server. Temporarily wrong size and all there. Yeah, they that's a so you think that's a correct, yeah, same case. So you talk at it. So you can aside finding that big one deeper to because and they just compare it to the Gerber. And there's use so over the所以你右边两个第一个都是 top stake 对。为什么会两个 stake 不到 ？So this would be something to confine if you just let the temperature or because of one direction they will just. So 一个 peak 是 outside 一个是 reverse 对吧？就是像这样的那个时候你的 sports 的更像那个 great then you have something like that in in order to figure where the next one value you have to this big guys can每个方面有4个项，上来一个是我的分布的上来。我
Okay, hi everyone. Welcome to the afternoon session. For those of you who don't know me, I'm Fiona and I'm one of the organizers of the workshop. And we're going to start the afternoon with Carolyn Zhang, who is going to tell us the answer to a very old question: what is a proof anomaly? Okay. Oh, you're supposed to have a microphone.
Hello? Okay. Hi, I'm happy to kick off this afternoon session, switching gears a little bit. And the question I would like to ask today is, what is an Hooft anomaly? This is work with Wilbur Shirley, Wenjie Ji, and Michael Levin. That should be out in a few weeks, couple weeks. This is kind of a scary, ambiguous word, but many of you are familiar with examples of these guys because many of you are familiar with SPTs. And we're familiar that when you have a symmetry-protected topological phase, this I've just illustrated in 2+2 dimensions, 2+1D, it's often associated with non-trivial boundary physics. So for example, you might have some degeneracy, spontaneous symmetry breaking in the cluster state. You might have gapless edge modes in a topological insulator. You in 3+1 dimensions, if the SPT is in 3+1D, you can even have boundary topological order. And so an SPT has non-trivial boundary physics. If you work a bit more with SPTs, you also find that SPTs have weird representations of the symmetry. So it's kind of boring in the bulk, but if you look at how the symmetry acts on the boundary, it acts in some non-on-site way. So in 2+1D, you have this exactly solvable model for Z2 SPT. And you can see that this is the representation of the symmetry on the boundary. And it's not just a product of sigma x. It's this like weird not on-site representation of the Z2 symmetry. And you can show that this squares to 1. So it's really a Z2 operator. It's just not on-site. So we know many properties of SPTs. And SPTs are associated with Hooft anomalies, which are associated with the non-trivial representation of the symmetry on the boundary. And even though this is a very old topic, SPTs have been studied for a long time, anomalies have been studied for a long time, there's still not a real consensus as to what the word Hooft anomaly means in the literature or in the community. So there was recently a poll at KITP asking people what is a Hooft anomaly, and it was basically 50-50 split. So half of the people said it's an obstruction to gauging the symmetry. What that means is you couple the symmetry to a background gauge field and you allow it to fluctuate. We'll see that this is for unitary kind of invertible internal symmetries. This is the same as being able to make the symmetry on site. So I'll use those words interchangeably. And then the other, just as popular definition of Hooft anomaly is an obstruction to a trivially gapped symmetric state. So as we saw, where these anomalies were manifest, which is the boundary of these SPTs, you had non-trivial boundary physics. You didn't have a unique kind of symmetric gap state. And that's associated with the second definition of anomaly. Okay, so there's a lot of recent work trying to iron out the details of what it means to have an anomaly, non-on-site symmetries, lattice model anomalies, etc. And there was very recent work that showed in 1+1D, these two definitions of anomaly are the same. So this happens if and only if this is true. And or in other words, a symmetry is uncitable if and only if there exists an SPT, or a trivially symmetric gap symmetric state. What we'll show is that this is not true in 2+1D. So if you work carefully in lattice systems, you can have a different classification of anomalies depending on which definition you choose. So yeah, in this work, we'll consider the most vanilla type of systems, which are lattice models in 2+1D, finite dimensional ancillas. The most vanilla type of symmetry is unitary internal finite zero form symmetries. And we'll show that there exist examples of not uncitable symmetries that are nevertheless admit trivially symmetric states. And we also give a classification of these kind of symmetries. So we say that these are non-uncitable but non-anomalous symmetries. Dominic else calls them anomalous. So depends on your definition in this context. And this is kind of we show that there's a classification given by second cohomology classes with coefficients in the rationals under multiplication. And that will be apparent later. So there's a nice mathematical structure of these kinds of obstructions. A nice side result of this work is that these kinds of non-uncitable but non-anomalous symmetries also give us entanglers for SPTs that were previously not very well understood. So what do I mean by entangler? I mean, if you give me a product state, SPTs are short-range entangled. So what that means is that I can prepare the SPT with a find-up circuit. And because these are different phases, if we keep the symmetry, that means that the circuit has to break the symmetry. That means the circuit has to contain gates that don't commute with the symmetry. But in any case, the circuit exists, and the circuit allows us to go from a product state to this non-trivial SPT state. But if you give me a SPT that you desire, how do we construct this circuit? How do we prepare the state? And this is the question of how do we obtain an entangler from the product state to the given SPT state of desire that you desire. It turns out that we have an understanding of what this USPT is for broad classes of SPTs, but not for all of them. And these kinds of non-uncitable but non-anomalous symmetries allow us to entangle some SPTs that we previously didn't know how to entangle. Okay. The ones that I will talk about are not the only ones in the literature. There are previous ones in the literature, but they just weren't identified as symmetries. So an example is this radical Fouquet circuit that was studied by Poe et al. And also Drew Potter. And It's a unitary operator that acts in this on these qubits on this lattice that to the fourth power is equal to 1. And it's locality preserving, so it can serve as a Z4 symmetry. You can also show that if you act it on a toric code bound state, it performs EM permutation along for each application of this unitary. And you can also show that if you restrict this operator to a region and take it to the fourth power, it will give you a qubit translation squared on the boundary of that region. And we will show that that means that this cannot be made, the symmetry can't be made on site and can't be gauged. However, if you look at the classification of Z4 SPTs in 3+1D, it's trivial. So this can't be associated with the boundary of any 3+1D non-trivial SPT, and it's not anomalous in that sense. And this kind of radical flow case circuit has recently been implemented in a superconducting qubit array by this paper from this past year, where they explicitly demonstrated using the protocol, the gates that were mentioned in the previous paper, this chiral edge mode, which comes from the fact that the symmetry operator square gives you a translation. Okay. So why is this symmetry operator squaring giving a translation weird? If I had an on-site Z4 symmetry, so this is just a Z4 symmetry, which is a product of local operators acting on each qubit or each on-site spin, then we can always restrict it such that we just take the product of those local unitaries that are acting within A. But whenever we take a symmetry and we restrict it to a region, there's an ambiguity of how we choose that restriction. So in particular, we can decorate this boundary with any locality preserving unitary, and those decorations are classified. So there's a classification of these locality preserving unitaries in 1D, and they are basically, for qubits, they're just integer translations. And there's an index that you can even associate with each of these locality preserving unitaries. So what that means is if you take this guy to the fourth power, then it has to have a translation to the fourth power, right? Because each of them comes with one of these guys, which has some integer translation, n equals 0, 1, -1, etc., up to a finite depth circuit. And you can't have something that this guy to the fourth power is translation square. And so that clearly says that UG is not an on-site symmetry, and it's not too hard to convince yourself that it's not equivalent to any on-site symmetry. Meaning, if you conjugate it by some locality preserving unitary or tensor with some ancillas, you can never get rid. You can't change this square to 4. Okay, so in summary, this Z4 operator does not describe the boundary of any Z4 non-trivial SPT, but it's nevertheless not on-siteable and not gaugeable. And this we will give a very simple example shortly that will that's even more simple than the Z4 example. But to do that, we'll have a couple slides of formal properties that will allow us to classify these guys, and then we'll go through this very simple example. So to classify these guys, it's useful to understand the classification of locality preserving unitaries in 1+1D. So these are locality preserving units, quantum cellular automaton, which are locality preserving unitaries modulo finite depth circuits. So we take all of these kinds of unitaries which conjugate local operators to nearby local operators, and we identify them if they just differ by a finite depth circuit. And these have been classified, as I mentioned, by this very nice paper in 2012. And they're basically just generalized translations. So with each input unitary, you can compute an index. And this index is P over Q, which is a rational number. This basically tells you the degrees of freedom translated to the right versus the degrees of freedom translated to the left. So if P is 2 and Q is 1, that means we're translating a qubit to the right. If P is 2 and Q is 3, that means we translate a qubit to the right and a Q trit to the left. And there's a way to even just compute this number given an input unitary. So it's something that's really computable. So that means that now if I have a symmetry operator in 2+1D, I can define this 1D operator by taking the restriction of the symmetry of G, and then of H, and then of GH inverse. And you can see that this guy acts as identity in the bulk of this region A, because the symmetry operators cancel. But they can give you some locality preserving unitary on the boundary of A. And what this indexes is just the GMVW index of this locality preserving unitary. And for the mathematical classification, you can do this. You can show that this is actually a 2 cocycle. What that is a function from 2 group elements to the rationals in this case. And there's a closure property, and that comes from the associativity of these symmetry operators. And there's also equivalence up to co-boundary, which is related to this ambiguity of how we truncate operators. But in any case, it's a well-defined mathematical object, and we can classify them. Okay, so that was very abstract.
Sorry, I just want to make sure I understand the procedure. So you've got the symmetry. Okay, so you've got G and H, and the idea is you're applying them both to the full region and looking the restriction to the boundary?
Right, so we have G and H, which are global symmetry operators, and you can restrict them to a region A. So you can then look at UG, UH, UGH inverse, and that will only live on the boundary of A. And then that's a, yeah.
That's how you're making your omega.
And then that's a locality preserving unitary, and you can compute the GMVW index.
Okay.
That will give you a rational number. Okay, so this is an extremely simple example that has a non-trivial index. It's just, you consider qubits on a 2D lattice, and you have qubits on the vertices and qubits on the faces. And you have an operator that's a Z2 operator, it squares the identity on this lattice. You can write this operator as follows. The operator consists of spin flips on all of the plaquettes, followed by a translation of the tau spins according to the domain wall configuration of the plaquettes. So what this S is basically a functional. It takes as input a domain wall configuration and outputs an operator that acts on the taus based on the domain wall configuration of the sigmas. In particular, it translates the taus in a counterclockwise direction with the upspins on the left. And this is a finite depth circuit. You can show it's a finite depth circuit, and you can show that it's locality preserving because it's a finite depth circuit. You can show that it takes local operators to nearby local operators. It takes this plaquette spin to an operator supported in the 6 plaquettes nearby. It also takes this tau spin to operator supported on the 3 neighboring vertices. And you can also calculate the index very simply. So we can restrict the operator to act on the lower half space, so below this black line. And then if we act with UG on this lower half space, then it will translate all the taus here because you have a domain wall. And then it will also translate the taus in this direction because you have a domain wall. And you can, if you work carefully through all the different domain wall configurations, what you find is that at an operator level, this guy squares to some translation with a finite depth circuit. The finite depth circuit comes from all of these swaps, but it's not very important. And you can compute this 2 cocycle, which is this map from 2 group elements to the rationals, and you can show that it's non-trivial under this classification. So that means that it's not unsightable and not gaugeable. Nevertheless, there's a trivially symmetric state. It's just a product state, actually. So the all up state on all the vertices and all plus on all the plaquettes respects this symmetry. And you can even write down a parent Hamiltonian that commutes with the symmetry and whose unique ground state is this product state. So it's really kind of a trivial symmetry. It's not obvious how to write down this Hamiltonian because you want it to be symmetric and a commuting projector, but you have good collaborators who can work out algebra with Pauli operators, and then they come up with this. And so this is kind of a complicated Hamiltonian, but it does the job, and there's no obstruction to like a trivially symmetric state for this symmetry. One interesting aspect of these kinds of non-anomalous but non-unsightable symmetries is that they give us new SPT entanglers. So as I mentioned before, sometimes it's interesting to ask the question, if I want to have a non-trivial SPT state, how do I get there from a product state? And we know how to construct these entanglers for many kinds of SPTs. So for example, there's a broad class of bosonic SPTs that are so-called incohomology. And there's a recipe for how to construct these unitary circuits that take you from the trivial state to these SPT states. Similarly, for fermionic systems, there's a broad classification of in supercohomology SPT states, and we know how to construct these unitaries that take you from the trivial state to these SPT states. You can find them explicitly in these papers. And these SPT entanglers are kind of nice. So first of all, we can write them as like very nice, simple finite depth circuits. And even though they contain symmetry breaking gates, these constructions allow you to define a circuit that as a whole still commutes with the symmetry. So it not only maps you from a symmetric state to symmetric state, but the unitary as a whole commutes with the symmetry. It just can't be broken into symmetric pieces. And that's about as good as you can get for an SPT entangler. However, there are still SPTs that we didn't know how to entangle up till now. An example is a very simple example is a 2 + 1D fermionic SPTs with the symmetry Z2 cross Z2F. And you can show that there's a Z8 classification of these guys. So that means that if you take the root phase and you stack 8 copies of it, that's kind of a trivial state. So the ones where nu is even, those are in supercohomology. So we know how to prepare those states. But the ones with nu odd are not of those class. And previously, there wasn't a known entangler for this kind of state. It has a simple physical intuition. It's Z2 cross Z2F. And so the Z2 domain walls are decorated by Katai wires. So it has a simple kind of decorated domain wall description. But it didn't fit into any of these kind of previous classifications, so it didn't have like a nice entangler. And provably, you can show that there's no symmetric entangler, unlike all of the previous classes that I mentioned before. So we know a lot about this guy. We know that an exactly solvable model for this SPT, we just didn't know how to entangle it. So there's a very simple fermionic model that's similar to the Z2 bosonic symmetry that I mentioned before. You just kind of, the plaquettes are still bosonic qubits. You just put Majorana fermions on these edges instead of the bosonic spins. And so you can show, if you're a bit careful, that there's a very similar Z2 symmetry operator that I compared to the bosonic case, that if you apply it to the product state, it actually entangles all these Katai wires. It's a finite depth circuit, entangles all these Katai wires, and it takes you to this non-trivial Z2 cross Z2F root SPT phase. That was just the one that was written by this Tarantino-Fitkowski paper. And you can show actually that this is not a symmetric under the Z2 symmetry. This is not a symmetric operator under the Z2 symmetry. So it's a SPT entangler that does not commute with the symmetry. It just maps one symmetric state to another symmetric state. And that's about as good as you can get for this kind of particular SPT state. All right, so I gave some simple examples, but there's actually construction for general two-co-cycle. And there's a close relationship between these non-on-sitable symmetries and flow K phases in higher dimensions. So this also gives new kind of flow K phases in higher dimensions that are not just SPT pumping phases. And then we also have various other examples in bosonic and fermionic contexts. And some future directions that might be interesting are looking to higher dimensions and having a more complete story, because I just talked about 2 + 1D in a particular class of examples. What are the physical consequences of this kind of index and a general relationship to SPT entanglers? So what kinds of SPTs can be entangled with symmetric circuits that are symmetric as a whole, but just contain symmetry breaking gates? And in what cases can you not do that, but you can use an approach similar to what we use for the Z2 cross Z2F SPT. So that will be able to kind of differentiate between different kinds of SPTs and how hard they are to prepare. All right, so that's all I have. Thank you for your attention.
Yeah, I was wondering if you can think of all of these non-trivial examples as like flow K SPT invariants for like full spectrum rather than just like a ground state.
Yeah, indeed. So the reason why there's a discrepancy you might have is because these are with operators where you have the full spectrum, and so you don't necessarily think that it should match with field theory calculations, which only care about the ground state. And so indeed, I think that even though we show that there are trivial ground states, it's likely that there are protected degeneracies in the higher energy spectrum, and that would potentially feed into this kind of physical consequences question. Yeah, and then there's more things related to that line, but we can discuss. Yeah.
So, so as I understand it, the part of what you discussed was, can I phrase it this way, that an anomalous symmetry is not on site. It's not on-siteable. But you're asking the converse question, non-on-siteable, does that make it anomalous?
Yeah.
And you're saying that it doesn't necessarily make it anomalous.
Yes.
Okay. Yeah, okay, I'm good. Yeah.
Yeah.
Okay, so I'm from a completely different community, from high energy theory, and there's something that I didn't follow, at least one thing. So in high energy theory, there's a fairly standard argument that says that if a symmetry is not gaugeable, then there cannot be a completely trivial ground state.
Yes.
Which basically argues by contradiction. You've probably seen this argument. So how does it go around your construction?
Yeah, so from the high energy theory perspective, you use the fact that an anomaly is an invariant under RG flow, right?
Exactly.
And this anomaly is not an invariant under RG flow.
How do you see that in your argument?
So, so it's kind of clear from the fact that, okay, so in this kind of lattice model, because you can have a trivially symmetric state under the symmetry, you can have a system, this can emerge in the IR. How do I say it in a simple way? Yeah, maybe one way to just see it is that you can have a trivially symmetric state under the symmetry, even though it's not gaugeable. And there's subtleties about gauging on the lattice and in lattice models. And you can see that in this case, the symmetry, even though it's an internal symmetry in the sense that it doesn't depend on the crystal structure, it sort of mixes with the spatial symmetries because when you restrict it, it has this translation. And so the microscopic implementation of this symmetry in lattice models actually, because it kind of mixes with the translation, it allows you to still have this kind of trivially symmetric ground state. And so, yeah, this is a case where this kind of anomaly is not actually invariant under RG flow. Yeah.
That's very interesting, but also very confusing. Okay, I'll have to read your paper when it comes out, if it's not already out. It's absolutely fascinating. Okay.
The fact that you can build this local thing on the edge, does that mean you can detach the Hamiltonian on the edge, like the surface Hamiltonian from the bulk? In some cases.
So it's often the case that if you have a gap theory, you can write an effective boundary theory. And that's the effective boundary theory that might like spontaneously break the boundary symmetry, et cetera. So that's you can do it in most cases. In this case, it's kind of funny because if you try to restrict the symmetry, then you have this translation along the boundary. And so if you want a Hamiltonian that respects that, there somehow can't be any coupling between the bulk and the boundary because then the Hamiltonian term will just grow as you apply the symmetry operator. And so it's actually like less decoupleable than your usual symmetry in that sense. Yeah.
Can you say a little bit, since you have it on your slide, about the relationship to, sort of these boundaries of these higher dimensional flochet things? Because the symmetry has a very flochet-like character in what it's doing. And so maybe you can give us a brief sketch of how this.
Yeah, so there's a mapping between non-unsightable symmetries in D dimensions, GQCA in D+1 dimensions, and flochet phases in D+2 dimensions. And you can see this from the usual, like in the usual anomaly case, you have an anomalous symmetry in D dimensions. That's related to an SPT in D+1 dimensions. So an SPT is entangled by GQCA. And then that's related to a G flochet phase in D+2 dimensions, which is a SPT pump. So that's kind of, but in this case, you have a non-anomalous, non-unsightable symmetry in 2 dimensions. And so that implies GQC in 3+1 dimensions, that's not an SPT entangler. It's just kind of entangle the trivial state. And G flow K phase in 4+1D, that's not an SPT pump. So that's kind of the new class of flow K phases that are non-trivial. They're protected by the symmetry, but they aren't like pumping SPTs, which is what we usually associate with G flow K phases.
Great. If there are no further questions, let's thank Carolyn. Great. So our next speaker is Drew Potter, and his name tag is a little deceptive. He was at UBC, but he's now at Continuum. And he's going to tell us about digital quantum magnetism.
Thank you, Fiona, and thanks for the opportunity to come to the conference and relive my glory days as a minor physicist. So today I'll be talking about a platform for quantum matter, although maybe not topological yet. And what I want to talk about is an experiment that we did recently on a trapped ion quantum processor, where we're starting to be able to simulate models of quantum magnetism at a scale and in a regime that you might care about for condensed matter physics, but where it's becoming very hard or possibly not achievable to keep up with classical computation. And so this is a result of a large collaboration, not only of people at Quantinuum, but also in partnership with universities who are really experts in some state-of-the-art classical methods, like Frank Pullman's group at Munich, group at Fermionic, Garnet Chen's group at Caltech. Yeah, I'll talk a bit about, yeah, basically we relied a lot on them to keep us honest with the state of the art on what classical computers can do. Okay, so since this is a condensed matter audience and maybe not so familiar with what we do at Quantinuum, I wanted to talk a little bit about the platform that we're using. So the quantum computers that we make are trapped ion quantum computers. Shown here is the current H2 system, where these purple dots are ytterbium ions, which are the qubits. They take a pair of like hyperfine levels in there that we use as a qubit. And they are levitated above a trap, which has the shape of a kind of a racetrack. And the qubits are entangled by laser light that couples the spin to the motional degrees of freedom, the vibrational modes between the two ions to mediate entanglement. And they can achieve very high fidelity entangling operations with entangling gate errors that are less than a part in 1,000. And another interesting feature of this system is that these ions are not in a fixed configuration. They can actually be shuttled around by electrodes. And so you can gate nearby ions, but you can actually do operations like splitting up a pair of ions, swapping them with other ions and rearranging them to rearrange into kind of different connectivities. And since the coherence times of these ions is quite long, there's little, although not zero, memory error accumulated during these transport operations. And you can kind of think about this as achieving an arbitrary pairwise connectivity. So you're not, even though the transport path is in 1D, you're able to simulate larger, more complicated connectivities. Okay, so with these kind of gate errors and with other systems that are have comparable gate fidelities, you can do a few thousand quantum operations or entangling gates before noise starts dominating your system. And with 50 to 100 qubits, the kind of scales that people have achieved, these are starting to get large enough where if you do kind of a random quantum circuit and sample the output, that it's not possible to do a similar kind of computation on a classical device. So in some sense, these random circuit sampling quantum supremacy type experiments are a bit contrived. There's not really clear applications for what you want to do, and they're basically contrived to give quantum processors a maximal advantage over classical counterparts. Basically, if you have a limited number of gates you can do before noise takes over your system, they use the maximum amount of entanglement per gate. They also have very unstructured circuits, and they ask you to do a very complicated thing, which is to take a snapshot of a many-body wave function rather than computing something that condensed matter physicists would typically care about, like an expectation value of a local observable. So what I want to talk about today is shifting gears from this kind of contrived quantum supremacy setup to trying to tackle questions that condensed matter materials scientists and chemists might care about. And here, if you wanted to simulate like a lattice model, maybe an Ising model will be what I'll talk about today. The bar for achieving a quantum advantage is much higher. And the reason is that if you want to describe low energy physics, Hamiltonian simulation requires simulating very fine-grained time steps, and which means that you're going to do noisy gates, but they're not going to build up that much entanglement. So you won't be able to achieve as long, effectively, time simulations as you might in a random, highly entangling circuit. And these models also, as we all know and love, are highly structured, and the classical algorithms are quite good. And so there's a danger that you can release an experiment with nominally like hundreds of qubits that if you do things in a naive way, you have no chance of simulating classically. But smart people who are experts in tensor networks can simulate it the next day on their laptop. Yeah.
There's a question.
Yeah.
There's a question of how accurate the quantum computer is representing the wave function, right? So you can represent an MPS with some lower accuracies. Is there a point?
Yeah, I mean, let's set as a target computing like local observables. Yeah, you could also ask, how hard is it to actually capture like samples from the wave function? But yeah, I don't know if you have any ideas of like a application for the latter, but normally I just want to know like, 2-point functions, maybe string order parameters if we're feeling fancy, things like that. Okay, so here's the setup of the model that we'll look at. So it's we'll keep things very simple. It'll be a 2D square lattice transverse field Ising model, and to show off that we have arbitrary connectivity to limit boundary effects, and also to make things kind of challenging for tensor network simulations. We're going to consider this on a torus with periodic boundary conditions, which can be relatively easily implemented in this architecture. We're going to trotterize the dynamic so that you alternate between applying the transverse field and the exchange interactions for a short amount of time, delta t. And we'll start from a unentangled product state that's at a tunable angle on the Bloch sphere between the z and x plane. And we'll parameterize the kind of energy density of this initial state effectively through the deviation from the mean field value of this theta, the one that would give you the mean field ground state. So that I'll call delta theta. Yeah.
So, is it really a periodic lattice?
Yeah.
There's some uncertainty of the assume in the lattice spacing.
Well, I mean, we just implement these interactions, so there's no actual geometry. It's not literally realized in the computer, but the rotations that we apply between all the gates are equal and wrap around. Yeah.
So the question is, the fact that you have this circular geometry, doesn't that allow you to connect it one way, or no? That doesn't matter. You can connect it any way with any gate. Like your geometry.
Yeah, you could do kind of whatever graph you want.
Do a Klein bubble.
You could, yeah. Yeah.
And the goal is to calculate what?
Oh, give me a sec. Building up to it. The total magnetization is the, and we'll look at basically total and local magnetization. But you can measure any local observable for or actually what you get is samples from the wave function. So whatever you want to do with those, you can do. Yeah, so what do we expect from this? So if you took infinitely fine time steps, you would simulate the time evolution of this model. We'll take a rather modest time step that's like a quarter of in units of inverse J. And what you would generally expect is that for a small but not zero time step, that this trotterized evolution is basically a Floquet dynamics. And you can approximate it up to a very long time by time evolution with a effective Hamiltonian H Floquet, which looks like your original Hamiltonian plus some other stuff that has the same symmetries but further neighbor connectivities and so on. And so this approximation holds up to a time scale that's like exponential in 1 over your time step for small time steps. And beyond that time, you start noticing that energy is not conserved. You get like Floquet Umklapp kind of processes that will heat the system up to infinite temperature. So if you look at a local observable like total magnetization, you might see something like, you'll see an initial transient where it relaxes to basically a thermal equilibrium under this Floquet Hamiltonian, where the temperature is set by the energy density of your initial state, which we'll control by this angle delta theta. And then for an exponentially long time, which if your time step is small is a long time, if your time step is large may not be that long, you'll see basically thermal equilibrium with respect to this Floquet Hamiltonian, and then beyond that you'll heat to infinite temperature and your observable will just go to its infinite temperature value, shown here as 0. If you look at a conserved quantity, you'll see a much slower hydrodynamic tail to this relaxation after this initial thermalization from diffusion, or yeah, whatever your hydrodynamics is. In this case, it'll just be diffusion. Okay, so what regimes in this model do we expect that a quantum computer can beat a classical computer? And so the idea that we had is that you don't want to look at too high of energy density because then the correlations will be very short and you can capture this with a very short range correlated ansatz. You actually also don't want to look too near the ground state because sensor network methods are very good in the ground state where you have area law or near area law physics. And so actually the hard point that I think that the hardest point in this model to simulate is something kind of near the classical phase transition, not too far from the quantum critical point, so that you actually have some coherent entanglement, and not too close to the ground state, so that the dynamics build up lots of entanglement that are hard to capture. So the large correlation length and large entanglement. Okay, so now with that in mind, I want to talk a little bit about some dirty laundry of implementing this on a noisy quantum device. So we're going to push the limits of what you can do without noise taking over your simulation. And to do that, we're going to leverage some nice properties of how noise affects a system that's describing Hamiltonian evolution. So if you have an error shown here as a star in a random circuit, it basically spreads and propagates within its light cone of the circuit and poisons the output of any observable that you pick. So this is for a random unitary, a circuit made of random unitaries. In a thermalizing system, the situation is very different. So intuitively, you would expect an error basically locally injecting some heat. And in a thermalizing system, that heat will kind of spread out, and its impact on local observables at a later time will be very small. You'll basically have just dumped a tiny bit of not sub-extensive energy into the system with a single error. And so the idea is that in these thermalizing dynamics, errors are actually less harmful in a sense than in random circuits. And what this theory paper here shows through simulations and arguments like what I presented is that this actually gives you a very simple dependence of an observable that you calculate as a function of the amount of noise you have in your system. Basically, if you compare the ratio of the noisy observable to the ideal clean one, it decays exponentially with some constant and times the rate of noise in a large class of models. Yeah.
By observable, you mean on-site or very local observable?
Yeah, it could be viewpoints or things like that. Yeah. And so this suggests like a nice way to get to kind of extrapolate the effect of measuring an observable that is in a noisy circuit back to what it should be in an ideal case, which was kind of introduced in a general context by these folks at IBM called zero noise extrapolation. And the idea sounds kind of crazy. You basically artificially crank up the noise in your system. You measure the lowest noise you can achieve and some higher noises, and you fit and extrapolate back to zero noise. And in these thermalizing systems, there's this very simple exponential ansatz. I'm showing here simulation data works very well to extrapolating from modest noise back to the noiseless case.
Under S, it's the different curves. This is.
So sorry, this is S is the number of time steps in the simulation. This is for a 5x5, something you can do with ED. And this is like the artificial rescaling of how noisy, this noise rate P. So basically your 2-qubit gate errors. So the way you do it in practice is we kind of do a bunch of benchmarking to characterize the noise model. And then we artificially stochastically inject like polynoise with the same structure as the noise model, but with like a tunable rate. And then do a few different experiments and do this fitting and extrapolate back. Okay, so let's see how this works in practice. Sorry, this plot is crazy, and I'll go through it in pieces. So to start, I'm going to start with this, this point here. That's a low temperature point, not too far from the quantum phase transition. So there's some correlations, but there's very little entanglement. And this is a point that actually you can do very well with tensor network methods. So I'm showing here results from MPS simulations that I can talk more about if you're interested in, up to bond dimension of a few thousand. And so we're going to use this basically as a benchmark to compare this zero noise extrapolation to well-controlled classical simulations. And then I'll go to some other point where the classical simulations have more trouble keeping up. Okay, so at this low temperature point, there's a few curves here. So purple is shown as like a extrapolation to no truncation with the MPS data. Blue is the experimental data for total magnetization versus number of Trotter steps with the kind of native noise level of the device. Green is artificially cranked up noise data. And using these zero noise extrapolation techniques that I just showed you, sorry, the purple dots are the zero noise extrapolated data, and they fall very close to this classical simulation line, which is the solid purple line. So it's showing you that even though you're doing a big rescaling to pull back the signal from the noise, it's actually working quite well. Okay, so now let's go to an intermediate temperature quench where the correlation length is still quite large, almost the system size for this 7x8 56 qubit simulation. And the entanglement is too large for the MPS methods to be reliable. So the way you can see that is, well, firstly, the truncation error is big. And if you extrapolate to large bond dimension, the extrapolation becomes very uncontrolled and gives you even like artificial like negative values, which are just totally unphysical. Yeah, and so the quantum data from the zero noise extrapolation shows some kind of transient oscillations that for short time when the MPS data is reliable kind of agree nicely, but then yeah, go beyond what these classical methods can do. So these data points were kind of exciting to get because we didn't know the answer. And we're like, okay, I mean, there's not a huge amount riding on the quantitative value of these points, but I think it's like one of the first data points you got from a digital quantum computer that you couldn't have said what its value was going to be ahead of time. Okay, so this was just showing one classical method, MPS simulations. You might think for a two-dimensional system that you could do better by taking a more natively two-dimensional tensor network ansatz. So we also worked with researchers both at Quantinuum and Garnet Chen's group at Caltech to really push on PEP simulations of the same thing. We also looked at a few different methods that were used to kind of overturn this IBM Ising model quantum supremacy claim, like sparse polydynamics and neural quantum states, which I won't talk too much about. But you can see that all these different blue curves, which are the classical methods, the kind of truncation and approximation errors blow up after 8 or so Trotter steps, well shy of what we can get from the quantum data. So I won't, all these devices were done on kind of state-of-the-art hardware, but relatively small, like few node calculations. So I won't claim that if you really pushed on like the biggest supercomputers for a long time that you couldn't reproduce the data up here. But I think we're starting to really push on the edge of doing beyond classical calculations with a quantum computer. Okay, how am I doing on time?
10 minutes.
Oh, perfect. Yeah, okay, maybe it won't take that long. Okay, so I want to talk about a second experiment we did, which is maybe not in this quantum supremacy regime, but the quantum advantage regime, but where we can see some slightly more interesting physics than just the local equilibration of total magnetization. And one of the key features you'd expect if you have a time step that's small enough to see a prethermal plateau is that you have an emergent energy conservation, at least until you hit this flow K heating regime at late times, and you realize that energy is not actually conserved. And so if you have an emergent energy conservation, there should also be emergent hydrodynamics and diffusion of things that have overlap with your energy density. So to probe this, we wanted to take a different geometry. Instead of a square geometry, we took an elongated 14×4 geometry just to give things space to spread out and to actually observe diffusion quantitatively. And everywhere in this blue region, we took the initial product state with the intermediate temperature quench, the things that I was just showing on the last slide. And in the middle, we just put a domain wall or a domain of downspins to basically make a stripe of like hot high energy states here. And then you can measure the exchange contribution to the energy, which I'll call epsilon, which is just like the sum of the ZZ interactions on the average over the neighboring sites for each site. And you'd expect in an energy conserving system that this would diffuse. So if you look at the Fourier components along here, they should decay, and their decay rate should go as the wave vector squared in diffusion. So here's a picture of the experiment for increasing number of time steps. You can see this energy density kind of spread out. And if you fit the decay rates of the different Fourier components along the x direction, you can actually see that they obey within error bars kind of nice diffusive relationship. So you can actually measure in this example the energy diffusion constant of this many body system of 50 sites in this setup, which is not surprising, but it's encouraging, I think, to see this data on a visual device. Yeah.
I missed it. What's the defect you put in? You put in just
so everywhere else is kind of this intermediate temperature thing that's kind of close to the mean fields value, a little bit off to make it classically harder. And then you just put a stripe of just purely down spins. I mean, you could do all kinds of things.
But you pin it or something.
Yeah. Okay, so what I've been talking about are experiments that I think are if you look hard enough in the phase diagram, you can find regimes where classical methods are really struggling to keep up, and we're kind of poking our heads out into this quantum advantage regime for problems that maybe don't excite this audience yet, but are kind of in the right vein to start tackling problems in like frustrated magnetism or other kind of topics that are more exciting. I think with these, the plans for this year are to come out with a similar device with 100 qubits and lower gate errors, and should have like a bunch of bells and whistles that make it better, where I think we'll be like clearly deep in this quantum advantage regime, where we'll be able to do stuff that just classical methods, even the largest supercomputers, have no hope of keeping up. And I think it'd be very interesting to start looking at more complicated models, things with possible like spin liquid ground states or interesting quantum criticality, and if we're ambitious, maybe even going beyond spin models to look at like interacting fermion systems. And I think another interesting target will be to start slowly incorporating active error correction into these simulations so that we can keep beating down the noise and get into longer and longer times, hopefully without needing to go all the way to a fully fault tolerant error corrected quantum computer to start leveraging error correction partially. Okay, so yeah, I think with this, I'm done with what I wanted to say, but except to thank again this large team of collaborators, without which none of this would have been possible, and thank you also for your attention.
I have a question on like the architecture. So when you add more qubits in this setup as opposed to the linear setup, less noise, is that correct? Can you comment on that, or is that so you can't comment on, or?
No, I can comment. So we're actually switching qubit types from ytterbium to barium, and we're also like pushing on all kinds of technical noise. So it's not obvious that scaling up would make things less noisy. Usually it doesn't go that way.
Right.
With this kind of shuttling architecture, there's no intrinsic coupling between scaling and noise rates, because you can just basically keep the ions far enough apart that there's almost no crosstalk.
I see.
So as long as you can just put more lasers in and keep everything working at larger scale, there's no intrinsic increase in like.
So the actual quantum computer will get bigger. When you get to like 1,000 qubits, it would be a much bigger setting, or no?
Yeah, so I think, okay, maybe I can put the picture back up. This next iteration will still be slightly 1D, although there'll be a junction where ions can like swap through the junction. And so in this new setup, the ions will never like swap past each other. They'll just go around the ring and resort through this junction. And I think going past this, you'd want to make like two-dimensional grids of these junctions, so that you're really using like a two-dimensional kind of grid architecture. And that we've demonstrated, well, experimentalists have demonstrated transport through junctions and pieces of this. So now we're just putting it together, basically.
Be a devil's advocate.
Sure.
Did you try to calculate what happens if you have 56 large spin classical spins?
Oh, interesting.
Right? Landau-Lifshitz Gilbert equations.
Yeah. We didn't try that. Yeah, I'd be curious to see.
So you can easily simulate it with your laptop, of course, right?
Sure. Yeah.
And at least in our experience, results are extremely similar.
Interesting.
So you would be hard pressed to distinguish between quantums and classical.
Mm-hmm. Yeah, I sort of suspect you wouldn't really quantitatively get these like transient approach to the equilibrium quantitatively accurately. Things like this hydrodynamic diffusion constant, probably if you have adjustable parameters, you can definitely hit it.
But it would be interesting to compare if you can say this is quantum, not classical.
Yeah, I mean, yeah, if you want to talk more about that, it'd be interesting.
Sure.
Yeah.
I think Central had his hand up.
Yeah, so given that you can, with these qubits, more or less take any unitaries that you want, can you just make the unitaries be randomly dependent on the bond?
Sure.
So then the dynamics is that of a randomizing model, right?
Yeah.
Then in all the regimes you're talking, whether it's close to the classical transition or close to the quantum transition, so there'll be Griffith's effects in the dynamics which slow things down dramatically.
So that is in principle possible. The rub would be that you probably need to go to relatively late times to see those effects.
Depends on the strength of the result.
Yeah.
That's a place where classical simulation will definitely stay. So I don't know how well you can.
Yeah, that'd be super interesting. Yeah, okay, I'm curious. And you could also like plant Griffith's regions and explore their dynamics and things like that. Yeah. Yeah. Okay.
So don't comment again the comparison between classical simulation and the quantum simulation. Because I think since we only require about 20 Trevor step, and everything is hard to do this on classical computer. What's the comparison you talked about?
Oh, sorry, can you maybe repeat the question? I'm not sure I got it.
What's your comments? How do you compare the classical simulation and quantum simulation for this problem when we only require about 20 Trevor step?
What do you mean? How do we so we basically try to calculate the same thing with these different methods, you know, push them as hard as you can.
But are you saying is this a hard problem for a classical computer, or?
Yeah, it's definitely a hard problem. I mean, there's always a question of whether like exactly at this scale, you're beating the best supercomputer with the best technique. I think, yeah, we've given some evidence that it's pretty hard to go beyond like 8 Trotter steps for these parameters.
How large is the system again?
It's 7 by 8.
7 by 8, and yeah, maybe because I'm not familiar with the classical simulation for this problem, but it just looks like 10 Trotter step, maybe 50 size is not.
20 Trotter steps, right? So 10 is kind of just on the edge of doable for classical method.
Okay.
Yeah. But this is dynamics, right? It's not like ground state where you can use Langshos or some kind of very simple thing, right? Yeah, so actually on this plot, I forgot to mention it. This dashed line is what you would get if you took, you know, a reason like a Floquet-Magnus expansion approximation to what the Floquet-Hamiltonian is, and computed the thermal equilibrium properties. And you can see that there's kind of, you know, there's still some transient oscillations. It hasn't quite thermalized. So I think it's those oscillations that will be hard to capture. The dynamics on top of like the dynamical approach to equilibrium. The equilibrium itself is not hard to capture for this parameter range. Yeah.
In these simulations, you're in a regime which is hard in one way and easy in another, right? There's this well-known thing that at very long times or very high temperatures, it's more or less classical. Very short times, it's very quantum, but we have good methods for that. In the middle, it's hard.
Yeah.
So that's where you are. Can you say anything more about the amount of classical versus quantum correlations you have in the state? Because a lot of these quantum methods are really geared towards the very quantum side. And even if there's a lot of spurious classical calculations, they can't deal with them.
Yeah, no, I was thinking about exactly this when I was putting these slides together like an hour ago. Yeah, I don't have to say about it, but I actually am kind of curious to go back and try to measure some like mutual information or like, yeah, maybe some more like something that's like entanglement negativity, something like that, and maybe an ED and C. But yeah, we haven't done any of that. I think that's a really good point. Yeah, Ruben.
Yeah, very cool stuff. Thanks. So you already kind of hinted at error correction. I have a kind of vague question, so you can take it anyway. But is there any perturbative way of including error correction, or do you immediately have to go to logical qubits and all the overhead, or is there any intermediate thing you can imagine?
Yeah, there's definitely intermediate steps you could imagine. One is like you can use error detection without active error correction. Yeah, and then you could either try to post-select or use something like the zero error extrapolation kind of technique to try to clean up the data. There are also like schemes that have been proposed for like partial fault tolerance, where you use active error correction, but you use non-fault tolerant ways of injecting like non-Clifford operations that still for like small angle gates have some error suppression. Yeah, so I think it's really interesting to ask like, what can we do without, you know, devoting 90% of our computer to producing magic states and having 1 million qubits.
So for the hydrodynamics, you could also construct a circuit that's explicitly say U1 conserving, and I guess benchmark that against known results for say random U1 circuits and diffusion constants. Has that been done or?
It has not. Yeah, I think random is, it's not fundamentally hard, but averaging over lots of stuff is expensive time-wise. Like the downside of getting like very clean gates and high connectivity is that the clock rate is a bit slow. You actually need to shuttle the ions around. You need to recool them before you do. The gates, since the motional modes are involved in the entangling operations. And so, yeah, you tend to have to like be a little bit picky with what data you actually take to, so like averaging over like 1 million random circuits would not be feasible, for example. But yeah, I think, I mean, I don't know, you don't need to like look at random circuits to benchmark you. Yeah, I think there's a lot of examples where we have like benchmarking against exact results, like for like dual unitary circuits, things like that. So I think we're kind of confident that, I don't know, that is like less the focus, I think, than trying to like push into like interesting non-simulable regimes.
Maybe, can you comment, because another thing that I don't know very much about the classical simulation frontiers, but another thing that I think is maybe not so easy to simulate is if you're interested in a Hamiltonian that changes in time. So, you know, either that I have some local, you know, I take one bond and I'm sort of driving it, or just, you know, maybe I want to like look at a ramp across a phase transition or something like that. Is that something you guys have thought about? And can you comment? Because, you know, obviously, like we are used to thinking of those as a continuous change of the Hamiltonian, and you have to do a Trotter expansion. I have no idea how those two kind of play.
I mean, there's like an obvious way of like approximately doing what you're doing with like piecewise continuous.
Yes.
Or piecewise constant Hamiltonians applied in a sequence. Yeah, you could do that.
But if I sort of wanted to go across a phase transition. Again,
yeah, so okay, so
it seems like it might be quite different from a slow ramp.
So one thing with like getting close to a phase transition is that here I paid no attention to this initial state preparation. And if you want to describe a critical state, that becomes like a much bigger part of the, or near critical state of the circuit depth that you're using. And there aren't really great all-purpose ways of preparing approximate ground states non-variationally. I mean, you could do adiabatic things or quasi-adiabatic things. You could also try to just simulate like cooling with a bath, things like that. Or you could just throw a Hail Mary and throw as many variational parameters at your wave function as you can stomach. So I think those are the best options that we can do without like a error-corrected quantum computer. Yeah, so I think that's exactly when we have like a bit more qubits and a bit more circuit depth to work with on these next generation systems. I think actually like preparing highly entangled like near ground states and looking at dynamics closer to ground state physics with like long correlation lengths would be really exciting.
Last question.
Technical question for you, but when you're comparing like the earlier comparison with matrix product state simulations, David Frank here, like how accurate is the wave function classically? It's probably very accurate. When you say chi is 4,000, it's like, you know, the truncation error in the MPS is probably, is it 10 to the minus 16 or I guess the question that like people are asking at CCQ is like, what if you just let chi be small, but you know.
Oh, that's what we do actually.
That's what you're doing? Okay, that's
well, that's what the folks at Fermionic
yeah, that's what they're doing. Okay.
It's more like a variational time evolution at fixed bond dimension.
Oh, so it's a TV.
Where it's something like, it's kind of like DMRG minimization of your overlap between your wave function at one time step, the time evolution operator, and the wave function at the next time step.
Okay.
And actually the extrapolation is done by trying to extrapolate to like perfect fidelity rather than zero bond dimension. It tends to be a little bit, anyway, I can show you some more details if you want.
Interesting. Okay.
Yeah.
Okay, let's thank you again, and have a 30-minute coffee break, and we'll come back. Go on.
I just we're sure you do it. There we go.
For a while, that's
We're like finishing. Yeah, you're finishing up. Right. Yeah.
it's like her.
Rather, probably going.
You'll find that you might say that. Yeah.
Every
So the-
single thing.
That it should like not argue very hard. It's can't even report its measure.
Yes, probably other people. I don't know any, but I don't know if the other probably saw that program.
Guys using the Symmetry program?
Technology program, also for giving.
Okay, I'm gonna try to do my best here to get the afternoon session started on time. So, our next talk is by Ruben Verresen of the University of Chicago, and he's going to tell us about symmetry-protected triviality. And criticality, okay. You know, Hubbard quantum.
Yeah, hi everyone. I want to start by thanking Fiona and part of this talks for the invitation and for organizing the workshop. So indeed, I'll stick to the theme. So I will discuss certain topological features, although I might stretch what you're willing to call topological, but I'll try to convince you. And also the quantum platform though, that we'll be exploring within is a pretty cool device in the Graphene lab at Harvard. So it'll be a full atom-based experiment. So since we'll be talking about topological phases, maybe the initial starting point is what do we even mean by topological phases, because the term is used pretty broadly. And maybe one of the most inclusive ways of thinking about topological states is space of matter that you cannot diagnose locally. Right? So in contrast to conventional states, where by looking locally, you can tell whether there should be a phase transition, right? Like ice and water, liquid water are locally distinguishable, and hence corresponding to the necessary phase transition. In contrast, liquid water and gas are not really locally distinguishable, and correspondingly, you can actually avoid the phase transition. So that kind of all matches up. They're locally identifiable. And topological phase of matter are all about going beyond that. Right? So we can't just rely on local properties, like in this conventional. So topological phase of matter does require, if to the extent they allow for order parameters, they should be non-local. And the simplest setting to explore this kind of physics is already in one dimension, in ground states of certain quantum systems. And here I'm reviewing two of the most basic ones and also one of the most studied examples, tracing back to the 70s and 80s. Kind of similar in spirit, right? So one is polyacetylene, or known in our community more as the SSH chain or simplification of polyacetylene, where basically you might know it refers to the fact that some quantum chain might have two different types of bond alternations in some effective hopping model. And even though both systems look incredibly simple, and they are in some sense, turns out there's a topological distinction between the two. Okay, so even though there's no reliable local order parameter, there's some distinction between these phases of matter, and they cannot be adiabatically connected to each other as long as you preserve certain symmetries of the system. And it maybe sounds a bit funny that there's no local way of distinguishing them, because I'm showing them on the slide and you can kind of see which is which. But the precise statement is, if you perturb from either of these fine-tuned points into a more extended quantum phase, and I give you one of the wave functions, there's no local probe that can reliably tell you whether you're connected to this one or this one. Okay? But instead, non-local order parameters can tell you. Pretty well-studied example. There's also another one-dimensional example arising in the spin-on-Heisenberg chain. This phase of matter is sometimes called the Haldane insulator, because Haldane was one of the first to appreciate and point out that actually it's a pretty interesting gapped quantum phase of matter. And again, so one can add some tuning parameter, for example, in spin-1 chain, so-called single ion anisotropy. We can kind of see on site that this parameter will be very large and positive. The ground state likes to be in this kind of boring product state of the SZ equals 0 state. But it turns out that although both states are quantum paramagnets, no local order parameter, no symmetry breaking, there's some topological distinction between the two. And hence, accordingly, there's some phase transition that's separated. They're not adiabatically connected. Again, no local order parameter has been pointed out quite a while back that there's some non-local order parameter that can tell you which of the two phases of matter you're in. Okay, and so both of these examples are now understood in a more general framework of what is called SPT order, or symmetry-protected topological order. Right? So how mouthful, so I'll just always refer to the acronym SPT. And just maybe one abstract slide, just to get the details out of the way.
when people talk about SPTs, what they're imagining is we're looking at ground states of local Hamiltonians, and we basically want to ask for unique ground states. So kind of a simple setting, those spontaneous symmetry rating, for example. At least unique ground state on periodic boundary conditions, so ignoring boundary issues, right? And once you're in that realm of local Hamiltonians with unique ground states, moreover, we ask for an energy gap of the ground state, which is usually associated with some stability properties. Then in that landscape of such Hamiltonians, we can talk about SPTs. Okay, so if you give me two Hamiltonians, if they have some symmetry, that symmetry might depend on the problem of interest, might be some spin rotation symmetry or whatever. We say two symmetric Hamiltonians are in distinct symmetry-protected topological order if the following two properties hold. Okay, but if someone ignores the symmetry or doesn't care to keep track of the symmetry, then the two Hamiltonians are adiabatically constitutive. But if you enforce the symmetry, for maybe various physical reasons, it no longer becomes possible to adiabatically commit. Right? Which means as long as you preserve the symmetry, there must be a quantum phase transition or perhaps intermediate phase. So that's kind of the general definition of SPTs. In some sense, the simplest type of topological phases that are known. And so even though they're very simple representatives, one can learn a lot by studying these in detail. And some of these insights then can extend to more powerful cases, like intrinsic topological. All right, so for example, what we saw in the previous slide fits that general framework. Again, here we have this spin one chain with some tunable parameter. I already told you there's some phase transition between these two different regimes. And in fact, one can prove that there's not an accidental transition. For example, as long as you preserve spin rotation symmetry, like this Hamiltonian has, this phase transition cannot be avoided. These are really distinct SPT phases. Okay, but if you were to ignore various types of symmetries, like spin rotation symmetry, then it becomes possible to kind of fit in this definition. And one can prove various things from this definition, which I won't do in this talk. For example, it can be shown that if you have such two distinct phases, a local order parameter can never tell you which phase you're in, but certain non-local order parameters can. And moreover, since symmetries are key, turns out that the symmetry is moreover internal, like spin rotation symmetry. You get various other physical properties for free. The phase has to have certain interesting entanglement properties, or also you might have heard that in presence of boundaries, there's certain zero energy edge modes. At the same time, we should emphasize that that second property really is more circumstantial. It depends if you have internal symmetries. If you have certain crystalline or external symmetries, then these properties do not automatically work. And as we'll also see that in the course of this presentation. Okay, so kind of the general lay of the land of SPTs. And one can ask to what extent can we realize and explore these types of simple topological states. And in this talk, I won't explore solid state approaches, but rather these kind of engineered quantum platforms. And there have been various interesting works over the past few years. There's a whole slew of works on digital simulation of SPTs, which is not what I'll be talking about, but just to mention what it is. But as you saw also in Drew's talk, in digital platforms, one kind of use, say, unitary gates to build wave functions. And then one can build a wave function defining certain SPT states and explore entanglement properties, etc. So there's a whole series of work that I'm not exhaustively citing here. Instead, in this talk, I want to explore analog quantum simulation, if you wish. I think the word simulation is a bit of a misnomer because the system really will be interacting and we really will be exploring low energy physics of these systems. And so these analog quantum simulators, one is able to engineer Hamiltonians to a great degree, not arbitrarily, but to a great degree. And one tries to create the low energy states of these Hamiltonians. And an advantage compared to solid state systems is that you can often access a lot more information. You can really just take snapshots of the whole wave function and reveal certain topological information that's usually inaccessible with local probes in solid state experiments. And there have been a variety of works, maybe just to highlight two from the Bryce lab in Paris, which is kind of a Rydberg and Treacer array-based lab, for those of you familiar. There, they essentially created kind of a bosonic version of polyacetylene or the SSH model with two different staggerings. And they were able to explore the SPT properties. And also in the Bloch lab, which is more ultra-cold fermions and optical lattice, they were able to explore some version of this Haldane topological phase of matter like the spin 1 Heisenberg. Although, just as a caveat, they explored it there in effect a spin 1/2, bundle Princeton spin 1/2. Okay, so the main takeaway from this slide is that these SPTs can be explored in these engineered quantum platforms. And so we could try to see what kind of interesting physics we can tease out of them. But at the same time, it's also useful to mention that all these previous examples are more about creating particular points in the phase diagram. For example, here in this experiment, they created the two different staggerings of the SSH chain. But one can ask, can we explore this in a tunable way? Can we have a tunable Hamiltonian in these systems? So we don't just create, say, deep in one of the SPT phases, but we can really tune across the phase transition. Because arguably, the quantum phase transition is one of the most interesting parts of SPTs, right? SPTs are almost defined by the fact that there has to be a phase transition somewhere in the phase diagram. That's unavoidable. So it'd be interesting if we can explore that, especially in these tunable platforms where you can maybe eventually down the road extract some universal data from those TFTs that can form field theory at the critical point. And also these quantum critical points can have quite drastic physical effects. Like, even though they appear at fine-tuned points in the phase diagram by their very nature, they can have some effects that high temperature. And so once we'll be able to explore these phase transitions, one can also explore certain consequences arising from it. So one very curious property of these symmetry-protected topological states is that they have a certain stacking property. Kind of a funny more is less kind of thing. This is very different from conventional phases. If I have a symmetry-breaking phase of matter and I stack it with the same copy of the symmetry-breaking phase of matter, and I maybe allow for some generic symmetry-observing couplings, the symmetry-breaking phase doesn't disappear, right? There will still be a phase transition. But this is not true for these topological states, or at least these types of topological states. You can have two of these like Haldane insulators, and you stack them, and you allow for symmetric couplings, and suddenly the distinction between topological phases can disappear, and the phase transition can be gapped out. It's a very subtle, interesting property of these SPT phases, which has played an important role in the theory literature, because it's a crucial tool to classifying all possible types of topological states. The fact you can add and subtract phases from each other. Interesting to see that once we can create a kind of these phase transitions between topological states, we can also check that the phase transition disappears if we stack. And another aspect that would be interesting to look into, that in the past few years, there's been an increasing interest in generalizing phases of matter beyond pure states, right? If we're thinking of ground states of many body systems, those are in principle pure or wave functions. But especially motivated by these kind of tunable quantum platforms, we have to come to terms with the fact that these systems are not pure. They'll be mixed generically. And how do we generalize our notions of phase of matter to these more generic mixed states? In some sense, of course, solid state did that many decades ago. Gibbs states are exactly that. But that's kind of a very fine-tuned notion of mixed states. And we should think a bit more broadly if we have noisy devices. And again, once you can explore this physics, you could try to see what about some mixed state effects you could explore. So that's kind of both some challenges, and I'll also, in a sense, as you can probably guess, certain outline of the type of topics I'll try to touch on for the remainder of this talk. To also then make things a bit more concrete, the platform we use to explore these kind of concepts is an optical lattice-based platform developed by the Graphene lab at Harvard. In particular, I want to highlight Lin Su, who's the leading grad student who has been pioneering this experiment, who currently recently also moved to a postdoc position in Columbia. And perhaps most of you are familiar with the idea of optical lattices, but very briefly. So basically, it's a lattice formed by light, and atoms are effectively trapped in these wells, just like you're used to in solid state, and they can hop around. So we have an effective closed Hubbard model in this case. We'll have bosonic atoms. So we're hopping between these lattice sites. We have an on-site Hubbard interaction, which penalizes if there's more than one boson per site. We will not work in the hardcore boson limit, so we'll also see double-ons, basically 2 bosons per site. And what is very interesting in this new platform, so far this first line has been explored, it's still very interesting, but it has been explored before in other platforms as well. But what is lesser explored is the fact that if you use magnetic atoms, then you also get strong off-site interactions. Sorry, the plus is over here. You get strong off-site interactions in addition to the on-site interactions, which enables new types of physics to be explored. And finally, maybe more of the detail at this point, is we found it also useful to add some explicit staggering. The reason for that will become clear in a minute. Okay, and what's also very nice in this platform is that they can directly resolve the number of atoms. So the way you should think about it, in each run of their experiment, they try to prepare some low energy, ideally the ground state, or some low energy state in this interacting model. and then they can take snapshots of a wave function, do it many times to get statistics. But in each snapshots, you can see, for example, this site has 2 atoms, 1, 2, 0, which is basically obtained by counting the number of photons emitted, and then they've characterized the fidelity with which they can kind of recognize occupation. Okay. Good. So that's kind of the platform we want to use to explore this kind of topological phase of matter and their criticality and related properties. That's the setup. Let me know if there are any questions already at this point. Okay, so what's the reason we were excited to use this particular kind of Bose-Hubbard model to explore topological physics? And I should mention, if it's not already clear, we're going to be exploring this in a one-dimensional setup. They have already experiments in 2D as well, studying certain symmetry-breaking states. And eventually, also interested to explore these kind of more topological states in 2D. But in this talk, I'll stick to 1D. So one reason to be interested, or one reason we got interested at least, is actually quite an old theory prediction from almost 20 years ago by Dallatore, Erzberg, and Altman, which exactly took this Bose-Hubbard Hamiltonian with both on-site Hubbard and off-site kind of the polar interaction, and they explored a phase diagram using DMRG, and they found that there's a few conventional phases of matter that you can easily expect. Let me discuss those first. So if the on-site Hubbard interaction is dominant and you have a filling of 1 boson per site on average, then as most solid state physicists are used to, right, for large U, you get a mod insulator, so in gap phase of matter. Whereas if V dominates, then they don't like to be too close to each other. And then maybe you can believe that if V dominates, you get actually a spontaneous symmetry breaking of translation symmetry, where particles form doublons and then empty sites, doublons and empty sites. And since it's a kind of spontaneous choice, you have twofold ground state adjacency in this density wave case. So far, nothing surprising. More interesting is that they found that in the intermediate regime, where both are kind of equally important, they get the Haldane insulator. This is the same phase of matter that was pointed out in the 80s in the spin-1 Heisenberg chain. And it turns out to arise in this Hamiltonian, which is maybe not too crazy if you think about kind of a spin-1 encoding, right? If you're in the regime where each well has either 0 particles, 1, or a doublon, you kind of get a 3-level system, and you can imagine labeling them as a spin-1. And they indeed find that the ground state in this regime is morally that of a spin-1 Heisenberg chain. Okay, and they also identify the symmetries of this Hamiltonian that protect this topological phase of matter. Since then, there have been various extensions, kind of finer resolution of this phase diagram, but these core predictions have survived.
I think I missed it. Why can't you have 3 bosons per site?
Well, you could. We're just energetically exploring the regime where that's not the physics, but yeah, you couldn't definitely.
What are the symmetries like particle hole and
Yeah, that's a good question. So from the Haldane, like the spin-1 chain, particle hole seems pretty natural, kind of spin flip symmetry. Yeah. Here that's less natural, right? Yeah. It's not really. So indeed, the more precise, robust symmetry is the bond-centered inversion. Which protects the Haldane phase as well. Then you could ask, well, the crystalline symmetry, how stable is that? And I'll actually discuss that, the effects of disorder, in a few slides. Okay, but again, this was kind of the guiding ideas that was out there. We're wondering, okay, can we explore the Haldane insulator, and I can spin 1 language, and I can not just the phase, but ideally the phase position and see these cool features. Okay, that's where we started with this project. So I'm kind of giving a bit of a chronological take here, and not to go too much into the weeds, but it's known that in principle these 2 different phases. So here I'm doing a vertical cut. Is the Haldane insulator and the mod insulator, even though they're both again paramagnetic at short distances, no local parameter. It's known that you can distinguish them with certain string order parameters. In the interest of time, I may not dwell too much. These are pretty well known, and I'm happy to discuss in more detail, but there's some subtle string order you could use to distinguish them. So that's what we tried in the experiment, and okay, here's the data. So in principle, this should be non-zero and then dip to 0. Once you, so you see this, the orange one is say the string order that should detect a topological phase, which should appear here for small u. So ideally, this should be non-zero and then dip down universally to a 0. And then stay 0 in the mod phase, and opposite for the Kuga. Okay, with a mother's eye, you can say, okay, maybe it's a hint of that, but okay, I'll also be honest, we were not super encouraged that this was what we got. So we can see hints of it, but it's not very satisfying. And we understand the reason if you do DMRG simulations, which is easy enough in these systems. even quote unquote deep in the Haldane insulator, the correlation length is easily 20 sites. Okay, that's kind of the order of the system size we can do. So it's hard to explore this kind of true invariance of phases of matter. So if already the phases of matter have this large correlation length, and we're trying to see transitions between them, you're gonna see that's not ideal. Okay, so we had to kind of think a bit, how can we try to isolate this interesting transition? For example, here, this solid line is known to be pretty interesting, compact boson CFT or Luttinger liquid, however you like to call it. How can we isolate the physics of that, but potentially making the nearby phases simpler so we can have better state preparation? Okay, so that's that.
How strong was V on this plot? Is that always fixed?
That's a great question. Just like Drew was making slides a few minutes ago, and I didn't have time to check V, but I could get back to you. But it's somewhere generic, like it's order of 3. But I just don't have the number there on this.
Ruben? Yeah. So having the long correlation length, isn't that ideal to look at the critical properties? Just try to look at length scales smaller than that.
Yeah, I mean, it's not unreasonable, but at the same time, okay, that's kind of the way I think when it's kind of smearing things out. So there's both the density wave, Haldane insulator, monoinsulator.
So you don't see the other phases, but you only have access to the critical point.
But then which critical one? Because the critical line here and the critical line here. So here is a compact boson CFT, here's an Ising CFT. Or maybe here.
The difference, yeah.
So kind of, I mean, I agree still could be interesting, but things get a bit fuzzy, then it becomes less clear what it's trying to zoom in on. Good question. Good. And maybe the also realistic answer is, once things become so fuzzy, it becomes hard to argue, is it because it's a quantum critical state or just because it's a mess, right? And it'd be nice, you want kind of a lower entropy experiment where things are 0 and 1 regimes, so you know things are working as you think they are. At the same time, our simulations here confirm we understand it roughly. So,
can you do periodic boundary conditions to see quantized string correlations, or in the experiment, is it always open boundaries?
Yeah, in this platform, it'd be, I mean, in principle, they can do 2D geometries, but for optical lattices, I think it's hard to do ring geometries, and tweezers that's more natural and has been done. So you should let me know if I specifically reasonable. Okay, good. So that's kind of, we're trying to simplify the nearby phase, but keep the criticality the same. And one way of doing it is by adding explicit chemical potential staggering. That's what this term is. We're adding a new term that they can implement in the experiment using something called an accordion lattice, but let me put the technical details aside. Okay, so what's happening? So maybe let's guide ourselves. First, I mentioned this term was not there. Then I have this phase diagram here in the dipolar V and onside Hubbard U axis. And this is a phase diagram we saw before. The mod phase, the Haldane, and the density wave. Okay, so that phase diagram I predicted before, 2 decades ago. And now we're going in this direction by turning on this term. And what do we see? Well, the mod phase is not too affected. It's some gapped phase, maybe gets slightly balanced, but roughly even, as you turn on this appreciably, there's some mod phase that still looks the same sketch form. But what happens over here? Well, the density wave, again, is kind of simple as well. The density wave used to have a spontaneous symmetry breaking of double on, hole. And one of these two now becomes the ground state, the other gets lifted up. So we kind of get this pinned density wave. There's a unique ground state over here. And interestingly, the Haldane phase of matter becomes also the same phase of matter. So this red line, this bottom red line, which actually used to be an Ising phase transition between Haldane and Chern wave, disappears, which makes sense. Symmetry breaking phase transition should disappear if you explicitly break the symmetry. How to get some intuition for why the Haldane phase adiabatically extends? Well, I made a little animation here. So, okay, what is this? One way to think about the Haldane insulator, it's very similar to the SSH chain. Think of each boson as kind of being in superposition of the well on the left and the right. Okay? And now what would happen if you turn on this imbalance? Well, they just kind of get slightly shifted over. And because this imbalance is staggering, you kind of pour 2 particles into one well and hold one gap. So let me do it again. So this is when μs is 0, and now I'm going to turn on this staggering. It will be clearer if I'd done more effort and changed the potential well, but this becomes deeper, this becomes shallower, so particles like to sit together. And that's kind of what happens as I tune away into this plane and it becomes this phase. kind of smooth changeover. Again, numeric shows us. I just wanted to give you some feeling.
Sorry, Ruben. So did you say that the Haldane phase goes away? So what happens to the edge states? They also get split, or?
Yeah. So exactly. So as you tune away from here, you break the symmetry that made it a non-trivial SPD phase from perspective of entanglement and edge modes. So in some sense, it becomes a product state. This little picture admits some kind of product state limit. If you go infinite deep staggering, you just get this product state picture. And also the mod phase, right? Obviously, this picture suggests there's some product state limit. What is maybe interesting, surprising, depending on your perspective, is that these are not the same product state limits. And in fact, you cannot adiabatically connect these two regimes. So in particular, these two regimes are in different SPT phases, not for an on-site symmetry, but for a crystalline symmetry. In particular, so whenever someone tells you something is in two distinct SPT phases, the question is, what is the symmetry? And the symmetries here are, on one hand, particle number conservation. Strictly speaking, only the parity, but the whole U1 particle number is conserved here. And site-centered inversion, which you can confirm is still a symmetry, even if you add diagram. And one can show that these two phases are in distinct crystalline SPT phases with respect to these symmetries. Intuitively, kind of at the site-centered inversion, it's like, are you having an odd or one particle or an even number of particles, like 0 and 2? Here. That include questions or?
You have 7 minutes including.
Okay, good, thanks. All right, so and also here to see that you cannot adiabatically transform them. If you were to try to naively transform one into the other, you would have to break site-centered inversion. So as long as you preserve that symmetry, you just cannot. This interestingly also been studied before theoretically. Kind of interestingly, they call it symmetry-protected trivial phases for obvious reasons, and they have a very similar spin-1 phase diagram. But what is perhaps interesting is that even though obviously, right, these two phases are not particularly interesting, I'm not going to tell you that. What is very interesting, well, pretty interesting, is that despite these phases looking very simple, the natural phase transition between them is exactly the same as the phase transition between the Haldane and the Martins. So it's a way of simplifying the surrounding phase diagram by preserving the nature of the criticality. Good. All right, let me just show you that we can see these different regimes in the experiment. And then we can also detect which phase we're in using a non-local string order parameter. Maybe, let me see. Well, let me briefly mention one non-local order parameter that distinguishes them is, as you can already see naturally in the picture here, if I look at, say, an odd number of sites, like 3, the number of particles here is odd, and the number of particles here is even. And that sign turns out to be a topological invariant. One can argue that more robustly, but let me just show you the experimental data. So here, now the y-axis is the tuning parameter. So for small μs, you're in this mod phase, which looks like this, 1 particle per site. So if you measure the parity per site, it's even. It's even if it's an even length site, and odd if it's an odd length site. So that's why it's kind of alternating. Whereas if you're in this kind of double on whole double on phase, the parity is always even. Okay, and here's where the predicted phase transition occurs, where kind of in between these two regimes. And one can kind of distill an order parameter from this, which is 0 in one phase and non-zero in the other. And in the interest of time, let me not dwell on the details, but you can imagine that by using this parity string order, you can define a respective string order for both phases. And again, as we tune from, say, the mod insulator to this kind of double and whole phase, one of the string orders is non-zero in the mod phase and dips to 0, and then it's kind of opposite for the other phase. So here we see a much clearer distinction between these two different phases. And here is where this predicted compact boson conformal field theory would arise. In this experiment, we're not able to extract universal exponent, but in principle, that sounds like a reasonable goal in future experiments. And one can contrast this with local order parameters. And again, as I tried to emphasize already throughout, there is no reliable way of locally probing which phase we're in. At best, it's going to look at some kind of crossover where things are non-zero generically everywhere, unlike these string orders. So in my remaining few minutes, so let me just recap what we've seen so far. Okay, we started off with this Haldane phase and the mod phase, and we kind of realized that by introducing staggering, we could simplify the phase diagram to try to isolate this topological criticality. And now we see it Let me just spend maybe 2 minutes just mentioning on maybe a minute on each for what kind of physics we can explore with these phase features. So the first thing I want to do is explore a stacking property. So as I mentioned before, from the classification of phases of matter, it's known that even though one of these chains, the Mott phase, is distinct from its other phase, if you stack both of them, they're actually now in the same phase of matter. That means the phase of matter should disappear. Okay, so we can see that now in the experiment, they can just literally do 2 chains, and we can couple them. In the interest of time, let me ignore the type of coupling. And here's the predicted phase diagram. So the y-axis is the coupling between the chains. So the chains are decoupled. Obviously, just copy-paste the physics on an individual chain. And as we tune between them, there's some gap closing. So the darker color is low gap. So here we're starting in one phase. We dynamically sweep through the phase transition, low energy point. We try to prepare the other phase. That's a bad idea in general. You get heating across the phase transition. You won't prepare a low energy state. And then we want to compare to that. What if we turn on the coupling? That's still symmetry preserving. So it's not that we're breaking the symmetry of these SPTs, but still the classification tells us the gap should open. So we can take naively a longer path. So that sounds worse, but the gap will be better. So you can see that in principle there's a finite gap now. I can tune between these 2 different regimes. And what we hope to see is a better state preparation. That's kind of a figure of merit, right? If we're not sweeping through the phase transition, there should be less heating. We skip that. In the interest of time, maybe I'll just guide your eyes to this plot. Here is kind of some fitted effective temperatures here, right? So if the coupling is very small, right, basically the physics of decoupled chains, we see some high, quote unquote, high temperature after sweeping through this because we swept through a phase transition. Whereas if we do it with this coupling, we take this longer path, but it's gapped. And even though we see at the same rate, so naively it's worse because you're doing bigger parameter change in a short time, we do see a decreased temperature, which means it's consistent with the fact that now there's no gap. Of course, numerically, we can also just check if the gap is there, but it's kind of a physical concept. And the last thing I just want to mention is what if your crystalline symmetry is not perfect? You have some disorder in your system, which is pretty reasonable to expect, right? Crystalline symmetries are pretty fine-tuned. And we can enhance that in the experiment, similar to Drew's talk, where you inject more non-ideality and see how bad things get. And so we can programmably put in disorder in our system, which breaks the protecting symmetry. And we can see the experiment looks like a complete mess. So if you don't have time to do that, don't worry. The point is the same thing that before nicely gave like a non-zero parameter, just like a complete scramble, which makes sense. We've broken the symmetry. There's no longer distinct phase. But the nice thing is we can do this many times. We get a whole distribution over different disorder ensembles. And the ensemble looks like a mess. But if we average over the ensemble, we now get an average crystalline symmetry. And now the string orders reemerge. So we get a non-zero string order here. This is due to some experimental facts. The theory simulations give us a nice 0 order parameter for the other one. And the main point is that if you think of this ensemble as giving a mixed state, like an ensemble state is no longer pure, that mixed state of phase of matter still now a crystalline SPT phase with an average crystalline symmetry. Just kind of maybe a baby case example of mixed state order. Okay, I think I'm out of time. So there's some fun questions one could explore. In particular, one could explore whether the stacking property can be used in practice to do better state preparation. Here we're using it as a way of detecting that the gap has opened, but you can imagine maybe it's a good way in general to explore, to tune across a phase transition if otherwise limited. And also, of course, interesting to further explore this kind of critical process. Okay, let me stop here. Thank you for your time.
Questions yet? Beautiful results. I remember from the 1D SSH that the distinction between the topological and non-topological phase of matter where the edge-to-edge entanglement was present in one and not the other. I don't know, with this experiment, I assume that there are well-defined boundary conditions on the edge of the change. Are there analogous microscopic readouts about, for instance, CZ and XX correlations that can say something about the edge-to-edge entanglement?
Yeah, no, it's good. Right, it's good to ask about the edge physics. So in the course of the experiment, they actually were able to put in pretty hard walls. And initially for the Haldane phase, we're trying to see the edge modes. Then we kind of gave up on that because the correlation length was so large. And then once we introduced the staggering, even though the different regimes stay distinct topological phases, the edge modes are no longer there. So it's true that for some of these phases like SSH, the topology also protects edge modes. That is not always true. And if you have crystalline symmetries, they do not need to protect edge modes. So then there's no more edge mode entanglement to look.
Maybe I'll ask a follow-up question later.
Just to clarify, so the Haldane phase had the spatial inversion and another symmetry, and that symmetry is the one that you're breaking, explicitly breaking.
Oh, yeah, thanks for the question. So the Haldane phase is topological in the usual sense with like protected entanglement and protected entanglement with bond-centered inversion. But our staggering breaks that, but it keeps site-centered inversion. Site-centered inversion, it doesn't affect the entanglement of the Haldane phase, but it still protects the distinction between the Haldane phase and the modern state. So the upshot is there's two different inversion symmetries, and one is being broken by perturbation, but the other one is not, and that's enough to distinguish.
So what if you broke the other, like?
Oh, then the phase vision would go away.
I see.
In some sense, that's what we do in this disorder experiment. We could have done this more systematically in a clean system and just break site-centered inversion. But at least it's consistent that I just do, here we just have complete disordered lattice, so there's no crystalline symmetries, and we don't see any signature of a phase transition. But in principle, that doesn't need disorder. So we could have done a clean version of that. Could have been interesting. We didn't.
Right. Are the critical properties understood for the 2D version of this?
Great question. Yeah, it'd be fun to think about the 2D case. I'm not aware of any works, and I haven't spent much time on it, but it'd be fun to think.
It's not obviously some standard universality class. Just
I really haven't thought about it. Okay. Yeah, we have to check them.
Are these phase diagrams like schematic or?
Yeah, this is schematic. We do have exact numerical.
There's some like super solid that could happen in these.
The
super fluid phase. That,
super fluid is kind of hidden there behind the plane.
Yeah, so why no super solids?
Okay.
All those charge density waves and bosons.
Okay, well, so this is a 1D phase. Maybe it also super solid is like, okay, my knowledge on. Okay, I see. So proximate super solid quasi long range or something.
I think for that you need incommensurate filling, basically. Like if you have like some commensurate.
Thank you.
Right,
Fractionalized
commensurate on the bottom, so that one, and then on top of that, you have some guys on top who are not locked. That would be.
Okay, thanks. Then in practice, we just look at the regime where we started to want to see, but okay, makes sense.
Interesting.
I think in the interest of time, we will thank Ruben and move on to our last. Okay, excellent. So our last talk of the afternoon is gonna, I think, be a nice natural segue to Ruben's talk. So by Zhen, who's visiting us from Penn State. He's gonna tell us about average crystalline symmetry-protected topological phase.
Great, thank you, Fiona, for the introduction, and thanks for the wonderful workshop. Met many old friends and new friends. So it's very nice that Ruben has already made the groundwork for me. I'm going to talk about this class of phases where you have crystalline symmetry, protection of the topological phase, but crystalline symmetry is broken by some disorder, and you get some phases that are still stable under this average symmetry, and some other new phases kind of emerge because you have disorder. That's intrinsically. The most important slide is my student Shawish, who is the driver of this later paper, and I also benefit with your collaboration with Judah on this paper on some earlier work on this average crystalline topological phase, where we show some intrinsic statistical topologies which happen. All right, so just one page of brief introduction of SVTs. these are great examples of SPT phases where you have insulating bulk, which are symmetric and gap. And then you have some gap phase edge models which are protected by symmetry. Right? For example, if you have the ordinary topological insulators, you have charge U1 symmetry and time which symmetries. This will protect in the free finger limit Devakul on the surface of the 3D topological insulator. And similarly, similar phenomenology applied to all dimensions and different symmetry classes. Swan the Howden chain and Swan the topological superconductors. Also sometimes right. So the key feature is the bulk is gap, and the surface has some gap with smoke, which are protected by the symmetry. And in the bulk, it's nothing happens. The bulk would also derive this topological response. For example, in this topological insulator case, this famous axion in actual magnetism that tells you that the theta term, which is topological, and it is equal to pi for the non-trivial topological insulator. And in this talk, I'm going to concern about this other topological phase. And early on, people have understand that if you have a topological insulator and you have magnetic impurities which break the time to symmetry locally, but preserve the U1 charge conservation. If the time of the symmetry is preserved on average, that means that you have independent magnetic impurities, and these independent magnetic impurities average to 0 and have exponential correlation functions. Then the TI phase still survives. The rough picture of all that is that if you think about topological insulators, on the surface you have magnetic domains, and these magnetic domains, because the time of the symmetry is preserved on average, you have half and half probability being up and down. And between the domain walls, you will have these chiral edge modes. And if you are at the average symmetry point, that hints you at this percolation transition, where you have a large cluster that can propagate through the surface, would have non-local or delocalized modes. And many examples people know that extends this paradigm to crystalline symmetry, some weak topological insulators. If you average external disorder, these surface states are still delocalized. Many in the early works. Okay, so these are some earlier works where we have some general theories concerned about on-site symmetry, where you have some symmetry that are strong. In the case of topological insulator, one symmetry for strong symmetry, and then some symmetry is broken down by disorder to an average symmetry. And the general story is that some SPT phases we know are still stable if you break down part of the symmetry on average. Example being topological insulator, where you break the timeless average. So this is good. So some of the SPT phases have stabilities under disorder. And perhaps the interesting features we find is that there are some additional phase which does not have a clean state corresponding. That means that if you remove the disorder, you either don't get a topological phase or get some gapless phase in that case. Right? So you don't have a symmetric gap bulk with these nice surfaces. So these are kind of the Venn diagrams where you have clean system SPT and disorder system SPTs. And they overlap a little bit, and then there's extra stuff, which is interesting. So in general, this is a paradigm where we want to study phases of matter in mixed state. In this talk, we mostly focus on disorder system, but we can also view these density matrices being generated in an open quantum system where a pure state, and they're undergoing some the decoherence process that makes the system mixed. And both situations can be unified in some mathematical framework, but we didn't talk about particular examples for the disorder case, which I think is useful. So I'm going to talk about these two main parts. The first part is an example of what we call intrinsic statistical topology. The name is a little bit mouthful, but the statistical PI has been discussed in literature early on in 2014, where people have found with these other some PIs are still stable. And the new ingredient we think is that this particular examples does need the disorder to stabilize a topological phase instead of being a pure state topological phase reduction. these orbifices. And then I'm going to talk about some systematics of how do we think about these crystalline topological phases, and there's some partial computation result using a so-called generalized dot state. Okay, so I'm going to move on from this ordinary TI to another version of the TI with C4T symmetries. These are crystalline TIs. There's no ordinary time Rosa symmetry, but there's a C4T instead. And so for this model, which has been discussed some time ago, is for spinfold formulas like electrons. So C4T raised to the fourth power is equal to -1 to the power of formula. So these are crystalline generalization of TI. The state is kind of interesting. So you have a gapped ball, which respect to the C4T symmetry, and on the hinge of these on the 4 hinges of this cube, you would have chiral edgements, which are protected by this. So Hamiltonian is really simple. You can write down the 3D TIs in Hamiltonian and then add another term that break the C4T, break the T symmetry down to a C4T symmetry. So you get these phases to the gap and you get some chiral thing. Right. And the reason I want to talk about this is because to think about these topological phases with crystalline symmetry, there's a very nice way which systematically kind of classify them, is that there's a backbone structure of these crystalline TIs. You can think about these crystalline TI with these 4 hinge modes as you have in the bulk decorate these 4 planes which are related by C4T symmetry by 4 chain insulators, and each of the chain insulators has chain equals to 1, -1, 1, -1. So this decoration is consistent with the C4T. So this decoration will give you 4 hinge mode, and in the middle of this bulk, you have to turn on some symmetric interaction to get them out in order to get a symmetric bulk. That is the feature of a topological symmetry. So in this particular case, you can do this kind of construction and find that these 4 modes with that C4T symmetries can be get out by interactions. Okay, and we can also think about the surface along the z directions. If you have translation symmetry, then these decorations will be copied many times in the unit cell, and then on the surface, this surface resembles resembles the Trevor cutting models of quantum functions. Okay.
Sorry, then I have a first question. The leftmost picture, is this all real space? Is it mixed?
This is all real space. I'm talking about real space. Because that's the real space construction. This is a commonest for strong interaction as well. It doesn't use the band structure for this. Okay, great. So this is an allowed state of crystalline TI. But now I'm going to talk about just a little bit different, which will changes the symmetry actions of this formula. So it's a completely different system with stiffness formula where the C4T transformation now raised to the 4th power give you that. So there's no non-trivial tension between this crystalline symmetries with formula hierarchy. So then we can show for this symmetry class, in this particular case, this 4 mode, if you change the symmetry transformation to that, you cannot get a symmetric bulk. Right? So this analysis is simple enough that I can do on the board. If you have this 4 mode that transform into each other under this rotation, right? You can actually group this mode into plus mode and minus mode. So these 2 sectors have C4T squared equals +1 and -1. And then the C4T squared is actually relate these 2 into each other. So this sector, the plus sector, can actually be kept out. But the minus sector, as you can see, is a square of anti-unitary symmetry -1, which is just like the boundary of topology into 2D topologies. So this set of mode cannot be get out because it has this anomaly that is the same as the U1 cross P symmetry 2D. So this is a way to say that this decoration is no longer allowed in the clean case. In the clean case, you won't get a gapped symmetric bulk because these modes are anomalous under the symmetry. I want to show this more generally to whatever definition you do, you won't get a non-trivial topological phase within that. And the key insight that we can do with disorder is that with average symmetric disorder, if you break these C4P symmetries on these images with disorder, and then this 1D node can actually be localized and give rise to Andersons. So this declaration is still fine, but the way that you get rid of these bulk mode is by disorder that respect the symmetry on average instead being precisely. So this class of localization problem has been studied before, which I've said that the anomaly of these edge modes are the same as 2DPI with U1 times symmetry. If you break time symmetry on average, and that disorder could actually localize these edge modes. So in order for this to be more realistic, we actually designed a model. This my collaborators excellent work. So the way that we realize this is just we have these edge modes, right? So we just write down each of pairs of these edge modes as a counter-propagating 1D graph program. So you can regularize that 8 edge modes here, and that's a unit cell, and then you turn on some inter-unit cell couplings, and that respects the C4T for the most part, this one speed. So this is some microscopic model which I'm not showing. That here's the 8-band model, which literally just discretize this knot state construction. And this model really has 2 kind of phases if you tune the parameters T and M. One phase is a trivial insymmetric, M is super large, and you realize a trivial insymmetric phase. And if M is in certain region, you get some metallic phase. So these 2 phases depend on the model parameter, but it never shows that topological insymmetry because the symmetry does not.
But so does that mean that I should think of the gapless phase as a topological gapless topological phase? Is there it has the hinge modes, etc.?
Yeah. Yes. That's what I'm trying to say. So once we have localized the bulk by turning on this disorder, then this topological mode on boundary.
No, but before you localize, the
Before
gapless phase, does that have edge modes?
the whole thing is gapless.
Yes.
So I'm not sure.
You could still have edge modes on gapless.
Which, yes. In that case, I'm not sure if the localization is.
I see.
Yeah,
Okay.
I don't.
Okay.
I don't think it will be.
I see.
I think in all the other on-site versions of these intrinsically average SPTs, the non-disordered ones are IGSPTs.
Yeah, that's what I was
it would be
wondering.
surprising if this weren't.
At the same time, it would be surprising if it's a pre-fermion intrinsically gapless.
Yeah, okay.
Anyway, we should chat offline. Yeah.
So, right, so these are the models, and then we start from the macro phase, which is in the middle, and then add this on. So this is the numerical phase diagram in L10. And this is the disorder space, this is the mass parameter between. And then in the middle of this macro phase, there's a localized phase. This particular batch here is because when M is equal to 0, this becomes one-dimensional wires, so that is particularly susceptible to localization. So that's why you turn on a little bit of disorder, it becomes localized. Otherwise, we need to finite disorder. So this will be the phase that we are targeting at, and the method we use to calculate this is I didn't do the calculation, but so there is some ratio between this classic 1D localization and with system size. You basically take a finite size in XY and then infinite size along Z directions and calculate the formation function of this classic 1D system. If that divided by L goes down with the system size, then you know it's localized phase. So we did the calculation in 2 cases. One is periodic boundary condition, we do see a localized phase, and then if you do this with the open Z boundary, then you see this ratio doesn't go down. And there's a nice kind of topological average response that one can derive is that you put the system and then thread the flux along X direction and then calculate. So these are all free from that. So calculate electron electric polarization per unit cell, and that goes with the magnetic flux to this linear fashion, and we can extract the slope actually give you this average topological response. So this actually realizes the phase where it is a metal in the beginning, but then once you turn on solder, actually resembles a topological insulator in an average sense. Okay. So that's what we call intrinsic statistical topological insulator. And there was a nice paper many years ago, long before my career started. It's my colleague Zhang, and they study this topological and the insulator. It's actually quite different. What they study is that they have a fully topological insulator, but in the trivial phase. And then they put the chemical potential here, add the solder, and they see there is the emergence of a topological insulator due to the presence of the solder. So this differs in certain ways. The first thing is that the solder is a symmetry preserving. So they turn out some random chemical potentials that will stabilize this group reactors. And another way that they distinguish this is that for our case, a clean TI doesn't exist with that symmetry. In this case, clean TI does exist if you just inverting band. But they have already taken the names. All right. Great. So that's an example. Hopefully that's a useful example to keep in mind. And I'm going to talk about a little bit of systematic how we think about these topological traces using this generalized log state construction, which we have seen a little bit on the previous examples. So it's this third way of constructing crystalline TIs is this log state construction, sometimes also called topological crystal. And the input is a symmetry group, a spatial symmetry group in certain dimensions, and then you go through these 4 steps. It's kind of constructive way to think about SPTs. The first step is to do the cell decomposition. You decompose your cell into D dimension, D-1 dimension, and D-2 dimension, all the way to 0 dimensions, and each of these cells are related by symmetries. But these 4 sigmas are related by mirror reflection slumps. So this is one particular 2-dimensional PMM. So the reason that you divide the cell is that you can decorate lower dimensional SPTs on this high symmetry lines. Right? So these high symmetry lines have additional symmetries which are outside, and then you can put some SPTs on these lower dimensional cells, and then see if that give you a non-trivial SPT overall. For these higher dimensional blocks, because they have no symmetry acting on them, you can adiabatically or using unitaries to turn them into trivial vacuum. So those are hollow states, and the things that you decorated on these lower dimensional cells with higher symmetry. Right. So the second step is to do this decoration. But not all decorations will be fine. Right? So you ask, if you decorate, let's say, you have chain on these 2 cells, can we get a gap block by getting out the intersections? These intersections will have even higher symmetries. You will have another reflection symmetry here. So if we can gap out this lower dimensional intersection, then we see they're obstruction free. So you will be able to gap out the bulk, get a symmetric bulk state. So this is obstruction free condition. If you cannot gap them out, that means this is not allowed decoration. You will generate some gapless state in the bulk. Right. So and then this 4th step, which is a little bit sometimes hard to explain, is called double equivalence. So it turns out that you can generate some free state on these 2D blocks. For example, you can generate a Marana chain in this 2D block and then pop it out to the boundary. So these are free state. They can be shrinking to vacuum, so they are free. And if your decoration pattern are precisely generated by those kind of free operations, then your state will no longer be a SPT, will be a trivial state. So these are the physical interpretation of this spectrum sequence classifications of crystalline topological phase to each of these obstructions and trivializations are these checks in the spectrum sequence mismatch. Okay. So generalized block state, if you have weak disorder, so we assume there's disorder that does not break the lattice structure. For example, you have random chemical potential, random pairing, or random interactions. So those does not break the lattice structure, but it does break the lattice rotation and translation symmetries. And we assume that we can still do this cell decomposition. And then what is changed in these steps? So for simplicity, we will consider the cases where fermion system with exact fermion parities and some average crystalline symmetries. So the total symmetry group is a non-trivial, it may be a non-trivial. It's the extension between the symmetry group of fermion parities and some bosonic lattice group. And the trivial and non-trivial extension correspond to spin or spin formats. So we assume that the lattice cell decomposition doesn't change. And the block state declaration now can accommodate name stuff because now we have average symmetry instead of exact symmetries on these high symmetry lines. So you can accommodate ASPs. And the obstruction-free condition is also a different set of rules. We have seen this in the case of the first intrinsic set is group order. These four edges in the beginning is obstructed in the clean case. Sorry. Yeah, these are obstructed in the clean case, but if you turn on disorder, they can be localized. So the rule is that now you can localize the states, it becomes short range interval, then you declare this to a topological. So these are the two places where you could potentially have some new ingredients come in. Great. So let me just talk about two examples here. So the first mechanism for having an intrinsic phase is that it's the same as what we have talked about before. So if you have these decorations, they are obstructed in the clean case, but if you turn on disorder, they can be obstruction free. So the usual way we do this is say if you consider this PMM case, we have these Marana chain decorations, and these Marana chain decorations are obstructed because this reflection symmetry will forbid a mask. And that is equivalent to say that if you fold the system into a 1D system, this Z2 exchange symmetry actually protect a SPT, which is non-trivial. So that means these boundaries cannot get. But when you have on-site Z2 symmetry become average, that SPT order, the one dimension become trivial, so that they actually can be allowed declarations. So basically, you can turn on some random mass terms here that can get out these these actions. So that's one way that you can get intrinsic phases by generalizing these obstruction conditions. The other way you can get the intrinsic phases is actually the declaration itself could be intrinsic. And this is a 3D examples where just a mirror plan is present in the group. And the mirror plan is a spinful symmetries, that means mirror plan square could be -1. So there is actually a Z4F intrinsic ASPT. So this is the intrinsic ASPT with on-site symmetry. That can be decorated here, right? So this SPT doesn't exist if you have clean system. So this is a new SPT that you can decorate. So these are the two mechanisms that you can get some intrinsic states. And so far, what we have explored is this 2D cases with spinless or spin-full fermions with exact Z2 fermion parity and average crystalline symmetry. So you can think them as classification of topological superconductors with average crystalline symmetries. And you can see that the blue entries are the intrinsic states. They actually pops up everywhere on this. And we actually, there is a more mathematically rigorous spectrum sequence method that we kind of cross-checked between this mathematical structural sequence method and our physical decoration method, and they show consistency. All right. Okay. Really boring. So this is the summary. I want to convince you there's something new that comes out. You can consider this order, and these are intrinsic topological states, and block state instructions under certain assumptions can be used to classify these average crystalline SPTs. And of course, we would like to have more understandings of what physical properties and include the UN symmetries, so that we tackle insulators instead of superconductors. And some prescription for Alice model organized. And in the first case, we do have a prescription because we know these wires can be regularized by 1D.